Hey everyone, good morning. We're going to get started here in just a second. Just want to make sure we've got the right Discord invite out for folks. So, all right, sorry. Okay, yes, you should have sound, hopefully. Good morning, everybody. All right, sound has arrived. Hopefully you've got sound, you got video. So we just want to make sure that we've got the right Discord. We're in session topics now, and I guess we want people to go State of the Union, 00 State of the Union. So hop over there. We know everyone likes to, and actually, I think, Adam, we would feel uncomfortable if the audio were too good right now, frankly. Like, we want to make sure that, like, my S's are grading or whatever else you need to know that at least it's us. All right. And do we have the Discord invite up on the YouTube? Excellent. All right. So hopefully people have got the invite. The sibilants are on point. That's great to see. All right, Adam, we good to go? Good to go. All right, let's. All right, good morning, everybody. Welcome to dtrace.conf 24. The DTrace Olympiad is, I feel like we need to have the procession, the DTrace procession to the Olympic theme, Adam. We're very, very excited to have you here for an online conference. This is definitely a first for us. We are all online. So hopefully if you aren't yet, hop into the Discord where you can heckle me from the Discord, or you can join me in heckling myself from the Discord. We've got there's a lobby in the Discord, and then we've got a per talk chat, so we can, if conversation goes on a particular talk, after that talk, we've got a channel to do that in. And then we want to still keep with kind of the unconference vibe. So if you've got something that if you've got something you'd like to present to us, it's not too late. Hop into the session topics, drop it in, and we'd love to hear from you. So you are at dtrace.conf. This is our accidentally quadrennial conference. So for those who haven't heard us, we described this history on the podcast on Monday, but the first dtrace.conf was in 2008. Adam is featuring the shirt from exactly. We're going to get Adam come into the frame here. Adam has got the lovely shirt from our DTrace.conf 2008. And I actually am wearing, everything's got meaning around here. I'm wearing the shirt from USENIX 2004. This is a shirt that is older than all of my children. My oldest is 20. As I was leaving the house this morning, I'm like, this is a shirt that's older than all of you. My 17-year-old says, "Why do you have a shirt that says unisex on it?" I'm like, "It says USENIX, not unisex." So anyway, having to educate my own children about the history here of USENIX. But so in 2008, we had this DTrace conference, and as I was trying to recall this, this is kind of before social media. Like, how did we even advertise this? Like, how did people sign up? How did people know anything about it? And as it turns out, Adam, we used this old thing called email a lot back in those days. There was like an email list of people who were interested in DTrace. So it's like, sure. Exactly. And you would actually, so that was a bit of a surprise. But I kind of found my initial post to this DTrace list that was at Sun at the time. And you you signed up for this conference by editing a wiki. So very much of its time in 2008. It was an unconference, which was the style of the day. You wore an onion on your belt, and you would show up to a conference where the first thing you would do is people would say the things that they wanted to talk about, and we kind of went to the whiteboard. And so we had no agenda when people showed up. We had a couple of folks that we knew wanted to present, but really no agenda beyond that. And we put the agenda together on the fly. It was a lot of fun, and it worked out great. It was a great conference. And in fact, it was so good that we was at the end of the day, and we were still we were having drinks and dinner. And Stephen O'Grady of Red Monk said, I got to hand it to you, this was a really amazing conference. But next year's going to be worse. Like, you just can't recreate this next year. And the year after that will, of course, be worse still. And everyone's going to compare it to this year. And it's like, wow, okay. Can't even get through the conference without being bummed out about next year. So we decided we're never going to hold this thing again. We're going to be one and done. That's it. It's going to be just going to have to live in our memories. And then by like 2012, we realized we kind of forgotten about it. And it's like, what we should do is an Olympiad cadence. So I'm not sure if there are other, there are some other conferences that have this like very infrequent cadence. The history of programming languages is one of them. I think it's great. I think more conferences should do this, but it's definitely a little bit weird. Every year for dtrace.conf has had something kind of like of the year. In 2012, we announced a new Illumos distro, as one did, as was the style of the day. In 2016, DTrace.conf 2016, DTrace.conf 2012 was at the Children's Museum here in San Francisco, or across the bay in San Francisco. In 2016, again hosted by Joyent. And perhaps befitting the style of the day, all of the videos were on a Vimeo account that was accidentally downgraded to the free account, and the videos have apparently been lost despite my best efforts. I'm really gutted to have lost the videos of 2016. And I still haven't, I guess maybe I should say the videos haven't been found yet, but I think those hikers may be dead, unfortunately. They've been gone for a while. So that was in 2016. In 2020, befitting 2020, it was canceled. We just, like everything else in 2020, it was canceled. We didn't have anything. Unlike the Olympics, maybe in 2020, we didn't reschedule. And we were also obviously busy starting a new company here at Oxide. And then befitting the style of 2024, we have shamelessly cross-promoted it across all of our media channels. Like and subscribe, hit that like button. I guess we didn't do a TikTok. There are certain depths to which we will not stoop. So also, I don't know that I'm afraid to install TikTok on my phone. Yeah, isn't that illegal now? Anyway, so anyway, your DTrace.conf 2024. Welcome, and befitting the style of 24, we have gone strictly online. So we're really excited to have you here with us. And I wanted to talk a little bit about DTrace since 2016. So really, by any measure, DTrace is a mature technology. I always hesitate. I never want to say DTrace is done because we don't want to think of it as done. But the reality is that it's got like a plate tectonic like rate of progression at this point. We just haven't had to do a lot to it. The most recent feature, I could be wrong on this, but and maybe Patrick's on the stream can correct me. But Patrick did writable uregs in 2018. That's the last feature I can find. So we've not added a lot of features, but DTrace itself remains in heavy use. And I should knock on wood here, because by saying it works, I am inviting the gods to punish us with some sort of horrific DTrace bug, but it does broadly work. And there have been bugs in DTrace, not many. Really, since 2016, Luke Manaden at Oxide found this bug that I referenced to here, Illumos 16480. This was fun because this was a bug that has been in DTrace since the very beginning, but only a compiler change surfaced this bug. And it was fun when Lukeman fixed that. So that was great to kind of have a bug that's been there since the beginning. We can't quite go Don Knuth and offering escalating bounties for bugs in DTrace. I would never go that far. But it does broadly work, and we've had the rate of change has been very, very modest. Very few bugs found, honestly. There are also one of the things that since 2016, we've done a little more reflection back on the origins. Adam, you had the idea to do a DTrace at 20 episode of Oxide and Friends, which was really great. And then perhaps riffing on that, P99Conf asked me to do a DTrace at 21. I promise I'm not going to do a DTrace at 22. I'm not going to do this every year. Where I think we're just going to treat like 2 decades and legal drinking age as separate milestones. But then I guess we'll do DTrace in its midlife crisis when it's 50. I don't know if I'm still ticking. But I don't want to necessarily kind of repeat some of the things we had said there. I thought those were kind of a great opportunity to reflect back. I really actually enjoyed the opportunity, P99Conf, another online conference, to kind of look back on some of the things that we had done right, some of the things that we kind of learned along the way. And then I think very, very importantly, the aspects in which we got lucky. I think people don't like to talk about when they got lucky. Everyone, I'm fond of saying that success teaches you nothing, in part because people always like to factor out the luck factor. No one wants to say like, well, God, I was really goddamn lucky. We were really goddamn lucky with DTrace, just to be clear. We did a lot of things right, but we got very, very lucky. And we were kind of solving the right problem at the right time was one aspect of luck. And then honestly, another real aspect of luck, something that we really didn't control, but was very much in our favor, is the fact that DTrace was open sourced. Didn't have to be. DTrace was born in a very proprietary era of operating systems. And, by the time we were talking about open sourcing the operating system, I was personally very enthusiastic for it because I remember vividly thinking at the time, this technology is so useful to me that it would be really awful to not be able to carry it with me my entire career. And now looking back on that, 2 decades ago, and the fact that we have been able to carry it with us our entire career or our careers, and it's gone in so many different places. It's gone to different operating systems. It's inspired different work. And the fact that it's open source was a huge lucky break for us, an existential lucky break. So we feel very, very appreciative of that. And then, of course, that what you said, we were in the right place at the right time with the right group of folks. So we really feel fortunate about that. So given that this is kind of like a mature technology, given that it is, we again, not done with an asterisk, perhaps, why have a conference on a mature technology? Well, one, because it's just fun to get together and it's cheap. We're doing it on the cheap. So why not? Also, I think we wanted an opportunity to make an awesome t-shirt. You saw Adam's shirt. Alan is kicking around here. Alan, do you want to come fashion model the dtrace.conf shirt for 2024? So we were inspired by the shirt that we had in 08, but that we took this is an actual gimlet. I don't want to actually like touch your body here. I think, but we actually, a lot of them, I'm very tempted because I want to point out so this is an actual gimlet sled that is, that's blown up here. And so Ben Leonard, our designer, did a terrific job. You got kind of oxide on the sleeve. So, if you're gonna, there you go. Thanks. we need like a cat in here to go after the camera. That'd be now. Okay, now Alan's playing with the camera. So you've got your shirt. Hopefully, if you haven't already, you can go get that Oxide shirt. So I think we really want an excuse for a shirt, Adam. That was part of it. That's a big reason to have a conference on it. But I think we also just wanted to talk about how this thing is being used. And for that, I actually want to go back a little bit because one other, I wouldn't say a change since 2016, but something else that has happened since 2016. So in 2017, Charles Beeler, a venture capitalist who unfortunately passed away recently, but was very influential for us, for me personally, for my co-founder, Steve Tuck, and me, Charles was running the Node Summit. And Charles was asked me to give a talk on Node.js in 2017. Now, if you know anything about the history of Joyent with respect to Node.js, 2017 was after the relationship had become rather complicated, which is really a euphemism for saying that we basically divorced. We had decided that our future was really, we had this really kind of heart-wrenching breakup as the direction that the community wanted to take Node.js and the direction that Joyent wanted to take Node.js were really not the same direction. Charles was like, I think it'd be great for you to give a keynote. And I'm like, no, that's a bad idea. I got nothing nice to say. Like I just feel like that's not gonna, he's like, well, I really think actually, if you got nothing nice to say, that's an even better keynote. I'm like, okay, that's deranged. But it did actually, let me actually think about what went wrong here. And I'm really grateful for the resulting talk, which is platform as a reflection of values, because it really caused me to think about, like, wait a minute, because in Node.js, we had well-meaning people that really did not see eye to eye. And, this kind of the split up was on the one hand heartbreaking, but not necessarily acrimonious. It's just that we were going in different directions. And it caused me to reflect on, like, why do things go the directions they go? Like, why do we pick things to work on that we work on? Why would we be in some communities where we agree on things and some where we don't? And you kind of look at these underlying values that will bind a body of software together, bind a work together. And as part of that, I reflected back on the values of DTrace. I looked at the values of a bunch of different things, but and I kind of threw out a bunch of different values. And the thing about values is, like, these are all like good things, but you're choosing among them. As I was thinking about some of the things that we made the deliberate choice on about DTrace, like, what did we choose? Some of the values that I highlighted for DTrace: safety, operability, expressiveness, and velocity. I kind of hate the term velocity because it makes people sound like a projectile, but velocity in terms of the ability to go from ideation to embodiment of that ideation very quickly and iterate. These are 4 values that I highlighted for DTrace, and these are, I think, essential, each one of these. And I think you could talk at length about each one of these values. I mean, you all know how important safety is to us and how much we view safety as a constraint on the system. That it has to be true that you can go onto a production system and use DTrace and not be worrying about what DTrace is going to do to the system. And we've done a bunch of things for the safety of the system. Some of them were like very clear about what we need to do about safety. Some of them were more subtle. I mean, one of the things that when you are have a D program, you can have effectively arbitrary memory references in that program. And it's very important that if you reference memory that's not mapped, that we don't panic the system. Obviously, we don't. But it's actually, memory is more complicated than that because there is memory that has side effects. So you need to be sure that DTrace is not permitted to issue a load to memory with side effects. And there are a bunch of things that we had to go do to assure that. There are things that we learned about safety that we had to learn along the way. One of the things that we learned is, and you probably have heard us over the years say, that the disabled probe effect of DTrace has to be 0. It's very important for DTrace to be present in a production system that the disabled probe effect is 0. And the enabled probe effect, we were a little bit less concerned about. The enabled probe effect we knew would scale with the kind of the scope of the question. If you enable every function entry and return in the kernel, that's going to have a much more invasive probe effect. But one of the things that we learned is that if you have something that's really invasive, and then you do something very intense on those enablings, the canonical one was a UStack. So if you get a UStack allows you to get a user level stack backtrace on kind of an arbitrary point, either in the kernel and userland. And we added the ability to have what we called UStack helpers that allow you in a dynamic system. Java in particular was kind of the use case of this, but we did it in other languages, including Node, Python, and some others. A UStack helper did kind of this not unbounded amount of work. It's not Turing complete, but it could be like just a lot of work. And if you do like a lot of work on something that is happening frequently, in particular would happen out of, say, a profile provider. And if you want to do something, 1,000 times a second, and it's going to take you more than a millisecond of work, which was not inconceivable for some of these really invasive things, you would have a system that was no longer responsive. So one of the things that DTrace does, and if you've never seen this, then you've never known this sense of terror. If you have seen this, you know what I'm talking about. When you run DTrace, and all of a sudden the system seems to have gotten very, very sad. Up, but sad. Pingable maybe, but like your terminal is like, I'm not getting any response to your terminal. Heart rate beginning to escalate. And after not too long, you will see a message, DTrace aborted due to systemic unresponsiveness. And DTrace imposes its own liveness criteria on the system. And if the system fails to meet that liveness criteria, DTrace assumes I am to blame and I'm ripping down my enablings. When that is correct, and often is correct, like DTrace, you were to blame. That is great. That good intuition. You were to blame. That is a bullet that just whizzed over your ear. And something that we added to the system slightly later. I mean, it was maybe a year or two after we had initially integrated DTrace that we added that. For each of these things, there are stories like that, where that do maybe set DTrace apart from some of the things that came certainly before it and to a certain degree after it. I mean, operability is super important to us. It's very important to us that DTrace is entirely present on the system that you need on. You don't have to install packages or download things or what have you. It's all there. It's very important that you can express. We want to allow you to express your question concisely. You shouldn't have to ideally instrument the system in terms of its implementation details. You should be able to ask your question pretty directly. And then we want to be able to do that really quickly. So it's important that you are able to ask a question, get an answer, ask a question, get an answer, ask a question, get an answer, and do that iteration very, very quickly. So each of these is essential. But there's a value that I didn't highlight there in that talk, in part because I was, throwing it together at the last minute. But a value that actually for DTrace is an overriding value, and it's worth expanding on a little bit, and that's utility. So the single most important value of DTrace is its utility. So, and this is a bit of a contrast, certainly from the things that came before it. So historically, people that worked on debuggers didn't actually work on debugging things. In fact, the thing they would debug is often the debugger or the compiler. Debugging groups often came out of compiler groups. And one of the frustrations with kind of the state of the art of debuggers in like the 90s is they were really designed for this kind of in situ debugging of kind of dead reproducible problems. Dead reproducible, a term that we agree that, like, I didn't invent that term, right?
Yeah, people get what it means.
They're right. Okay. Very reproducible, which is like a problem you would have in a compiler. And it doesn't actually match what a complicated system that is misbehaving. In situ breakpoint debugging is not that useful. It's a technique that you kind of want to have, but it's like there are many other techniques that are way more important because you can't stop the system. You can't afford to stop the system. It's a production system. In DTrace, we developed the thing that we needed to debug the system. We use DTrace ourselves to actually debug the system, understand the system. And that is the utility of DTrace. And it's like really focused on that utility. Understand the behavior of production systems. We're not actually trying to do more than that. I mean, one of the things that people looked at early on, it's like, oh, I could use DTrace. I could like implement hot patches in terms of DTrace. I could actually modify the operating system. And we're like, no, we don't want to do that because that doesn't serve our utility. Our utility is the comprehension of a production system. And everything that we do serves that goal. And we then ourselves use DTrace and have augmented DTrace, have fixed DTrace, but have extended it to serve that goal. And you've heard us use a couple mantras over the years. Concise answers to arbitrary questions was kind of our tagline when we were developing it. Another thing you may have heard us say over the years is that the proof of the debugger is in the debugging. It is kind of easy in a debugger to do things that seem like they would be valuable, but actually aren't valuable. So we've always believed that if you are extending the system because you're debugging a problem, that is something that has utility. You know you need it because you're debugging a problem that needs it. In the same vein, we've always said DTrace is a workhorse, not a show horse. So DTrace is designed to be put to work. And sometimes if you look at the arcana in DTrace, and there's some real arcana. In fact, the name of this very conference, dtrace.conf, the conference named after a driver configuration file, and all drivers have in the operating system have configuration files. The dtrace.conf file is somewhat special because we use that configuration file to specify properties of DTrace. Well, why would you want to do that? For this somewhat arcane feature called anonymous tracing, where we can actually instrument the system during boot. And actually, one of the things that at Oxide, one of the things that actually I love that we've added to the system, Andy Fitteman, who unfortunately couldn't join us today, but added to the system, is the ability for in the Oxide rack, we actually can pull that comp file from actually over our we call IPCC from our service processor. So from our control plane, we can, without modifying the operating system, change what we trace during boot, which is really pretty neat. But arcane. And it's like, you don't frequently need to instrument during boot. That is not something that we do frequently. When you need it, you really, really need it. So if you've used DTrace a lot, you've been around people who use DTrace a lot, one of the things you'll hear people say is like, there are these features that when you don't need, you don't care about. But when you need it, you really, really need it. And that's true of anonymous tracing. It's true of, it's true of aggregations and thread local variables and clause local variables. But it's true of things like speculative tracing. You may look at speculative tracing and mean like, why is that important? It's like, well, we've used it to solve like real problems. That's why it's there. It's there because it has been used to solve real problems. And when you see that arcana, for effectively all of it, there is a story behind it, a bug behind it, a time that we needed to extend the system in this way. And because utility is so important to DTrace, a part of the reason to get together, even when the system is so mature, is to talk about some of that utility, talk about the way people are actually using DTrace. So a bunch of the talks you're going to hear today are from people that are using DTrace and showing you how they're using DTrace, maybe some of the patterns they're using, but we are using it a lot here at Oxide. So we've got a couple of different folks who, when we were talking at the conference, like, God, I don't know if I have much to say. Like, I use DTrace all the time, but like, I'm not sure I've got much to say. It's like, actually, that use is something to say, and that's interesting. And you're going to see a couple of folks today, we're excited to show you that. So that's like a reason to get together, is to kind of talk about that utility. And we love seeing that. We love when people are actually using DTrace. If you're new to DTrace, you're kind of looking at it from the outside in, We really encourage you to get in and actually use it. We're going to have a talk today from Dave Chico on how do I learn how to use DTrace? Because one of the things that Dave has done here at Oxide is introduced a bunch of new people to DTrace. So you're going to hear, I would really encourage you to jump in and go do that. And Adam has got some great resources he's put together that Dave's going to point you to from a long time ago now, but the things that are still very much germane. Another reason to get together is because the DTrace values are not actually unique to DTrace, of course. We share values with other systems, with technologists and other domains. And just as, frankly, DTrace was very inspired by systems that preceded it. I mean, and you see that inspiration in a bunch of different places. I mean, we've been very upfront about the inspiration we drew from awk. If you look at that kind of that velocity and expressiveness, it looks and feels like awk for a reason. We did learn when we were going in front of the architectural review board that, at least at the time, I'm not sure if this is still true, that compiler people actually are not so into awk. That I remember we were in front of our PSARC review and one of the reviewers said, I don't know, this just looks a lot like awk to me. And we're like, highest praise. Thank you very much. Highest praise, unworthy of that praise. Thank you. And then you realize like, oh, that was actually, sorry, that was an insult. I didn't realize that was an insult. We loved awk. We love awk. We drew inspiration from awk. We drew inspiration from other systems as well, certainly from Lockstat. A bunch of other systems that we drew inspiration from. And then DTrace has inspired other systems. And you're going to see some talks today on some other systems that DTrace has inspired. You're going to see some talks about, and we got Chris here with us in the studio. We're going to get a great talk from some of the work that Chris has done on the DTrace port to Linux, and in particular, using eBPF as a backend for DTrace. I think I'm really excited to see that. And you know, how can we kind of take these values to another system? How can we take these values up stack? And Nahum's got a talk that is that I don't think is actually directly DTrace involved at all, but is a lot of those same values about the comprehensibility of a production system. Very excited to see that. So you're going to see some talks from some other bits of the stack that have those shared DTrace values. So we're excited for those as well. I think we might even get a talk from Rye on some of the stuff that he's done and is doing. Really, really exciting stuff there. So in terms of DTrace in 2024, you know, I said DTrace hasn't changed much, and that's true. I mean, the core of DTrace has not changed much. The world, however, has changed a lot. I mean, one thing that's interesting is to think about, you know, from 2008, 2012, 2016, it's like the world has changed a lot. And, you know, we think about 2008, going back to the video in 2008, where I was thanking Ben Rockwood for videotaping us. And I'm like, God, when is the last time that I said videotaping in earnest? Like, I hope it was that day. I got a hunch I was, you know, using that all the way through 19-dickety-2. But you know, you think it's so long ago that we didn't, you know, this is like we barely have photos of dtrace.conf in 2008. And even since 2016, so 2016, 8 years ago now, you know, not much has changed in DTrace. A lot has changed in the world, and in particular, the rise of Rust. And you know, those of you who follow Oxide, and indeed in the name, you know, it's a tip of the hat to Rust. Rust has been essential for us, and Rust and DTrace share many values. There's a shared worldview around first principles thinking and rigor, comprehensibility, understanding the system. And it's really unsurprising that these two demographics have kind of found one another. And, you know, I think if you look at folks, certainly at Oxide, there are people certainly at Oxide to whom Rust and DTrace were equally new. There were also plenty of people who were kind of coming from that C world, new DTrace well, and were learning Rust. And then there are plenty of people who were coming from the Rust world and learning DTrace. And it's been fun to kind of bring these two demographics together because really they are turning into kind of a single demographic around shared values. And I think the most important work DTrace related work that has happened since 2016 is the work on the USDT probes in Rust. So Ben Knacker and Adam did absolutely terrific work on the USDT crate. We're going to get a talk from you two early on in the day, and I think it's important because that foundation has been, I mean, absolutely essential. I mean, this has happened a lot for DTrace with me in my career of like, oh my God, what would we have done without this feature, or what would we have done? And what would we have done without the USDT crate? I mean, I guess we would have done the USDT crate, which is why we did it. So it's like we actually know what that world was like because that's why we did it. But this is one of the very first things that we did. That was done, I think, in like 2021. I mean, pretty early. And I'm like, hey, I think we might need this. And it's like, of course, absolutely. But like a lot of things, DTrace, holy shit, if we need it. I mean, this thing has bailed us out so many times and has been very, very important for us to understand the system. To the point, I mean, just like to keep it very current, we had an issue just this week. We're trying to understand like why we had a transaction that was much larger than we expected in the database. And one of the things we needed is like we needed some additional probes to be able to understand it. It was like a top priority to get that done because we desperately needed DTrace. We use it all the time to understand our system that we've built at Oxide. So for us, DTrace and Rust are I would say two great tastes that taste great together. But I understand that is now an extremely dated reference, but that is that is about chocolate and peanut butter coming together for you millennials. This is chocolate falling into peanut butter or peanut butter falling into chocolate and vice versa. I think I need to stop making this reference because I explain it every time and I make it sound like even weirder. Like Gen Xers are like, why are you bothering to explain? And millennials are like, what are you talking about?
Yeah. It's just like so deep.
It's just so deep in the psyche. I just can't get it out. I'm so sorry. So anyway, here you are. It's the Gen X Storytime Hour once again. So this is kind of where the state of where we are in DTrace in 2024, and of course you're at dtrace.conf. We've gone completely online this year. One of the things we definitely appreciated is that with people much more dispersed, with the cost of travel high, with our conference admittedly like a little off piste, I would say.
Yeah. Boutique.
We recognize this is a small conference. This is one might say weird, but a little offbeat, a little boutique, a little off-piste. That it's not something that's necessarily easy to justify travel for. So part of that zero cost, and really we wanted to make it accessible to everybody. So went completely online. So really excited to experiment with this. I know a bunch of you are already in the Discord. If you're not, hop in there, where you can, the Discord has been, as presumably many folks know, but Adam and I co-host a weekly podcast, which used to be a Twitter space. And there's certain things some things, very few things, maybe a thing or two. I'm not taking I may miss something. I reserve the right to miss something about Twitter spaces, even though I can't think of anything right now. But the thing that we actually love about having Discord for the podcast is that Discord discussion ends up being a really important part of the podcast and feeding back into and we monitor that discussion and feed that back into the content. So really excited to see your contributions today in the Discord. Hop in there. I would also say that kind of keeping with that unconference vibe, it's not too late. If you got like, God, I got something I would love to present on today. Hop into the session topics so we can know who you are and kind of get you slated in. We don't have an actual schedule, but we do have an ordering. So we have some people with time constraints. We want to make sure we get them and able to either go to bed at a reasonable hour for those who have joined us from Europe, or be able to go on to the next commitment. So we do have an ordering. So hop into session topics if you've got something that you'd like to present on or say. We want to keep it light. As I was telling folks inside of Oxide, we want to keep we call it Demo Friday vibe. So every Friday we do demos, very unstructured. People can demo something very small. That's okay. You got something like, I think it's only gonna be like 5 minutes. Hop on there. We would love to hear from you. So hop into session topics there. Again, hop into the particular topic for each talk. We will be taking breaks of the day. When we take a break, we'll hop up with a placard to let you know when we'll be back. So so you can also be able to step away. Obviously, everything is recorded. All the recordings we made available. We're not going to lose them this time. I'm not going to lose them this time. We're not. Definitely not putting them up on Vimeo. So forget Vimeo. They'll be up on YouTube. We are on the one hand, it's been lighter lift to do an online conference. On the other hand, it's definitely not zero lift, and there's a lot that needed to be done. We are hugely grateful to Kevin Spring on the Oxide team for all the logistics that Kevin has done in terms of setting this thing up. Please, nobody tell Google that they have accidentally created a terrific integration across their properties between Google Meet and YouTube. I know if you're the Google employee who did this, I know you did this against your management told this is not your OKR. Why are you doing this? I think this might be valuable for people who use our products. What? No, that's not what we optimize for around here. Anyway, if you are the Google engineer who did this, thank you very much. If you are at Google and were previously unaware of it, please don't make it your OKR to kill it, because we are loving the fact that we can have a Google Meet here that we can really easily stream out over YouTube. So really terrific stuff. Thank you very much to Google there, and thank you for Kevin for getting all of that set up. We're very grateful for Ben Leonard, our designer, who has designed everything Oxide. When you're looking at anything Oxide, you're like, damn, that looks good. That looks good because of Ben Leonard. So we are very, very grateful for Ben and his t-shirt design. And I've been using the first person plural because this has been such a team effort between Adam and me. But Adam, thank you very much for being my partner along the way. We've had and being on the podcast, and Adam has been really encouraging of us to let's do this. Let's get everyone back together. And we made our pledge at the DTrace at 20 episode that we pledged there would be a dtrace.conf 24. Here we are. And then for those of you who do happen to be in the neighborhood, we'll have a social event after the conference tonight. And so if you can join us for that, that's great. You can go get the tickets online for that. So, and then finally, thanks to all of you. Thanks for joining us. Really, really excited to have you here. Really excited for the ongoing use of DTrace for kind of expanding that community, and excited for all of the new folks that are using it. And with that, let's kick off dtrace.conf 2024.
Awesome. Do we want? I think the most salient comment from the chat was someone loved your Forkyard talk when they were in middle school.
They were in middle school. I was like, there you go. I was under the sheets watching that at night when my mom told me that. Yeah.
So that I also had a little quiz for you.
Yes.
When do you think awk was released?
When was awk released? So, I mean, it's obviously, I guess, I don't think, I would say it is in 1979.
It's pretty close. Beta, early versions in I think 77. I think the first full release was in 83. I just point this out in that DTrace is older now than
awk was then.
Awk felt
old,
very old.
Right. Yeah, I see what you're saying. Thank you. I appreciate this.
Well, there's a theme.
There's a theme. You know what? And I appreciate Adam is trying to make me feel old, which is good. It's honestly, you were in middle school for Fork, doesn't move the needle.
Yeah.
I mean, it's whatever. I had kids that weren't even born yet. So it's I know, lame. But the awk thing that does actually, it doesn't. When I first came to Sun, I was the youngest person in kernel development by a decade. And being, a young Turk. I wanted to make everyone else feel old. And I kept like trying to shop around to get currency on. And I was this when that happened. I was this age when that happened. I was in high school when the Berlin Wall came down. Nothing. And we're all walking to lunch. And I'm walking with like 9 engineers. And I'm just like, keep fishing around. And finally I said, I was 3 years old when Star Wars came out. And it was like they had all been simultaneously punched in the gut. People like literally doubled over because that was like, okay, that's the sweet spot. Like I was 3, you were 13. Like, and anyway, and I know that
Last comment of that, Tom Lyon says he was there when Aqua was being written. So,
there you go. Exactly. So sit down.
there we go. Do we want to take a break till 10?
Sure. Yeah. We'll take a break. Let's resume at 10 o'clock. And I think we've got you and Ben up on deck. So we'll be take a quick break and we'll see you back in just a couple minutes and with our first talk. Awesome.
Right,
Thanks, everybody.
is coming here.
He's installing Chrome.
Yeah. Hey, folks, just a couple minutes. We are installing Chrome to do the fancy screen sharing. So I'll be right back. All right. Chrome installed. We are back. We are 4 minutes later than anticipated. Hey, folks, I'm Adam Leventhal.
I'm Ben Necker.
And very excited for dtrace.conf 2024 to kind of pass the baton from Brian's State of the Union. We wanted to talk about work we've done building a USDT provider for Rust. Now, in particular, because like we're going to see a bunch of work over the course of the day that builds on this, that uses it. So wanted to start out as the foundation. So talking about the past, present, and future. But we realized that like actually the present is like much more urgent and exciting. So we're going to start with that. So the present of DTrace and Rust. So fairly early on in Ben's tenure at Oxide, fairly early on in Oxide, full stop. You said it was February
18th of 2021.
There we go. So
it's the first commit.
Pretty early. We figured out like we're going to want these probes. We'd seen the use of USDT probes in lots of different uses in DTrace. And I'm going to talk about this later, but USDT I think is arguably one of DTrace's most successful accidents, or at least accident in terms of the breadth of its utility. And again, I'll talk about that later, and its origin in perhaps too much detail, but you know, you can go for it. So we've used USDT early on in Sun, in C programs. We used it in Java. We started using it in JavaScript and other dynamic languages. And in all of these, we've seen this virtuous cycle play out where probes give us better debugging, and then that better debugging leads to more probes, and that leads to yet better debugging. So we knew we wanted to kick this off early on
and make it possible to add these DTrace probes everywhere we could conceivably want a DTrace probe. And importantly, we want to make it easy. And when I say guilt-free, I mean, like, it's not going to create overhead. It's going to be a thing that we can add pretty much everywhere that we find some salient point of interest. So userland statically defined tracing is for identifying statically these interesting places to dynamically instrument.
So, I think I want to start by kind of talking a little bit of just about how you actually mechanically add these probes. And it's, as Adam said, we wanted to make it as easy as possible to do that. And very early on, so that as you build the code, you're kind of doing it, you're sort of building these things side by side. You're debugging it yourself, you're building it yourself, you're deciding what the interesting things are as the developer. So you can, decide which points to instrument, as you're building it. And then as you debug it, you can say, well, I should have had this probe here, I'm going to go do that. So it's really just 4 steps today. In Rust, right, you just cargo add the USDT crate. Then you define this module that we have here. It's decorated with this macro called USDT provider, which just basically says make this available as a provider. And then there's a bunch of function definitions in that, which just look like normal Rust functions. They have empty bodies, but basically the signature of that describes what the name of the probe will be and then what the arguments are. And we'll talk about this a lot, but you can put, we started with sort of the integral types, things like integers, and strings, but then we ended up adding a bunch of really, really useful support for basically any Rust type, which is, I think, extremely valuable. So you can have as many of these as you want, you can have as many providers as you want, and then you put them in your places of interest in the code by calling, in the 3rd bullet point, this my provider :something, and you'll notice it's a macro. That's the first thing that's interesting. And the second thing is that there's a closure here. The double bar is a closure in Rust, and it returns the arguments that you're going to emit in the probe. We'll talk about why that's important later. And then you just call DTrace. So you can see here, we're just tracing this first argument. And I had a little dummy program that's just sitting and incrementing this counter in a loop. And you can see this counter going up. So it's very, very easy to add these things. It's so easy, in fact, that we're going to do it live in a few minutes, and I'll show you guys how to actually do that. And it's really just a few lines. I didn't want to take a little bit of a sidebar into kind of how this actually works, because it's a pretty cool mechanism. And so Brian had mentioned at the beginning that there were people who were familiar with Rust but not DTrace, and that includes me. So I knew Rust when I joined Oxide, but I had basically knew of DTrace, but that was about it. And this was a really cool project for me, kind of coming in initially, because I got to work really closely with Adam, who built the fucking thing, and then I can understand exactly how it works, and it's a very cool mechanism. So what I have here is that macro. I ran a program called cargo expand, which is a subcommand that takes things like macros and derives and all those sorts of things and blows them up into the code that actually then gets passed to the compiler for code generation. And you can see here that there's a few things. We call this lambda here, a closure here, to get the arguments. So that's that thing I mentioned where you provide the macro with a closure. And then we are destructuring all those arguments, and then we call this little inline assembly, this ASM bang block. We call this inline assembly, and really the important part here is the NOP and then the arguments, which is the second line. So you can see we're passing in one of these arguments in registers. The USDT probes have this fixed set of registers that the arguments are supposed to be put in, and we have support today for up to 6 of them. But this NOP is the really interesting part the part that I found really interesting when I first learned how this works. So these points, as we mentioned, are static in the program text. There's this NOP, and then we can talk about this later, but we separately record where those NOPs are in the text. When you ask DTrace to enable the probes, when you do that DTrace -n, whatever the probe is, it finds this NOP looking up that saved location, and it rewrites it. It dynamically rewrites that in the program text from a NOP to a trap. And so that traps back into the kernel. The kernel knows where these arguments are, and then it will run your set of actions that you've described in the D language, given all of these arguments. And so you can do lots of really cool things, like make probes that are conditional, or you will run actions that are conditional on other probes, and all of this stuff is really the power of DTrace that we've all seen. But the cool part here is that we talked a lot about the zero disabled probe effect. It's just a NOP in this case, so it really is as close to 0 as you can get, and we'll see. the next slide actually, how these enabled probes make certain things even lower cost. So this is the same cargo expand output, but here it's for this specific part of the probe that is this is enabled guard. So in the kernel, we don't have these kinds of things. These probes are sort of always enabled, but in USDT, early on, they put in this idea of guarding kind of complex work in creating probe arguments behind this is enabled guard. So here, what we're doing is we're emitting some inline assembly. We have this is enabled flag. We're emitting some inline assembly, which by default is just clear racks or set racks to 0. And now, when you actually enable the probe, in addition to rewriting that NOP, what we saw on the last slide, DTrace comes in and rewrites this clear to be a move 1. So it's sort of setting this flag to true, and then the rest of your code runs, right? So that's where this if is enabled is not 0. Do some other stuff. So this is part of the reason that we provide the probe arguments as a closure, because if it's not enabled, that closure will not run, and we wanted to make very, very clear that that's an important piece. So if you can't rely on side effects, you can't rely on sort of anything. All you really should be doing here is the work that's needed for the probe, and that's kind of it. You shouldn't be doing anything else.
But it's also the case that even if computing the arguments to the probe is like monstrously complicated or expensive, like that's fine too.
Yeah,
because that's only going to happen when this is enabled predicate evaluates the truth.
That's right. And so you know, it's not literally 0 cost, and that you kind of have to evaluate this instruction, this clear racks, but it's about as close as you can get in any real system. And so yeah, you can compute much more complicated arguments, which in fact we do. We'll get into in a minute when we talk about passing arbitrary Rust types by serializing them into JSON. So we'll talk about that in a second. But this is one of the really important things, I think, that made us feel pretty good about adding support for things like, you know, any Rust type, because that complexity and the cost of doing that serialization is all only under, you know, probes being enabled, right?
That's right. We wanted it to be easy. We wanted it to be guilt-free. And this is the way that we minimized the disabled probe effect, something Brian talked about in the State of the Union, that the disabled probe effect was much more important in DTrace than the enabled probe effect. Enabled probe effect can be, you know, significant depending on what we're doing here in Rust. But disabled, it's the cost of like this clear instruction, a compare instruction, and a branch. Like it's not 0, but I challenge you to measure it in almost any kind of meaningful code. Certainly when you know, Ben was adding some DTrace probes to look at transactions against our database. Like you're not going to be able to measure those 3 very trivial register-based instructions in the context of a database transaction.
Yeah. Some questions in the chat.
Please.
So one, does the create support architectures other than x86? Obviously, we're only using an x86.
Yes. So
Yeah.
we support x86 and also ARM64 for Mac. So I'm going to run these on my Mac, which is one of their ARM-based Macs. So we support both of those.
Yeah, and the nice thing is like a NOP is a NOP in every assembly language. So clear, you know, whatever. It's a nice instruction, but we have to specify the register. But a lot of it is very similar from architecture to architecture.
And then another question: does the first argument always have to be borrowable as a U32?
No. So you can put any types you want that are supported. So we natively support all the integral types of any bit width, integer types of any bit width, and strings. We also support through JSON serialization, which we'll get into more in a bit, any Rust type that's annotated with this serialized derivation. So basically, if you can serialize the type to JSON, which you can do for almost any type, you can pass it. And then that'll get passed over to DTrace as a string in JSON. But
you really are a big surprise. Like that's coming up.
Sorry.
Stay tuned, everyone.
Yeah.
Just be patient.
We'll get that. You're right. So no, we do the borrow part is because we do a little bit of work to try to borrow things if we can. So the type has to be borrowable, but almost every type can be borrowed. So it's not a big deal. But we do that basically just to avoid copies wherever possible.
Right.
Yeah. So like I mentioned, we're going to do it live here. So I'm going to share something else. I'm going to share a terminal, and I want to show you know, how we actually add these to a real program. So I have here.
It's somewhere back in Chrome.
Oh, I just got in Chrome.
There you go. There's your.
Thank
can go share that guy.
Yep. The question is,
See if we can get the right terminal. There's only 2 to choose from.
I think that's it.
There we go.
But now I have to find it. Oh, it's back behind here. Here we go. Okay. So I'm in this little program that Adam wrote called System Simulator, which is a tool that we just use for kind of simulating a storage system where you have a client that's submitting requests to store data. The back end of that is sort of doing many requests and trying to handle many requests in parallel. The details of the system itself are not that important, other than to know that if you look in the source code, there are a few different parts, but we're going to look actually at this persist, which is representing kind of the actual persistence layer that's sort of doing the work of storing the data. So, so this is unmodified. I just cloned this. This is on our Oxide Computer GitHub repo, so you can clone this yourself.
This is further simulating. You listen to this talk and you think, hey, DTrace probes, I'd love to add them. How would I do it?
Yeah. So I'm going to run this program, as is without any probes. And you'll see that what we're doing here, I should build it first. When Adam wrote this, originally it just has logging statements in it. So we're going to see what those do, and you could kind of see it like doing a bunch of work. The details here are not super relevant, other than there's a client that's like sending requests to do work. Those have some ID. There's a background task which is processing those in parallel with some parallelism. So what we're going to do, like I said, we're going to go into this persistence layer here, and we can see the important part that I want to look at first is this enqueue function. So you can see, hey, we have a debug logging statement, which is starting the persistence. It says, cool, I've gotten this ID for my persistence request. I'm going to go do some stuff, pretend to do some work, and then later we will say we finished that work, right? We'll let the client know that we actually finished doing that persistence. So as I mentioned, the kind of first step here is cargo add USDT, which is very easy. So then if you look at the persistence code, we're going to add here, the first thing is the provider and the probe definition. So we can do USDT provider. Let's call it persist.
Yeah, so with the USDT create, you have to define your probes, your provider, your probes. And so what Ben's doing here is just, we've got this attribute macro. It's going to emit other macros, but this is the definition of each of the probes. Is a probe named enqueue and probe named persist, and each of them take a U64 as the only argument that you're going to pass to this thing.
Worth elaborating on the filth that we're crawling out of in terms of doing this in other systems, because this is much more of a pain in the ass. Actually, if you're in a C-based system, it's actually a
We'll
lot
get
more
to that and talk about
Yeah.
when we talk about how we built this originally. I think the
Yeah.
first stop is going to be like how you would do this in C, which is actually how you used to do this in the USDT crate with like a separate .d file. We'll get there though.
Yeah.
Bill? Like, I don't know. I thought it was pretty neat. Okay. Anyway,
No,
It's
it-
love
it-
also
it's
part of the
very
we'll have a lively Q&A session at the end, apparently.
So, this enqueue function, I'm basically going to, probe the entry effectively and the exit of this enqueue function, which is the work being done by this persistence layer. Where we have this logging statement, conveniently, we're going to say, hey, that's a logging statement. You might wonder, where do I put my probes? This is one of the good examples. Anywhere that you might log something is a potential place that you might want to put a probe, because obviously it's a place of interest in terms of monitoring the progress of the program. And so you might want to probe that, especially if it's something like I'm about to start some expensive operation, or I've just done some, or something failed, some operation failed. Those are really good examples because you may want to sort of know what happened during that. And so tracing the beginning and the end is a very common pattern to sort of conditionally do, other tracing sort of during that processing.
If you've ever looked at a log statement and thought, oh, geez, I recorded this data, but I actually wanted some other data, or I wanted to know what was happening around the log, or I wanted to know what happened right after or right before. That is some of the utility of these statically defined probes in your Rust code.
Right. So I'm going to put a persist : enqueued thing, and I'm going to probe, and I'm going to return the ID there. And then I'm going to do persist : persisted, and again, returning the ID here like that. So if I've done this all correctly, we should just be able to cargo build this, and it'll now build all the USDT stuff. So it'll take a bit longer. There we go.
Nice.
in Q. Oh, right.
What do we call the thing?
I think I called it in Q.
Yes, perfect.
Yeah, in Q.
Nice.
Oops. The cargo build this. Now if I do dtrace, what I'm doing here is I'm gonna just I'll get to this minus cap Z in a sec, but I'm basically just saying I want to trace that ID every time either the persist in queue or the persisted probe fires. So I'm gonna run this.
Remember, persist is the name of the provider that's been created. And we're saying let's turn on everything and then see the ID that we're printing.
So there you go. You can see that it's basically just incrementing this counter, persisting things. Here at this point, it's doing it in serial. If we caught the beginning of it, it would be doing some of them in parallel. But by this point, it's sort of backed up. The queue is full, and so it's sort of processing them one at a time. But you can sort of see how easy it is now to add these probes to basically any Rust program.
I mean, it took us longer to install Chrome.
It took me much longer to install Chrome than it did to do the work.
Yeah.
Okay, so let me go back.
And you want to talk about cap Z. So
Oh yeah.
when and this can become more evident later on, but when you start your DTrace program, you specify like what you want to probe, DTrace, the system, will go out and look for these probes. Now, in the case of these Rust usually and statically defined tracing probes, they don't exist yet. Like they only exist once after the program starts running. So minus cap Z to DTrace says, in fact, why don't you run it without minus cap Z? We should show, but minus cap Z to DTrace says, DTrace, don't worry about it. Oh, we already have them running somewhere. Okay.
Well, I think it worked because it's loading. I'm doing minus Z.
Oh,
minus
okay.
Z, right?
So I'm actually a little surprised that worked. We'll go look at that later. But minus Z says DTrace, like, don't worry about it. If you don't find these probes, like, just keep on trying. And if they appear later, oh, I know why, because we're on Mac. Oh, and we'll talk about that later. Anyway, little reveal here.
There you go.
So minus cap Z can be important. The reason minus that my DTrace by default will kick you out if it doesn't find any probes is if Ben had typed, had fat fingered the name of the provider, or we started to look for a system call that didn't exist or whatever. DTrace thinks we know that's probably a better user experience is going to be to tell the user, hey, there's no such probe. Is that really what you meant? And if what you really meant was this, then yeah, add minus cap Z.
Yeah.
And we'll explain why that worked and why we thought it might not in just a little bit.
Okay, let me stop that presentation and start the other.
Yep.
Okay. So we did it live.
Sure did.
Yeah. So now Adam's going to talk about the path.
Yeah, I wanted to talk a little about the USDT origin story. And this is going way back. So before DTrace, and Brian mentioned this in the State of the Union, there was other dynamic tracing facilities in the Solaris kernel that we were learning from. Dynamic in terms of how they worked, but not in terms of not systemic in scope. And in particular, there was this facility called Lockstat, and Lockstat was like fairly amazing. Lockstat would dynamically modify the code in locking primitives, obviously like a very performance sensitive, delicate piece of code, but dynamically modified the code in a running system in locking primitives to be able to gather statistics about kernel locking. What are locks that we're holding for a long time? What are locks that are heavily contended? It was an extremely useful facility. Now, as part of doing the DTrace work, one of the things that Brian did was to fold that Lockstat dynamic instrumentation methodology into a provider. So then Lockstat just became one of the providers of DTrace, and the Lockstat command became a DTrace consumer. So, and then we were able to use those Lockstat probes in concert with any other DTrace probes to make even kind of more nuanced and complicated investigations of locking. So really cool. And we thought, hey, wouldn't this be nice in userland? We did all this userland tracing stuff with the PID provider. Wouldn't be nifty to be able to look at userland locking primitives. And so I started building this thing that we were calling P-Lockstat or Plockstat.
I guess you're not going to speak ill of the dead because of what you're supposed to tell this.
Oh, I didn't know that he had tried.
You tried to do the sock wrong.
Oh,
It was extremely bad. When you said awful, I thought you were going to talk.
oh no, I didn't know. So the late great Roger Faulkner apparently made a swing at this. I did not know that. I was just sort of sent in as a youngster to like not knowing that there were already corpses there.
Yes.
So,
Like,
but I started like dropping these symbols around libc, and we took a look at it and we're just like, no, this is not it, and we can't integrate this. And so we integrated the bulk of DTrace, and we said, okay, let's pause, let's think about what we want to do from Lockstep. So we came up with a new idea, and the new idea was to do something a little, like quite a bit more generic, rather than just me going in by hand and sprinkling these shibboleths of probes around the libc locking primitives. What we would do is modify the locking primitives to identify the points of interest in the way that we just saw Ben doing for our example. And then we would stash the metadata associated with where the locations of these points of interest were in the binary itself. In previous attempts, it was this unholy knowledge between DTrace and a command and the implementation, but rather saying, let's remember where we put these probes by gluing it into the Elf file, into the command, or into the shared object. And then when programs start, we use the metadata that tells us where these probes are to register probes with DTrace. So when a program starts, I octal this description of these probes down into the kernel. And the way we did this was to make small modifications to make files. Make files being how we used to make C programs back in the day. I don't know if I have to specify that. But we had to make, it's kind of a small change to the build process to generate this object file. Now, in thinking about this, I was reminded that I actually had preserved this document for how we came up with this from the archives. And I was digging through my files last night and unearthed this thing that I was fairly sure that I had. And I want to zoom in on part of it because it actually describes the mechanism like pretty accurately. So on the far left, you can see there's like this pile of files that represents our input C files. And the C files get compiled into object files, and then they get split. And we have our object files get further modified, where we kind of figure out where the probe points were. And then we create this new object file, which I was calling trace.o, and it to kind of keep that metadata. And then in that make file, it all would get glued together at the end. And this is more or less how USDT worked in C, worked in a lot of different systems for a very long time. Now, when I was showing this to like patent lawyers at Sun way back when, now I think there is a patent on this, but it's all been, it's all based on the MPL. It's all like in the public. So there's an explicit patent grant.
There is an explicit patent grant. I've got other things for you. 17 years.
Oh, it's just like in the public domain. Okay.
Like,
Oh, boy.
better.
God, sorry. I mean, Walt Disney really knew how to keep their copyright. So anyway, in the public domain, doesn't matter, whatever, that's fine. When I showed this to the patent lawyers, they did spot a problem. And I'll just give you a moment to see if anyone in chat can identify the problem.
That's already on it.
Okay, yeah. So it turns out the patent lawyers really did not like that I apparently was working on this while in China, because apparently if you build anything you build in China belongs to China, is what they told me. I don't know if this is still the case. And they're like, it is very important that you did not finish thinking about this while in China. You might have started thinking about this in China, and also please put away this document. We don't need to see it again.
Please destroy it, but I did not ask you to destroy it.
That's right. Right. We've never seen it. You've never seen it. Let's move on. Okay. So moving right along from the archive. Okay. So USDT, I think it is fair to say, was kind of an accidental hit. Like we knew we wanted to build this Clockstat thing. We did Clockstat was great. I don't even know I've used Clockstat that much. Maybe you're like looking at me like you've used it a ton. I've used it some. Sure. Clockstat was great. And we knew we'd add probes to things like Postgres, like when are we starting a transaction, when are we completing a transaction. But then it found surprising life with tracing other languages, in particular dynamic languages. So things like JavaScript and Java and Ruby and PHP. PHP.
No. Liza's suggesting that the P in Clockstat stands for Pudong Shanghai.
Yeah. That's the homage to to the Pudong hotel back then. That's lovely. So again, we didn't see this coming for USDT. We didn't see the utility, the breadth of utility, but I think that is arguably the place where we've seen some of the most development and use of DTrace in like the past 10 years.
I would think to like we did have SDK at the kernel, which is also
Did have SDT in the kernel. We used SDT in the kernel a ton for the dynamically defined tracing provider for the kernel to look at, I mean, like disk IO, process lifecycle stuff for sure. But I think that the surprise of USDT was its applicability in like dynamic languages.
Absolutely.
And
Yeah.
in tracing places that we didn't sort of know how we were going to trace, right? Like in Java in particular, when you're in this JIT, like how do you know, like the functions don't exist to instrument? How do we even talk about it? So we found some amazing utility there. And at least it is enabled. We've already demoed is enabled, but I wanted to talk about where that came from. So early on in C with USDT, I guess we sort of convinced ourselves like things are sitting around in registers anyway, so maybe it's not that expensive to just like pass it to the probe. Like it's again moving some registers around. Like we're on Spark, we're not moving that fast anyway, so who's going to notice? But then when it came to dynamic languages, we discovered that some of the most important arguments that we were passing through these probes were very expensive to compute. Like as I recall, in Java, even like discovering kind of the name of the method, the name of the class, these things were not right at hand. It wasn't a couple of pointer chases away, but it took a lot of work to figure out where we were.
Was it Ruby in particular that was like Ruby was devastating.
Yeah,
To
maybe
get this information.
yeah, because I think we did
I
this.
remember
while-
like what was the actual use case was like we had got to do something
I think
else.
we did this while you were at Joyan and I was at Delphix, and we cooked up this stuff.
Is it enabled?
Yeah.
No.
Was it before that?
Yes.
Oh, really?
Yeah, because I know where I was.
Oh, really?
When you and I were talking on the phone
Okay.
and you were describing this, and it was
Okay.
like, yeah, that's a very,
All right,
very,
there you
very
go.
good idea. No, it's that Sun. It is. No, it's going to be prior. It's like 2005, 2006.
Oh, wow. Okay, much earlier than that.
Yeah, I think it's. I think it is the Ruby. I think we done the Ruby provider. Joint had done the Ruby provider though before I worked
Oh,
there.
okay. There we
So
go.
that may be where you're getting the Joint tie-in.
Got it.
Scott Barron at Joint had done the Ruby provider. It was devastatingly slow.
Yeah.
Anyway,
There we go. You're right. So devastating. So with regard to disabled probe effect, and we really wanted to remove that disabled probe effect. So as Ben was describing earlier, in C, we would generate a macro. I almost hesitate to call it a macro just because I'm so in love with Rust macros and they're so beautiful, but like these like search and replace text strings feel like so primitive, but it was a macro that would evaluate to 0 when disabled. And then the DTrace kernel would overwrite the instruction to drop in a 1 rather than a 0. And then we can add this simple guard around whatever was expensive.
So I think our first version of the USDT Rust crate really took basically everything that was just described in terms of how you glue these different parts of the object files together to produce this final binary, all of these macros, and we really just like made the Rust compiler do that for us. But it was very much like a transliteration of the C process. So we at Oxide we use Illumos for our host operating system. And so we were focused on Illumos as the first consumer, and we really modeled it after that process in C. So the idea for the first implementation here was to force people to write the provider definition the way you would in C, which is in this extra file written in the D language, where you describe the provider effectively. That module that we saw 10 minutes ago, you would write a very similar thing in C, or in this D language, excuse me. And then you would have a few extra compilation steps where you would take that, we would process it, we would generate some sort of extra metadata in these object file sections and glue those all together. So this is very natural in a makefile centric world where you already have make is basically just an automation around a bunch of shell commands. There's one way you could think about it, right? And it's not uncommon to add these extra steps, and they all get sort of wrapped up into the final targets anyway. So you don't really see them too much. It's not that big a deal. But in Rust, this is pretty burdensome. The more you add these kind of build steps, if Rust has the notion of a build script, something you can run at before compile time of the main code, but they are a bit unusual still. They're not widely used. And they're, adding more of these steps is definitely like a burden for most Rust developers. And those were definitely, I think, unexpected. The other big thing is that Rust has this idea of there being no life before main runs. And what this really means is that they make very few guarantees. The Rust language makes very few guarantees about what code you can expect to run and to be available before the main program runs. So as an example, if we're writing this probe definition in D, we want to take all of this and generate at the end of the day something called DOF, which is the DTrace object format. These sort of extra metadata sections are written in this kind of mini ELF-like format, and we want to send that down to the kernel through the octal that Adam mentioned. But to do all of that, you have to do a bunch of processing of these of the provider definitions, of the probe definitions, to generate this DOF, and it's a pretty tricky thing to do before main, right? Because you don't really have access to things like collections, like a vector or a B-tree map or anything like that. And you can't really build these complicated string tables that are inside the DOF format. So it's pretty hard to do all of that before main runs in Rust, at least reliably. So we decided to sort of take a step back and instead we store that probe metadata in a different kind of, not in DOF, but in a different kind of stripped down metadata format in these probe records, we call them, store this metadata that you need to construct the DOF. But then we require this explicit registration step, which is a bit of a wart that we'll talk a little bit about later. At the same time, it's kind of nice. Rust is I think, has an emphasis on things being pretty explicit. And I think that's a good thing in general. So it's not, I think, too onerous to have this registration step. And what that does is takes that metadata in this very stripped down format, constructs that DOF, and then does the ioctl that we described. So this is sort of where we started. And again, this is all kind of in the Illumos only world. We were just on x86 at this point, really kind of focused on getting something that would work, getting the metadata described and sort of understand what we need to actually do to register these probes at runtime. And then enter Mac OS.
Yeah. So, yes, this is a typographical joke, and yes, that is a form of dad joke. But Mac OS works different. So one of the ways in which Mac OS works different is, at first we built this mechanism in Illumos. We tried it in Mac OS, and we got very strange results. It just turns out like the implementation is a little different. They use some of the fields differently. Some of the addresses are different. It's different. But one of the ways in which macOS is different in a terrific way, it speaks to some of the strength of Apple. So Apple ported DTrace to macOS 10 in 2006. I should note also, it was like a surprise to us, and it was a surprise to us in the dumbest way possible. The folks at Apple wanted to meet with us. They were evaluating DTrace. They said, evaluating, that sounds great. We'd love it if you ported it.
They wanted us to come to Cupertino.
They wanted us to come to Cupertino. I didn't remember that. But
Yeah, they asked us to come to Cupertino, and we're like, no way. If you want to meet with us, you're going to come to San Francisco. Like, that's going to be the end.
And they did. They came to San Francisco. And like, that was also, I was not tipped off. And they came not with like, so tell us about DTrace. Like, what does it do? But it was more like, in this structure, on this field, on the 5th bit, what is the significance of this? And things that the three of us, Brian, myself, and Mike Shapiro, the third DTrace author, looked at each other. If any of us know, it's going to be one of us. No, three of us. No, two of us. Even though the answer to these questions.
I just did depositions that were less pointed.
So, very, very specific questions. So we walked to that meeting, and the dummies that we were, we thought, wow, they had done their homework. Those were great, thoughtful questions. No, of course, they were 99.8% of the way done with their port, which they then announced like a month later.
So you'll be asking a PLOC, PROC-LOC ordering issue. Is one where we're just like, you're very glad that you have there's only one human being on the answer.
Yeah, exactly. So like the ordering of locks being a question, you're really only asking when you've got a bug. Okay, so so they made this port. It was terrific and somehow surprising, but it was great to see. I think this is not hard to say, but one of Apple's greatest superpowers, among them are user experience and integration. And I think it's also fair to say that coming from Sun, these were not our superpowers. One of the things that we were really impressed by with Apple's DTrace port was the UX and integration. So out of the chute, there were tons of processes, tons of USDT providers available just by default. In fact, if you're on a Mac right now and you do a DTrace -L, you will see thousands and thousands of USDT probes in all of their core services, and they are still there, and they are still used, and they are still firing these probes. Very impressive. I think at Sun, we had a few probes, like from the kernel group itself, like plockstat, but beyond like the kernel group itself, we did not have it. Like Apple's version of Perl shipped with DTrace probes. Sun's version of Perl did not ship with DTrace probes. So really great on the integration. The other thing that Apple did, which was amazing, was build that integration with the compiler and linker. So rather than having this, the Pudong Shanghai mechanism of doing a ex post facto modification of the object files, emitting a new object file, modifying your make file to link it all together, Apple instead just says, why don't we just make the linker able to do this whole thing, which is great. And what it meant is you didn't have to change your build process, you didn't have to change your make file. We were just, you just add the probes, and they're good to go. They're there in the Mako file that the compiler and the linker emits.
So we took this idea and sort of ran with it a little bit when we built USDT to work on Mac OS. So we realized that we could get away on Mac OS with no probe metadata. There's no probe registration. There's still a function for probe registration, but it just succeeds all the time because nothing is required at all. Instead, as Adam said, the compiler and the dynamic linker are sort of working together to just like do all of this stuff for you. So instead of on an x86 like a Lumos machine, instead of emitting like this inline assembly with the clear racks and all this other extra stuff, we take those same macros and we emit totally different code, which I've copied here. So instead, we are emitting the same functions with the same sort of magical symbols that the C toolchain on Mac OS will emit for you. So that's what this like massive DTrace provider with all these $signs in here. The compiler is taking this probe definition and emitting a function that is called this thing, which has this special naming based on the symbols and then also the arguments. And in Rust, we can do this instead. So that's not a valid Rust symbol name. So you can't name a function literally that, or at least you couldn't. I think you can today actually, but you couldn't do that when we first built this. So we use this attribute, this link name attribute. Rust has a lot of code generation mechanisms for modifying how the actual code gets emitted, where things get linked, all that stuff. And so we could say, hey, actually, I'm going to call this function underscore something, but then you're going to call it, when it emits a symbol name for it in the actual binary, you're going to call it this 397 character thing. And I promise that you when I write this, you'll just transliterate it for me in the final binary. And then at the end, the rest of it is sort of automatic. So now I have at the bottom here this assembly that we emit for the actual probe site. So instead of like a NOP and this clear racks or any of that sort of stuff, instead what you see here, so this is on ARM, so the BL is a call, and it's saying, actually, I just want you to call this function, this symbol called something, underscore something, which is that giant DTrace underscore probe, et cetera, function. But otherwise, it works very similarly. We're creating the arguments in the same way. We're calling your closure. We are unpacking them, putting them into the right register. So again, the register names here are platform specific. So it's X1 rather than RDX or whatever it is on the other ones. But all of this kind of happens automatically when you run when you emit these, when you compile your program. We're actually calling out to the C compiler to learn what these functions are supposed to be named. These symbols are supposed to be named.
To the D compiler.
Yeah, sorry. So Apple has a DTrace invocation that will generate a header file basically from these D definitions. If we do that to learn what these symbols are supposed to be named and then insert them in the code that we generate from the macro.
Yeah, and so the result is like we're kind of plugging into that Apple integration toolchain for the Rust USDT implementation on macOS.
And even though the actual kind of guts of this are pretty weird and janky, I think this was a kind of a important moment for us that we realized that the value of that integration in terms of like a developer experience where you don't have to, I mean, even the assembly that you're emitting is much simpler. You don't have to sort of, the register probes thing, if we were only on macOS, there would be no register probes function. It would just do it automatically, right? At the time that the dynamic linker loads the program. I think that there's a lot of stuff that Adam's going to talk about later that I think we can take from this and learn from this and you know, helps us understand what a better future might actually look like. So the last thing I want to talk about in terms of sort of building the process of building the USDT crate is the idea of complex types. So we hinted at this at the beginning, but
well, if just to talk about the origin, like, so we were using the USDT crate, and our colleagues were like, "This is great. Like, I love 16-bit integers, 32-bit
even
integers,
64 if you want."
Strings are pretty nifty.
Our colleagues were very impressed, but they also thought like, hey, what about, like everything else? Like, what about all these types that I use to record stuff?
Yeah.
And like having to unmarshal those into a pile of strings or like U64s or whatever seemed like kind of a pain in the neck.
Yeah.
So we thought like, how do we show off the rest of these, the type richness of Rust and have that come through in our DTrace probes?
Yeah, so as Adam is getting at, I mean, Rust really encourages lots and lots of types. It's very cheap to make new abstractions and to put types together. But then, of course, we have to like unpack them all by hand if you wanted to use the original implementation of the USDT crate, which sucks. So instead, Adam had this really great idea of there's this very popular crate. I mean, it's one of the foundational crates in the Rust ecosystem, which is called SERDI, which is for serialization and deserialization. And it's extremely widely used, and we can serialize basically any type into almost any type into JSON. And I think in like 2011 or so, the JSON action somewhere around there.
I think 2014 or something like that. Yeah.
There's an action in JSON.
JSON action.
This was now a joint for real.
Yeah, that was for real joint.
Yeah.
So there was an action added in DTrace called JSON, which does exactly what it says on the tin, which is it would take a string that was supposed to be JSON, and you could inspect it in various ways. You could pull out keys or values and sort of understand, process the structure of JSON itself. And so this allowed us, I think, well, actually, before I do that, let me just sort of show how this works. So in Rust, you might name a struct like this, and you've got, say, two U32s in that struct. And you could just add this derive serialize on top of it here, and then you can just put that as a probe argument in your provider. You don't need to do anything. You don't need to destructure it yourself or do anything manually. You can just provide it as an argument. And what we will do in the probe macro that gets emitted, we will do this, which is we basically call that closure. We get your argument. In this case, this details type. We take that and then we actually call this toJSON function, which is really a wrapper around a SERDI function or a SERDI JSON function that takes your type and turns it into a JSON string. There's a bit of a wrinkle here, which is that the serialization is fallible. It can fail. And so we have to kind of wrap everything in this kind of result type. So you have at the top of it, you have like an OK or an error key, which tells you basically, yes, the serialization worked and here's what it is, or no, it failed and here's what happened. But other than that, we can now pass this JSON encoded object as a string, so just the char star to D, which has now this action, this JSON action for inspecting it, so you can pull out the OK or the error variance and sort of see what happened there, and then just sort of use this much more natural way of expressing the object that you want to pass from Rust, which has these very complicated types, or can have these very complicated types, into the much simpler types that D has by default.
Yeah, and just to pick up on some of the themes that Brian mentioned in the State of the Union, I think this really emphasizes the utility that goes into the development of some of these DTrace facilities. Like, is this the most elegant thing in the world? Like serializing things as JSON, shoving in with the kernel, copying in a string, and parsing through it? No, it's not the most elegant thing in the world. But it also like was not that hard to do and gave us just a tremendous amount of utility and value. Like, it's unbelievable how useful this mechanism turned out to be, how little work it turned out to be. And like, yeah, is it a little icky? Yeah, it's weird. I don't know. But the like sort of real robust thing would have been just an epic journey that we weren't going to go on. And this got us probably 90% of the value.
I would also say that this is also like, it's kind of like, it's a lot of work to do this, but it's work that's only being done
That's right.
when you have enabled the probe.
That's right. So when we talk about like disabled probe effect, if we weren't guarding this with an is enabled thing, it's like, yeah, I could be. Turned out you just added JSON serialization into my hot path. Like, actually, that does make my transaction look very snappy by comparison. But yeah, we're only doing this when this is enabled. The other just quick point I'd make is that Apple did their DTrace port in whatever it was, 2006. I said, Josh Clulo, our colleague here, had developed the JSON action in 2011. Apple has taken that in their port. Like, I don't know what cadence with which they're picking up stuff, but it's available in the Apple DTrace port. So this is not like an Illumos only special.
Source code to which is presumably made available somewhere. For the
Is
license.
available.
Exactly.
We've looked at it to figure, when we were trying to figure out the initial implementation on Mac OS, we were trying to figure out, they have slightly different struct definitions for their DOF stuff, and we were trying to figure out why.
Apple does seem to abide by the license and makes source available. Is it the most convenient?
Is it the most abiding by the license?
Probably not, but I'm sure their lawyers will tell us it's just fine.
And one of the nice things, the last bullet point I want to mention here, this JSONification is actually what really prompted us to take the provider definitions out of D and put them in Rust directly. And I think that was it sounds like a small thing, but I think it's a big deal to not have this extra file lying around that you have to keep in sync and make sure is, up to date. And, then maybe you don't get the same level of type checking. And I think that was also putting them in Rust, I think added a bunch of, it made it much more natural, made it easier for people to do. They didn't have to like learn a new syntax really, because like these are just function definitions that look very similar otherwise to a Rust programmer. And I think that, is also going to show up in some of the themes that Adam's going to talk about at the very end, about like how we could do this a little bit better.
But we needed to do this because we wanted to specify a type. It wasn't an int, it wasn't a string. So we needed some way of specifying a type. And of course, we wanted that type validated. Like we don't want you to be able to call this probe with whatever. We want to make sure we know that you're giving it the right entity.
Yeah.
All right. So now buckle up. We're going to talk very briefly about the future. Because I think that we have this sort of accidental success with USDT. And it's been great for us here at Oxide, great in Rust. But it has made us think like, what would better look like? Now this title, the Oasis is half empty. So back when we were at Fishworks, back at Sun, a colleague was doing some work to develop DTrace, and he came to us, to me and to Brian and to Mike, and started explaining all the ways in which DTrace was deficient, things he couldn't do, this and that. And we all kind of sat back, and we had thought DTrace was pretty great actually, and it let us do things. And I think my response at the time was, John, we like to think of our Oasis as half full. So in this case, this Oasis, this kind of water hole in the desert, it's great. Like, and to quibble, feels dismissive. But I think it has made us realize like the ways in which this can grow. So we've used these USDT probes a ton. We've got a ton of value. But like this macro that has mod functions, like I know it's sort of more familiar and it's like emitting more macros, feels like a little weird. Also, we have these, we mentioned this, but we take these records that describe the probes, we put them in an ELF section, which is really just something Ben and I made up. And then we have to massage those to turn this into the DOF that we send into the kernel. C and on Mac OS with their linker involvement, we don't need to do it that way. But on Illumos and other platforms where you don't have that linker integration, you do. And the structure of these is kind of weird. consumers also have to remember to call this USDT register probes thing. And that's sort of fine if you're sticking them into a binary. It gets weird if you have it in a crate. So for example, we have our web server framework Dropshot that Dave Pacheco and I worked on. It has DTrace probes. And we have to find a way to call register probes, and we do it when you're starting a server. It's fine, but it's also a little weird. And you have to remember to kind of sneak in this call somewhere. And even with the bulk of work under is enabled, it does feel like there's an opportunity to have even less disabled probe effect. And I just observed that like every tracer and compiler in different languages are all kind of doing their own thing. This did make me think like, okay, what if we had some standard for statically defined, dynamically enabled probe points for all the tracers? What if all of the tracers in the world, us and eBPF and anyone doing anything tracing got together? And this is just like not going to happen. I don't know why. It just seems so ridiculous. Like we're never going to decide like, oh, let's find common ground. Let's make a standard. Like standards bodies like sometimes work, but just it does not feel a place where standardization is going to happen. So okay. Second big idea. I think Rust should natively expose DTrace userland probes. And this was an idea that was not originally made, but Graydon Hoare, original author of Rust, wrote this issue in the Rust RFCs back in 2013. I think Rust should expose DTrace userland probes. Hey, me too. We all do. That'd be great. And so it was very encouraging when I stumbled over this to think like, okay, they were thinking about DTrace probes natively in Rust very early. So that's cool. So why would we do that, and what would that look like? So if we had first-class probe definitions, we could avoid some of this sort of stranger macros generating macros stuff. The type checking that we do is okay, but relies on other kinds of type generation. We could avoid the need for explicit registration, which again is too easy to forget. And then I think another neat opportunity is to lay code. We could potentially lay code out in a more kind of a more optimized way. We could take all of this disabled by default code, all of our serialization of types, stuff that somewhere else out of the hot path, not just like under outside of a branch, but kind of out of the flow of control completely, and do a more intelligent layout there. So the thing I can imagine happening here is that Rust leadership on USDT and DTrace integration could lead to more followers. So one of the neat things that we saw is that other tracing frameworks followed this USDT mechanism that we built. And in some cases, like with system tap, even the command to generate header files, to modify object files was named DTrace. Like that these other tracers shipped with a binary whose name was DTrace. And why did they do that? Well, the project had used DTrace to add probes to the program, and it was easier to follow and have those make files be backward compatible. So kind of weird, but I think that Rust, first-class Rust compiler collaboration with DTrace could really lead to other tracers and other compilers in other languages following suit and kind of having that ersatz, the de facto standardization, especially as we see the benefit of even closer integration, more natural, more fluid, available by default, and with kind of like a simpler mechanism for registration. So that is what we came with. I hope that folks now take the USDT crate and add probes to what they're doing, whether it's on Mac OS or on Lumos or other systems that support DTrace and support USDT. And I'm hopeful for the future of what USDT and Rust might look like. Any questions?
I think we got all of them answered as we were going through. That was really great.
Awesome.
Thank you.
Do we want to take a 5-minute break?
Yeah, I was thinking 5-minute break. Does that make sense? We can.
Sounds good. We'll take 5 minutes. We'll start up at 11:05 with our next speaker. Thanks, everyone.
For our next talk, we've got Kyle Simpson is here from coming to us from Glasgow. Kyle, take it away.
Sure thing. Thank you very much. Let me figure out screen sharing once again. Okay. I believe you should now see slide show up. Is that correct?
Yep, we can see it. Looks great.
Okay. So just a heads up, my throat's been getting a little bit worse over the day. So if I'm overly crackly, then I'll try my best to push on through. My name's Kyle. I work with Oxide primarily on maintaining our packet transformation engine, OPTE. And what I'm going to talk about today is just a fairly simple utility we put together to make exposing nested enumerations and other error types up to DTrace scripts a lot more accessible and a lot more performant for us. So to give some context, OPTE, the Oxide Packet Transformation Engine, is our packet processing stack for virtual machines. Fundamentally, any packets which leave an instance to talk to another instance, or to talk to the outside world, or even for one of our internal services to talk to the outside world, these packets have to be encapsulated by OPTE or decapsulated if they're received. And to do that, we implement it as a kernel module within Illumos. DTrace itself is a fantastic tool here, and it gives us an incredible amount of value, because otherwise we would have a lot of difficulty in being able to actually instrument and inspect all of the steps which OPTE is taking. So to do this, we make use of a lot of statically defined tracing, or SDT probes, and we use these just for several reasons, down to Rust in particular, but also to tie them to several events. So Rust's name mangling, as you've seen come up in several of the other talks so far, and also unpredictable inlining can make it hard to know when specific functions that we're looking for are happening. So we use SDTs a lot to make sure that we always get we always have probes firing when we expect them to, and for the events that we really care about. In particular, we use this to show and to demonstrate the final decisions made by a port as to what should be done with a packet, to show the incremental effects of like pair layer processing in packets, what decisions are being taken every time we go through, the router, NAT, the gateway, the firewall, etc. But we also use them to show parse failures and serialization failures, which are absolutely crucial for debugging certain classes of issue which come up when developing this sort of thing. So it's no understatement to say that DTrace is absolutely key for debugging and developing this piece of software. When it comes to the sorts of information we want to attach to these SDTs, though, like here's an example of a result type for the final, basically the final decision that is made for every single packet. And if you've done a lot of Rust programming, this will look quite familiar, this structure, this idea of having nested enums, which allow us to trace exactly, or effectively trace a series of decisions made about something, along with like additional context along the way, and it gives us a very strongly composable way of expressing errors and results. When it comes to parsing errors, this gets considerably deeper. We have deeply nested enums here. We have leaf nodes containing additional data pertaining to the variants of interest that we care about. And while this makes it easy to deal with these values in code, and it makes it easy for us as humans to look at them when they're printed out in debug format. However, around February of this year, one of my colleagues, Matt Keecher, was doing a bunch of additional flame graph work on one of the sleds, and noticed that in amongst the traces he was taking, here is XERX, which is basically the method which is called whenever a packet is received on the network. To give some context, the packets we're looking at here are ones that we don't care about and that we want to drop because they're not encapsulated. The open question that Matt raised was, why are we spending so much time here in this bad packet parse probe function? And, there are two instances of this badness going on here, one of which is this alloc format. So that's the debug representation of an error type being called. As it turned out, this one was just a call to basically, push the messages onto var ADM messages where the format call had fallen outside of the macro. No biggie, easy enough to fix that. However, we had a more significant problem here, which is in the STT probe that we had set up, bad packet parse. So to make this usable from within the STT context, one of the things that we had to do was effectively to print format these values out. And as you can probably expect, when you're doing this on a per packet basis for the packets you don't care about, that's actually extraordinarily expensive. And you can see here that it's, we're spending more time printing out these values for probes that we're not necessarily caring about or listening to in total than we are, say, actually parsing the packet and making a decision on the fact that we should drop the thing. Not even the fast path is immune from this. So the first type I showed you, which wasn't too deeply nested, we're still paying some of that tax here because it's been inlined out here. But we do have another call to the basically a helper function wrapping one of our STTs, which requires, again, that we express the decision made for this packet in a format which is, readily amenable for use in an STT. Or a DTrace script, I should say. So fundamentally what's happening is that, calling STTs themselves is basically free. As you've seen, they're replaced by NOP instructions, or they're set as NOP instructions when you load the kernel module in. And when we register those probes, those are replaced with jumps to, yeah, exactly. Brian, I'll come on to that shortly. Unfortunately, getting data into the right shape for these SCTs is not a free operation, and we do not want to have to think about paying this price for every single packet that we admit. Part of the problem, and it's a good problem to have, is that idiomatic Rust errors really encourage us to store and think about error chains in this way. Not just for handling them in the program sense, like having these nice composable configurable errors, but as operators, these give us a chain all the way down to what went wrong in the first instance, as well as potentially every layer of the stack that they happened in. These root causes are useful to have, and they're not necessarily recursive friendly, particularly if you have an error type which comes from a third-party library. When you cross over that boundary, well, you can't even decode that manually in your D script in a consistent way without invoking nasal demons. It's not a nice position to be in. And even if we did control every aspect, manually decoding these things is going to be very tricky, very brittle, and very error prone. So just going back to thinking it through. When we take an example of one of these decisions that we've made, a process result drop in this case, this has all the information we need to understand why individual packets are being dropped. So it's unwieldy, but when it comes down to how we want to handle this, so as we've just discussed, manually decoding all this information and DTrace is out of the question because it's extraordinarily brittle, and when we cross into another library's error type, we have no control there. We could flatten out everything we have within our own program into a sort of God error type. The problem then is that you lose a lot of this nice composability, and you spend a lot of time writing automated conversion, like from and into methods and so on. And because we're in the kernel, we don't have as enabled. So we can look at this from another perspective. If we draw everything out, well, we're computer scientists, right? This looks an awful lot like a tree because it is. More importantly, this is a tree of strings and leaf nodes who have additional data. And at least for the error types that we've constructed here, we have bounded depth. And this gives us something that we can maybe use to try and get all this information up to a consumer while doing the minimum amount of work possible. So derror itself is a very simple trait. Basically, we just ask that any form of result or error can provide a label for itself it can tell us whether or not it has a child. And if it is a leaf node, then it can fill out some amount of leaf data attached to this label block. And when we're filling a label block, all we really do is recursively say, okay, I have the current error, give me the discriminant. Does it have a child? If so, push that label on, rinse and repeat, push that label on, push that label on. And when we hit a leaf node, we fill out the data. So the way we handle this is we have a compile time fixed storage that's const L. And at runtime, this more flag is set if we ever, encounter a chain which is deeper than L. And just to make things really simple for ourselves, we do still have the trapdoor of if we have our own string and we're willing to play one or two unsafe games to make sure that that string lasts longer than the label block itself and does not outlive the SDT context, then we can pass that information up and just fill that in as one of the labels, so long as we correctly make it a C string, of course. So given that we have a lot of error variants and a lot of nested types, one of the ways that we handle this is we've put together a simple enough proc macro, derived derror. Fundamentally, all this really does is it goes down every single variant we have and converts, a C string representation for the variant's name and provides a child walker for any of the tuple variants we have automatically. If we have something that's not actually containing another error that we want to parse or handle, we have a wee leaf annotation here. And in practice, one of the things you'll notice from the first slide where we looked at the error types is that bad error was originally a string. Having this sort of enabled and empowered us to actually automatically derive all of this and get that additional information without doing the string format. So unfortunately, handling leaf data within the proc macro could be done, but we took the decision just for expediency to explicitly make this a user choice, really. In practice, it works, but the DTrace needed to handle this sort of variable length thing is slightly awkward, and I'm probably doing it wrong to some extent, and I've been doing it wrong since March or February. But the useful thing is that it does not fundamentally change on either the call sites that we're interested in, and it does not change on, it does not change the call sites we're interested in, and it does not change with respect to the type of enumeration that we're actually working with. So this is a pattern that's more widely reusable for no matter no matter which error type we want to introduce down the line. If we want to, create something new that we hadn't cared about at the time, and it looks slightly different from what Rust programmers will be used to with the debug format, but the output itself is readable and it does capture the full chain of errors all the way down to the root. So here you can see that this one does include the old string version before that had been migrated over. But you can see that it just sort of proves out that, we can have leaf nodes, we can insert data. If we have a custom string, we can pop that on too. No biggie. Easy ways to solve problems that we want to kick down the road. So I guess practically, finally, did this solve the performance problems we were having at the time with this? And the answer is, quite a convincing yes. So this is just for the unexpected packets that we were dealing with, the ones we didn't really care about. We had, a mean 1.23 microseconds down to, around half that to process it here, because we managed to get rid of this block here trivially and this block through all of this work. You can see here that the amount of time we actually spend, selecting this discriminant drastically smaller than either of these two blocks. And recently we did end up rewriting the parser stack within OPTE. So one of the things I was initially worried about when we did this work was that, if we were to hit an external library with more difficult boundaries or like hidden types private variants or so on, that we wouldn't necessarily be able to provide the functionality we need. As it turns out, converting the base parse error types from that library to match what we have here simply required us just to, fill out all of the C string variants here, and then the amount of implementation for the trace itself is absolutely minimal. And you can see the output here is sort of as you'd expect. It tells us, we have this class of error. Here's the layer in which it was observed, and here's the actual error class that we're dealing with. So it's not a perfect solution. It was effectively built to solve this one performance issue we were having at the time. So if we were, to spend more time in this, it'd be an issue of thinking about how to better handle variable length data blocks or generic data. One of the things I was interested in upon revisiting this was the idea that we could maybe, encode the maximum depth required, or sorry, the minimum depth required to capture the entirety of an error type within the de-error trait using const generics, for instance. Like that would give us the compile time assurance that a given label block is large enough. And if you care to look at the implementation, there's a lot of Dyn references being used, which I would prefer to remove since it does have a cost associated with it, but this is, orders of magnitude smaller. The main lesson of this talk is make sure your SDTs are REPRC friendly, of course, and make sure that your inputs are cheap. See also, there was a related OPTE issue on converting something that looked cheap into a different type that was friendly for an SDT, but it turns out if you do that enough times, then that gets expensive too. So make sure to feed your SDTs well, and your kernel modules will probably behave as you expect. Thank you very much.
Awesome. Yeah. Oops. Sorry, Kyle. That was great. Really terrific work, and very creative in terms of taking all the power we get in terms of the compile time power at Rust and turning that into something that is known at compile time that we can actually then go and look at that dynamically. Really, really great stuff.
Yeah, Kyle, I had not seen that before, but the intersection of this Rust macro and the power of that kind of to produce this for DTrace is just delightful. Just excellent work. Really neat to see.
It was so great that it was able to distract Adam from punching me in the shoulder for not having his enabled probes in the kernel, which I was definitely beginning to fear for my own safety there for a minute. So we still need his enabled probes in the kernel. We should do that. We should do that. Well, if only someone had suggested that in 2004.
Yeah, good. An RFE like 20 years in the making.
That's right. All right. Great stuff, Kyle. I think Alan, you are next.
Yeah, so why don't we just like switch right over?
We'll switch right over. Do you want to get us into a new chat room here?
Yeah, we'll get in a new chat and we'll get you in the chat and we'll just tap dance while we talk.
All right. Yep. So Alan, why don't you sit in the hot seat?
Alan, what's the name? What session? What should I call your session?
Monitoring.
Monitoring.
I'm asking to join.
Oh yeah, Kevin needs to add you in there.
Yeah. Okay, I think we did. All right. Yeah. I mean, I can be on camera with.
He was not talking to you. He was not talking.
Oh, okay.
And there was an implied no.
All right. So I'm going to talk today about building a monitoring tool and the sort of steps that I went through to do that. And hopefully these are generic enough that you can reuse them for your programs as well. So this is sort of, I was inspired by VMstat and IOstat, and I work at Oxide here, and among the many things I do, I work on the storage layer, and I would really wanted to know sort of what was going on with the storage software. And specifically, I sort of had this like questions like, what's the overall health of what's going on? What's the current activity in the storage layer? Were there any problems in the past that maybe missed? I want to be able to observe a lot of processes at the same time and potentially different things within a single process. So these are sort of my high level goals that I had. So a little bit of background to help you understand some of this. The Crucible is a storage layer. It consists of an upstairs and 3 downstairs. It's a crate or library consumed by our hypervisor, Propolis. And we can have multiple hypervisors running in the same system and multiple instances of Crucible inside a single hypervisor. So that sort of sets the sort of stage of what I want. I'm now gonna switch over to the terminal and show you live. So in order to make this probe, to make this monitoring tool work, we put a bunch of DTrace probes using the USDT stuff talked about earlier into Crucible. So if this is a library file for Crucible, and we have a whole pile of probes here. I have the benefit of sort of knowing a little bit about DTrace before we started writing the code, and so I put probes all over the place for everything. I like to write a lot of bugs, and in order to make them not so hard to find for other people, I put a lot of probes there behind to help, sort of leave some breadcrumbs there. And basically, I put probes all over the place. And the specific one I'm going to talk about here is this up status probe that we put in using the very meaningful name of arg. I called it arg because the example in USDT uses arg, and I just never bothered to change it. So if I look at this arg here, the struct, what I'm doing here is basically I've collected a whole bunch of state that I may want to.
We're not getting output.
Oh, you're not?
Yeah.
Interesting. It's not updating the. It's one of those weird mask things.
Process some acting. I don't try unsharing and resharing. I don't know.
Yeah,
Sometimes Bednacker curses systems.
I can curse as well.
You can either have working audio or you can have.
You do the terminal.
Oh, there we go.
There we go.
And is it moving now? Like if you move your cursor? Yeah. Okay. Great. I fixed it.
Good job.
Excellent. I didn't want to read this out loud. Pub struct arg open. Okay. So basically, what I have here is a structure that has a bunch of information in it that can tell me some information about what's happening in the storage layer, and then we have a probe that inside Crucible there's this main control loop that goes around, and every so often you'll say, okay, go fill out the structure. And so this gives me sort of the basis on which I have the information in my program. Now the trick is, how do I get this information out of the running program into something I can use? And let's switch over to, let's see what else did I want to talk about before I do that. Yeah, so actually what I want to do first is show you the result, and then I'm going to walk you through how we created it. So if I switch to the other window here, and I say, it's not updating that. If I run this gives me a nice little summary, and I'll explain in a second what all the things are, but this gives me a nice little summary of what's going on my system. I have a column that's the process ID. I have a column that's the session ID. And then I talked before about the 3 downstairs that are part of Crucible. This is giving me a status on each one. I have a counter for the number of not quite IOs coming through, but number of jobs that we've created. I have a delta for how many since the last time we printed a line. And then these are a bunch of additional statistics that are sort of specific that I care about. But it's basically giving me a quick summary I can look at, fits in a small column width. And I can look at this quickly and go, oh, yeah, looks, everything's good, or I see some problems right away. So you see the structure on the right side here. Let's start with a simple, I'm going to actually exit this. A really simple probe where I'm just getting that up status and I'm printing it out. And if we come over here and I run that, we can see here's the probe name, and then here is that giant blob of data that is basically the structure that I had in my program. And we can make this a little better. I can clean this up a little bit. So what I'm going to show you here is the step-by-step of my D script as it becomes the final thing you saw on the left there. So now I'm telling it to be quiet, and I'm going to use the JSON ability to read in that giant blob and just give me the OK field. If we look at the output over here, you can see there was an OK that was then the entire structure. So if I run just 2, takes a second, probe fires, we get a big blob. Now, some of you may notice this is just a giant JSON blob. And if we wanted to, and your system has it, you can do something like pipe that to JQ. If you wanted to pipe that to awk, and those of you who want to join the awk conference, you can now go off and this is the great awk problem too. So you could do all this in awk, you could do this in JQ, you could write a program that consumes this JSON blob and does things with it. So there's lots of options you have at this point. I'm going to continue down the pure DTrace path and show you how I did it with DTrace, but really the door is open for all sorts of stuff. So I think that was all for 2. So, okay, so now let's go to the next sort of level in this thing. I want to say, instead of printing everything, just give me this one field in my giant blob. So if I run that one, so we got 2 things going on here. The first one is, if you notice, I no longer am exiting at the end of a probe hit. I'm just letting it run. And I'm printing just the next job ID. So what's happened is there's multiple processes running on the system, and they've all hit this probe. And so I'm getting the output from all my different processes as they hit it. So let's continue the evolution here. If I look at the 4th program, now I'm going to print the process ID, which we have as PID available in DTrace, and then the job ID. So if I run that, starting to look a little more sane maybe. So now you can see the process IDs are repeating. We're getting our job IDs. But you notice there are 2 14776s here with different numbers. So that's the same process, but multiple instances inside that process of this probe fire. So I want to further give us a little more information about which one of those instances I'm looking at here. So if we look at number 5, now I'm doing another little trick. Let's run the output, and then we'll talk about it. So I'm doing a couple things here. First, I'm pulling out this session ID field into this full session. And I'm giving this a self because I don't want multiple probe firings to clobber this variable. And if I have a lot of processes and a lot of sessions, they'll stomp on each other if I'm trying to do something inside the probe like this. So this self tells it only for view. So I take my session ID and then I strip off the first 8 characters of it. And then I print that self session ID as a string too. So now I've got my process ID, my session ID, and the specific variable, the next job ID. So obviously, you look at these numbers, they go by quickly. It's sort of hard to tell. Are things changing? What's happening? Maybe the next thing to do is give ourselves a little delta on what has changed. Switching over to my next DTrace 6. So now we're doing a bunch more stuff. I'll run this on this side and then we'll talk about it. So now we can see for each one of my processes, my session, we get the current counter and we get the delta since the last time this probe ran. And there's a couple things I had to do in my D script to get this to work. The first is I have this associative array that I'm now using to store my, part of getting a delta is knowing what the previous value was. So I have this associative array I'm using, and it's indexed on the session ID, because that's the most unique thing I have. But I don't know my session IDs when I first start out. So in D, you can say, I just want to init one of these, and then the rest will work when I actually try to use them. So this sort of is a way to like initialize everything to 0. Then I have, so another trick that we're doing in this, also in this script, is I'm doing my same things before. I'm getting my job ID, but I'm using this function to convert it into an integer that I could then do math with. Before it was just the string that I was printing. Now I'm printing this as an integer, and then I can do math on it. And then we have this sort of logic to not print a big number the first time through. All right, so that's number 6.
One question.
Sure.
So you've used a thread local variable there with self points to. Could you use a clause local variable this points to? Do you need that outside the clause?
Outside the, like, between,
Like, are you
it only matters for this printing.
right? Yeah. So interesting. Yeah. And so you'd use a clause local variable if you wanted to.
Okay, is that this?
That's what this points to.
Okay.
Yeah, it's slightly less enabled probe effect.
Actually, I had this before and I changed it to self this morning, but whatever. What the question was I'm using self here, and I could also use this as a way to even further restrict the scope of this variable. Because for this particular, I only care about it to print the message, and once this probe ends, then it's fine.
So, right.
All right, so now let's add some more columns to the end of our output. We'll run that over here, and then we'll talk about it. So if I go to, I think I'm just going to do this now. Now we have the same start, and I'm doing a couple more things in this case too. I'm now printing connections, ELR and ELC. These are sort of things specific to Crucible. But one thing I'm doing is I'm reading 3 of them, converting them into integers, and then adding them all together. So I get like a little summary. So instead of having to print 3 different columns, I just print 1, and I can look at these columns and say, well, it should be 3. And if it's not 3, then something's going on. And this is, the other columns tell me, well, this is what went on. But we'll get to that in a sec. So I think that's all for self. Yes. So we've added those columns. So another thing that's going on is I have these these three downstairs that are part of my upstairs, downstairs, my Crucible, my storage layer, they have a state in them. And I want to see what that state is, because that state tells me information about what's going on in the system. So if we skip this guy, let's take a look at number 8 here. So what I'm going to do now is in that giant JSON blob, I have the state. That was all playing the same. Look at that, look at bug. I actually want to print the states of each one of these downstairs and put that in my output. So if I run number 8, it's good. I now see the state, but I'm really starting to stretch my column width. That state value there, active is actually one of the smaller ones. There's some that are bigger, and it's going to mess up all my columns. Things won't line up. I hate that. So I have another trick that I stole from Josh that we can use. Let's see. Let's go to number 9 and see what sort of shenanigans I'm into here. So we'll go down here to where the printing is. I'm now using D0, D1, D2. And if I go up in order to get that, here's the magic. So I'm taking my state, copying it out, and I'm using this inline as sort of like a lookup table. And I say, if I want index that matches active, give me back active. And if I want new, then print new. If it's live repair ready, print LRR. So this little bit of shenanigans allows me to print and keep my columns all pretty, all aligned. Now we see the active is replaced with act. So this is just another trick to help you display your information in a more concise way. And then all that's really left here, there's a couple more trips. But basically at this point, the only thing left to do is give myself a little header, which I'll do now in the final. And if you remember, this was the original script that I ran to begin with. And if I run it over here, up, Control E. So now we get another trick. I have this variable that all of the probes we will look at. And then I go down to the bottom and I say, if the show variable is greater than 20, then print a header. And then in my probe, when my probe fires, every time it fires, I add one of its variable. So this is just a little sort of trick to get this nice column to come out, or the nice header to come out every 20 lines or so. So then you get your header, you get your information. You've sort of made it concise. You can get all the columns to line up. And I think that was all I really wanted to show. Yeah.
That is awesome. Someone in the chat is asking if you can emit ANSI color codes.
Answer is yes.
Well, I was just going to say, it's not totally clear to me that this Paul Smith character isn't actually an alt from Adam.
New account created today.
Exactly. Just a little bit suspicious.
What a handsome question.
Tough but fair, says Adam. Adam used ANSI.
Yeah, like in the Java 1 keynote 1,000 years ago, we used to show the difference between userland and Java, system calls and the kernel. And it was how we made like DTrace sufficiently visually appealing for a keynote, let's say.
So there was one other little thing I wanted to, that I just actually figured out this morning. Does this version have it? Yeah. So there's one more little trick here too that I also wanted to show that just got added at the end here. So right now, there's this thing called target which is if I'm on the over here and running my dtrace command, I can say, run this for process ID. What was the one that had multiple? 147. Let's run here. 14776. So if I give it this -PR, what that tells this line here is that only if target is there, not 0, only show things that match this PID. So my same script I can have run for everybody, or if I give it a -P option, it'll only run for that one process. So now I can well, I see there's a problem with this one system. Let's focus in on that and see what's going
Hold on, how do you do that?
on. So this, I say if target is 0 or
Oh, okay.
target is PID. And if I don't give target anything, then it defaults to 0. So then it does everybody. But if target is
Got it.
on 0,
Always enable it. You always enable everybody. Yeah. I got it. Yeah.
all right.
That's awesome.
Yeah, very cool stuff, Alan. Thank you.
So this is all, I didn't have to talk all the details because in your presentation, Adam, I'm using all the same stuff that Ben showed, that you showed. It makes it really easy to add probes. And I think knowing how easy it is to add the probes, I just throw them everywhere. And it kind of,
And it should be said, so if you want to hear more from Alan on Crucible, you join us on Oxide and Friends. We had a great episode on Crucible. And we use DTrace for Crucible all the time because we've been just very and also one of the things that's been great about the USDT support and with all the rich Crucible support is when debugging a problem, it's so easy to add probes just as part of a debugging something.
yeah.
You add a probe, recompile, throw it on there, and it's like in a way that I've not actually with USDT, I've not been able to do that prior to the bus work.
Yeah.
But great.
All right.
Hey, we are going to switch. Very cool, Ellen. And Apo, you should be in the. Oh, there we go.
Stop out.
Apo, and he asked me to try my best on his last name, and I'm going to try Alasutari. So Apo, okay, pretty good. All right, we're gonna and
Not bad.
all right, passable. And you were going to talk about USDTs the wrong way, and we're going to hand it over to you. Thank you, Apo.
Now only to figure out how do I share it. There is the sharing. Good. And that is probably the correct window. Okay. So I hope you can see my screen.
Yep, all good.
Yes, excellent. So we shall get going. In the last decade of the Sun Empire, the Fading Empire's knights created a new overpowering probing technique, the Vestit. And this would not be rivaled for more than a decade after the Empire's fall. The archaeological record is very unclear on where this magic came from and whether it was actually magic in its entirety. The Magitech knights were then capable of great feats with this technology or magic. However, they were unable to stop the empire from falling to ruin. We see in the archaeological record the Tappian Schism and then post-Empyrean bee schism, known for their idolatry of bees, of course, and also the luminous Empyrean remnants, all carrying clearly Magitech influences. Today, I am very happy to show you new findings in the archaeological record based on our research, showing that indeed Magitech that we believe to be magic is actually technological in origin and can be learned in this fading age. So USDT is the wrong way. We're going to look at how a fading age scholar such as I, in the short span of a month, learned from zero to mediocrity the secret arts of USDTs. And especially since we already heard very in depth on what these actually are in DTrace, I'll talk more on the Linux side, because that's where, well, that's where we end up in. So let's start by tracing my outline. I am a TypeScript developer, so I am Aapo Alasuutari. That's how you pronounce the name. I know it's really hard, but that's the fun part. I'm a TypeScript developer by day. I work in automation. My day job is in an automation user interface. By night, I become a Rust developer writing a JavaScript engine of my own. I'm also a fairly avid open source contributor / albatross. So I pop up here and there. And as said, I'm writing my own JavaScript engine, or we have a group writing the Nova JavaScript engine in Rust. And if you know anything about JavaScript, it's that it's dreadful from an optimization and performance characteristic standpoint. So bad that the only real way to understand what JavaScript is doing is to profile it. So I must provide a profiler in Nova. All of my users, potential users, if there ever are any, will be entirely lost without a proper profiler. So, okay, I need USDTs. I want to have USDTs in the engine for my users, but also, of course, for myself. That being said, a month ago, I had no idea how USDTs actually work. And even worse, I'm a loyal Arch Linux user. DTrace for Linux seems to be dead. And I tried compiling Oracle's DTrace, but that seemed to be impossible in Arch Linux, at least the newest version. Trying to Google USDTs just gave me USDT headers for C and C++, but like, what about Rust? So I figured, okay, I got to learn this. I have to learn this the hard way. There's no other way. And turns out this was the wrong way. So we'll retrace my steps up this long stairway of mediocrity in the Finnish winter. You can kind of think of these as like a training montage. You should have the eye of the tiger now playing in your back, in the back of your mind. All right. So USDTs in Rust. We already heard about the USDT crate. Unfortunately, it's Ilmos and OS X only. It does work great on Linux as well. It just does nothing, which works great. There's another crate called Sond, which seemed quite interesting, seemed like it would work, but it relies on CFFI. So it compiles or it just relies on the C++ headers, compiles those on the C side, and then calls FFI, CFFI on those from Rust, which kind of sounds like it's going to be very inefficient. Maybe with LTO this will work, but you call C, C calls probe, maybe not. I also couldn't get it to work anyway. After writing this talk, I actually found a third crate. There's a probe crate. Also, it's Linux only, which is a bit unfortunate. It does exactly what USDT crate does, works with a macro and so on. But obviously, I didn't know about this a month ago.
I apologize for interrupting. Are you sharing slides, or are you sharing a page of notes?
Oh, damn. I should be sharing the slides, but
Yeah, sorry to interrupt.
Yeah. No. That's
Not interrupting earlier.
We were enthralled by your
Let's-
telling and then system tap.
Yeah. Let's see if this would work now. Let's try again. Now you're at least seeing this thing. And now if I go to presenter view, it's still working good.
Very good. Yes, sir.
Yeah. And we left all somewhere here. Okay. Yeah. So the probe crate also exists, but it also was a bit rough on the implementation level. So after looking at the options, I figured, okay, I want USDTs to work on Linux. I'll just adapt the USDT crate for Linux. Like how hard can that be? It can't be too hard, right? I still don't know what I'm doing. Like I know what I want to do, but I don't know how. I don't even know what USDTs actually are. And at this point, I start looking around on the internet, like at a concrete level, what is a USDT? Just please tell me, what are they? Obviously, we were told about an hour ago, but yeah. So I'm going to mostly skip this part because we already heard this, but in the DTrace USDTs, I couldn't find any technical documentation in the archaeological record, i.e. Google. I really dug deep, and it's really weird that I actually didn't find any of the real documentations. Like the Open Solaris link today, that was the first I ever heard about that. I was like in the old Hacker News comments where B. Cantrill and B. Greg are studiously avoiding each other's eyes. And I was in Wayback Machine reading old Sun blogs and comments where people are fighting over DTrace licensing and whether or not system tap is influenced by DTrace or not. Weird places to go to, and especially weird to find no information on like how is this actually done with all that looking. But luckily we have Oxide and Friends. We have now DTrace.conf for future me, and we have the USDT crate code. So that actually kind of gets me further along. Okay, USDTs, this coming from the Oxide and Friends episode, USDTs are embedded in the compiled executable. Still doesn't tell me what they are. DTrace interacts with them, and producer-consumer split is important. Not quite clear why. And then there's this particular. Let's see if I can bring up my yeah. There's this particular which you can't see. Okay, there's a great issue which I will link later on the USDT crates GitHub repo, which explains in excruciating detail very well how USDTs actually work. It's just you don't find it on Google. Dave Pacheco has a great blog which explains this stuff in quite good detail as well. You just can't find it. Okay, but we've heard already how DTrace USDTs actually work. What about on Linux? What about with system tap USDTs, or how they call them SDTs? They lost that U there for some reason. These are used by system tap, Linux perf, eBPF nowadays. And all of them talk about these as DTrace probes or SDTs. And some people will, just to underline the joke, Tapian schism, B schism, these are system tap and eBPF. I just wanted to use the word schism. So that's kind of where this whole thing started. So they actually very often say that they support DTrace probes. Just, is that the same as like DTrace probes, or is it something different? I couldn't find a technical documentation on Google. Again, same thing happens as with DTrace probes themselves, except there is actually fairly good documentation in the System Tap wiki, but you can't find it on Google. You need to know ELF to understand the explanation. And even if you find the wiki, you can't, like, looking for SDT, searching for SDT in the wiki will give you 0 results. The search is somehow broken. Also, I don't know what ELF, so I didn't understand the explanation when it was staring me in the face. So nobody is really explaining how USDTs actually work, except Dave Pacheco. But yeah, so it's time to go reverse engineering into the archaeological evidence left by the Sun Empire in their fall to ruin. And now with this, we're actually starting to get up those stairs. We're really closing in on the truth. So DTrace probes, we already heard, they're made up of the clear RAX instruction. This is the is-enabled probe, and then a NOP instruction, which is the main probe that can take arguments. Well, I'm getting a question. Yep. Okay. So where was I? I'm sorry. So there's also an ELF section for each probe. This obviously tells DTrace where the instruction, the NOP instruction and the clear-RAX instruction are located. So there's essentially, there's an ELF section for the is-enabled probe and an ELF section for the main probe. 2 different sections, 1 for each probe. So in Linux, it works the same way, right? Right? No, of course it doesn't. We're in on the money. Now we see in Linux side with the STAPSDT probes, System Tap SDT probes, there's only 1 NOP instruction. This is the main probe. There's only 1 ELF section. There's also an additional extra section only once in each executable for offset adjustments, but let's not care about that too much. What you find may be interesting here is that there is no is-enabled probe. Instead, a probe, the NOP instruction, its ELF section can have a semaphore attached to it. This is just a 16-byte unsigned integer static value in the writable part of the executable. And it's read during runtime to compare its value to 0. If the value is larger than 0, then the is enabled value is true. But that's kind of crazy when you think about it. Like DTrace today, multiple times mentioned over and over again that the disabled probe effect should be as close to 0 as possible. This does not really sound like 0 to me. We are always, every time you see your probe, or every time you're coming close to the probe, you read that 16-byte unsigned integer and compare its value to 0. This is, maybe this is why semaphores are actually rare in Linux. I only occasionally encountered them when looking up STAPSDT probes on the internet. So, okay, at least the ELF is same. The ELF header sections, they should be basically the same. But no, of course they're not the same. There's some like minor differences with alignment and so on, which is probably just Unix versus Linux. But most importantly, the arguments which are defined in the ELF section are not defined in the same way. In DTrace, it's something like this. This is not quite correct, but you can read this and understand, aha, that's a UIN32T. Yeah, that's a CARP star pointer. Yeah, okay. This is what the equivalent looks on Linux. That is readable if you know the GNU assembler syntax. Mostly readable. You still need to understand what the first part there is before the @ sign. But this is basically on the left side is the size and the same sign of the argument, and on the right side is how you read this value. Where did you find the value? So, and I have actually left a mistake here, but the -1 at parenthesis RDX, that would mean read an read a signed byte through the pointer, which is located in RDX. You can actually add offsets to the pointer value both before and after the parentheses, so dereferencing. And I think you can also add multiple registers together to do interesting pointer arithmetic. And this is probably another reason why semaphores are fairly rare in Linux, because you can actually do a lot of the parameter mangling that you would normally need to do after the is-enabled probe, but before the main probe in the arguments themselves. So now we have achieved it. We are mediocre. We have mediocre understanding of USDTs and how they work in DTrace and on Linux side in the system tap world. What now, though? What do we do with this information? Well, we use what we've learned. So I already have a PR open in the USDT crate to make it work with Linux. It works wonderfully with that code, only the tests need some shoveling. I'll get to it. DTrace for Windows made a bit of a splash. And I'm thinking maybe that wouldn't be a bridge too far after this. Only I'm not quite sure. It kind of seems like, looking at the code, they don't yet support USDT, so maybe we'll have to wait a bit with that. Of course, my JavaScript engine already has a PR open to use USDTs for tracing. And it's been I had that moment the first time that I could run my program and actually see what it's doing live. That was, I thought that first moment was kind of a joke. And then I got it like, whoa, this is actually this is real. This is so cool. Side note, QEMU, that's a hypervisor, right? Or emulator, not quite sure. They were actually looking for Rust tracing impulse just last week. And I think USDT would be pretty excellent there. What can you do? Well, just to make sure that no one else needs to learn USDTs or DTrace the wrong way again, write about the tech, write about USDTs, write about DTrace, write about any tech you do. Maybe do some SEO to make sure that it actually comes up on Google as well. Link to other tech writers, boost others on social media and so on, so that this information stays on top and is, available for the next generation. Right. That's all I had. If you have any questions or comments, shoot, and otherwise, I'm done.
That was delightful. Thank you so much for doing that. Really enjoyable, and thank you for, as you were describing the mechanism in step as insane, I think I had commented on being crazy. So I'm glad we're on the same page there. Helped me make sure I wasn't just taking crazy pills as you were describing what seems like a very strange mechanism. Thank you so much. It was a great journey through memory lane and through Dave Pacheco's blog, which we've all been
there.
Yeah, we've all been like, why is nobody on the internet except for Dave Pacheco can teach me about this? Thank you very much.
Also, your jokes crushed. We were all guffawing, but we're muted because we didn't want to steal the video from you. So you should know all your jokes were landing.
Yeah.
And
you.
would you mind putting a link to your slides so we can? I think we missed the first couple of slides when we were all enthralled by your storytelling. So we'd love to pair it with that. We can clean it up in post.
Yeah, we'll get that figured out in the video. Okay, and then Kevin, if you will approve Nahum, who is going to talk, well, wait.
We're going to take a quick break. We've been going for an hour.
Well, we got, so lunch is coming in half an hour. So
Okay.
my thought is let's press on.
Let's press on.
Thank you, Nahum Shulman. Thank you very much for joining. And I'm excited. You're going to be talking about open telemetry and Dropshot, is my understanding.
That is the plan. Can you hear me?
We can, yes, and we can see your slides too.
Perfect. Okay, and I'm on the wrong slide. Oh god. All right, here we go.
Now we can see your first slide, even better.
Amazing. I've linked to the slides in the Discord channel as well. But yes. All right. So where's my notes? Here we go. All right. So the purpose of this talk, I love DTrace. And I also love distributed tracing, and I think OpenTelemetry is really great. You all love DTrace. If there's anyone here who has never heard of distributed tracing, then if I've found someone in the lucky 10,000 today, then that's successful. But also, I do want to do this work. All right. So the context back in the day when I was at OmniTI, there was an incident where a Rust application, where a Perl application was misbehaving in production. And I was very fortunate that Theo Schlossnagel had put the USDT probes into Apache that was running on the servers that I had suddenly found myself debugging. And so this DTrace script that you can see on the side, which was preserved by Leon Fayer in a talk of his that is linked in the speaker notes, is something that I wrote in anger while missing out on Thanksgiving dinner. And it helped debug the problem. And the lesson I learned from this is very much echoed by my experiences using OpenTelemetry in recent time. And why I believe that it is very useful for application code. I think for high performance system applications, the stuff that Oxide is working on, you really need the no probe effect. DTrace, you only turn it on when you need it. For high level applications, particularly when they are talking to each other over the network, it is really worthwhile to spend the performance and storage on capturing this information sort of all the time and being able to benefit from it. So yeah, I was staring at this output and seeing literally like these endpoints are much slower than the other endpoints, and saying to the developers, hey, please go fix the those pieces of code first, because if we fix that, that'll help make things better before they sort of finished fixing the bug. So that's how I ended up looking at these sorts of things. All right, so just sort of recapping, we had USDT in place, and I was very lucky that we had it there. And I had root access on those machines. I could log in and I could run DTrace. But today, I now run my applications often on top of a Kubernetes cluster that someone else manages. And my applications are both the client and a server. And there's other people talking to me talking to other people. And just knowing what my application is doing is not enough to fully understand the system. An abridged history of distributed tracing, link to the article by John Willis that I stole this from. Originally, there was the Dapper at Google and Zipkin at Twitter. I spent a few years working for Uber's self-driving car unit, ATG, which is where I was introduced to Jaeger. And now there was an open source project called Open Tracing that has now sort of become the tracing part of OpenTelemetry. And the two things I really want anyone looking at these slides right now to take away from this is the concept of a trace and a span. So the picture shows a trace. A trace is made up of multiple spans, and there's a parent-child relationship between spans. So you can see like this is a client span, and underneath it is the API span, and it does these things. And this ability to visualize a distributed system is very important, and also the ability to sort of to instrument and measure it and understand it. So why would I want to put OpenTelemetry into Dropshot? I anticipate writing new software, and for any reason you might want to use Dropshot, the linked in the notes is the contract as code as contract, which I had misremembered as code as contract as code. So I had to go find it. Adam and Dave did a great talk explaining why you would want to build your applications this way. And having clean API boundaries between pieces of software is a really great thing. And using Dropshot helps you do that really well. And like I said, I'm going to be writing software in distributed systems, and I want to be able to integrate into those systems. So most recently, I worked on a piece of client software in Rust that was talking to Golang applications that were already emitting OpenTelemetry tracing spans. And so I was able to add OpenTelemetry to my application, and everything sort of is beautiful, and you can see it in the tracing systems. And if I write server software, I want similarly, regardless of what language, as long as the clients and services I speak to are using OpenTelemetry tracing, that we can all sort of see what the system is doing. All right, so demo time. I think I need to change my share real quick because I'm going to want to present just the whole browser if I can, please. It should be here. So now you should see my whole browser. First, I'm going to show some staged output from a previous experiment that is not currently what the code I have is right now, but to sort of show the thing I'm aiming for. So this is with all sorts of unfortunate names, showing a client speaking to a Dropshot piece of software, and because I'm still having trouble getting the parent-child relationship to work out quite right, this is showing up as a child of this instead of this. But you can see then inside this thing that I'm trying to find that I made 2 more calls to a Dropshot service. In this case, this was all in a single process. Later on, I was able to get split up my front end and my back end, which is the I have things in today. And so you can see the client talking to this front end, and then separate. And if you see these black bars, OpenTelemetry tracing has this notion of sort of what's the active span. So if you can see like there was something not quite right, because these were sort of, as far as I was concerned, the active span, but they weren't marked active. So over here is the other side, where the front end was actually talking to the back end. And this is actually sort of a useful visualization to see that I had this thing that was talking to this other thing, and it was working. So what we're going to do is we're going to go into my Jaeger and just make sure there's no traces here. And if I share my shell real quick, should be, where did it go? It is named, oh no, window, there we go, there. Okay, so hopefully you see my shell now. So I have Jaeger running, I have an OpenTelemetry collector running, and a traffic front end. And I have a couple of pieces of software. I have this front end. Actually, I'll show the back end first. The back end, which is basically ripped off of one of the Oxide demos for Dropshot, where it's got the counter, and the only thing that's different is I have wired up the OpenTelemetry stuff to be listening and sending out traces, spans. And the other file is this front end, which again is the same file, just sort of hacked up. And I added an endpoint. Where did it go? Named /get. And what it's going to do, and it's littered with comments and skeletons of things I'm trying to get working, where I'm going to call into the front end, and then it's going to make a couple of calls to the back end to get the counter. So this is the code that I'm working with. It is still very much under development. If there's a BOF where people want to help me hack on this and get things actually working, that'd be lovely. So if I run the back end and run the front end, and I run curl in a way that has it emit some OpenTelemetry tracing headers as well, then if we go back to the Jaeger, then if I look for traces, we can see a few different things. I didn't highlight. There's something which is in another slide, in the next slide, that will become important in a moment. But you can see the client made a request to the front end, and I've named that something a little cleaner now. Now it's a drop shot request. You can see that it did get of /get, and it was 200 whatever, and that it's from this drop shot tracing, the drop shot crate version, and then over here I do have this. Here's this span that came from the front end that made a couple of requests to the back end. And again, those are drop shot requests, and they were /counter, they were exit 200, right? So you can see the shape of sort of traffic as it flows through the system. Sorry, wrong button. And the other thing that I'm going to highlight briefly and then sort of talk about some other stuff is I have these things that are from the tracing crate. And the tracing OpenTelemetry crate. So I'll talk a little bit more briefly, but I'm going to show the code because why not? So oh God, Chrome is not helpful with this. The drop shot source server.rs. The tracing crate, and I actually named this feature Tokyo tracing instead. So if I've enabled my Tokyo tracing crate, if you use the tracing instrument macro, then the tracing crate will wire up a ton of stuff. And if you use tracing OpenTelemetry, you can get all that stuff shipped out using all your existing telemetry stuff. Tracing. And so here's another one. And this one, you can see that I've actually annotated it to skip the fields that are coming in from the function call, but to actually annotate with things like that I might care about, like request method, URI, things like that. All right, so back to Chrome, back to the browser. So you can see how when we got into this request handle, I was able to see, like, yes, this was here's the headers that were accepted, that it sent, and the HTTP version that came through, all that stuff. So that's the little bit of technical demo I have. Again, I'm still actively hacking on this code, trying to get it to work properly. And someday maybe it will. Back to the slides. So there are some open questions. So if you, and linked in the slide, in the speaker notes, the OpenTelemetry project is trying to decide right now whether to sort of stick with the APIs they've built out that are sort of mimicking the rest of the other operating system, the other programming language implementations of OpenTelemetry, or should they switch to the Tokyo tracing crate? I believe a maintainer works for Oxide these days. And if so, that would simplify. You could always just use the tracing way of setting up all the tracing information and then just export it via OpenTelemetry, which would make a lot of things much simpler, as you saw with the macro that I was using in the example. Additionally, there's a discussion in the Dropshot project about moving to Tokyo tracing. Again, if Dropshot adopts tracing, then just having all of that stuff exported via tracing OpenTelemetry would probably wire up a ton of visibility into Dropshot applications very, very quickly and easily. And there's also an issue about looking into USDT tracing being more generic, which if it were, it is possible that then in USDT, one could implement the OpenTelemetry bits and then have it live there instead. But I don't know. Probably not. Yeah, so next steps. I'm probably going to keep hacking on this. I want this for myself. I'm doing my best to keep it all sort of gated behind features, so that if you compile and you don't enable it, then it's not in your code at all. But that if you do, then it's right there. And again, if I succeed, then I will open a PR. But if it is too invasive, then I will maintain a fork outside. And that is it. If there are, I haven't been looking at the Discord, so there we go. There's tons of stuff in there.
Thank you for this.
Yeah.
I think you got to most of the questions through the course of your talk. I would just say, like, this has already spawned chatter at Oxide. Like, this is exciting. We should use this. So a lot of abstract, in some cases, concrete enthusiasm. So really cool stuff. Multiple DMs saying like, "Hey, we should use this. Should we use this? Shouldn't we use this? Why aren't we using this?" So very cool stuff. Glad you worked on it, and thank you so much for presenting. This was delightful.
All right, let me stop sharing.
Yeah, no, just to echo that, this looks really great. Where in terms of availability, you said that it's you have it sitting in it.
There's a ugly branch sitting in my GitHub. I think it's all linked in the speaker notes. It is not yet. It is not yet other developer ready. It is ready for like someone to help hack on it with me in a pairing for a little bit and get it into shape. Hopefully, someone who has a bit more understanding of how to pass. There's like 3 different notions of contexts, and figuring out which context I need to pass around is proving tricky. So probably rubber ducking with someone else who understands things would be great as well. Or again, if the tracing crate is the way to go, then doing that. But yeah, mostly I wanted to make sure that people are aware of this kind of thing for big distributed applications where you're less performance sensitive and more important to be recording the important data so that you have things like latency, which pieces of software is talking to which, where's the slowness in your distributed system, as opposed to just debugging high performance storage systems on a single node.
Yeah, absolutely. And I think that there's such a kind of a shared approach with Dapper and the systems that it inspired, Jaeger and then open telemetry and so on, open tracing. So I think it's great, really exciting stuff.
Yeah.
Thank you very much, Nahum.
Yeah, thank you. Do we want to break? I know lunch is not yet here. Do we want to?
Yeah, let's.
An hour?
Yeah, let's give folks a we've got the famous Dave Pacheco.
Right, a lot of Dave Pacheco hype.
The incomparable Dave Pacheco.
That's right. So stay tuned. Big agenda for the afternoon.
And then Chris Van Hees is here. And Ryan Goodfellow, our afternoon agenda. And then potentially we got some other.
You've seen some slides slinging around. We have Robert working on some slides. Eliza just realized that she may have a speaking part in this production. So may have a full afternoon.
Okay, sounds good. Do you want to would 45? Do you want to break 45 minutes or an hour? What do you want?
I say an hour just because the food isn't even here yet.
Okay, fair enough.
But whatever you think.
Sure, let's get that sounds good. Let's do an hour. And with I think we have the intent of wrapping by 5 o'clock Pacific. Which I think we'll probably be on.
I think we'll be on time for that.
On time to do. So yeah, let's wrap for an hour. Great talks this morning all around. Yeah. And really just a delightful cross section. It was really great, and thanks to especially those folks coming in remotely. Really appreciate it.
Yeah. This is a great morning. Very, very exciting. Thank you, everyone.
All right. See you back in an hour.
Yeah, back in an hour, and a big agenda for the afternoon. See you soon.
All right. Welcome back, everyone. The morning session was terrific, and people have mentioned Dave Pacheco a bunch. So I feel like the man who needs very little introduction, Dave Pacheco himself.
Thank you, Adam. All right. Well, I have been using DTrace for kind of a while, but in the last couple of years, especially, I've had the pleasure of introducing a bunch of people to DTrace, and so I thought I would share a couple of resources that at least I have found useful, and I will actually be interested to hear whether other people have found them useful as well. And I figured it might be good at some point, maybe later in this, to crowdsource other things people have found useful, because I know people learn it in a lot of different ways. Anyway, one of the big challenges I know a lot of people have learning DTrace as well as other debugging tools and other tools, the test tools are also in this bucket, is that if you don't have a concrete problem in front of you, it's often hard to know where to start. But once you have a concrete problem in front of you, then you don't know anything about the tool yet, so you don't really know where to start with the tool either. And you're often under time pressure. And so one of my favorite things is Adam's DTrace Bootcamp from several years ago. One of the things I like about it is that, where is it? Is that it opens saying that it's very much a work in progress. It is
Not been much progress.
this is from 2005, I believe. But what I really
Very much work in progress.
Past Adam has left us a note.
Yes. I'm trapped in a software factory.
the thing I really like about it is that it has both a bunch of examples, but then concrete exercises for you to extend those examples. And so you don't need a concrete problem to solve to go start playing with it. So as an example, it gives you, I think it gives you an example of listing all the probes on the system. And then it's like, here's how you specify a particular probe. So now like enable that one probe. I should just actually go to the deck. Yeah, so, you know, here's how you can list all these probes and then list some of them, combine these things, try using wildcards. The answers are not here, but I think each of the exercises is generally a pretty small extension of what it's already told you. So I think that's not generally a problem, and there's other good resources for learning about that as well. Anyway, there's a ton of stuff here. It goes through, you know, it goes through all the basic stuff. It goes through listing probes, enabling probes, adding predicates, aggregations. I can't remember if there's, there's associative eraser in here as well. Spread local variables, stack, all the basic stuff. Like I think if you go through this, you will have at least seen all the stuff that people use on a daily basis with DTrace all the time, which is great. And it's in this sort of iterative way without having to have a problem in front of you. So I like that a lot. The thing that folks have told me is really useful for if you've really not seen DTrace at all before and you're like, I'm just getting started with it, the Dynamic Tracing Guide, which is the ebook on the Illumos website, is both a great introduction to what DTrace is, including a bunch of examples of how to use it. And it's also a great reference. I think it is basically the canonical reference for so many things. So if you want to know what subroutines exist, actions, variables, let's see, I have that up over here. So this is on lumos.org books DTrace. The getting started section, you know, walks through some examples similar to the bootcamp does, which is great. But then you get to all these reference sections for the different providers, like the profile provider. That's actually sort of a more complicated one to document because the probe names are dynamic, but like the proc provider lists all the different probes that exist in the proc provider and what they mean and what their arguments are and the types and things like that. So this is a really good reference and it's also a good introduction. It's also the only documentation, I think, for a lot of topics that I was going to call more obscure. I think you called arcane earlier around like anonymous tracing, postmortem tracing. I'm not sure I've ever used postmortem. I don't know. I have used postmortem. I've definitely used postmortem. I forgot.
Oh my God.
It's been a little while.
It's like a test. You
I've never used anonymous tracing, but I have used postmortem tracing. So if I were starting from scratch today, I would start with that book. Then I'd go through the boot camp to work through a bunch of those examples. And I think you'd have like enough to hang new content on that you could start playing around with it on real problems. Then there's the DTrace tips, tricks, and gotchas presentation, which is Brian's presentation from 2005. This one definitely assumes that you've already got the basics down already. But then it goes on to cover, you know, what it calls tips, tricks, and gotchas. So tips are things that are documented but worth highlighting, I think. It's a good summary. Tricks are techniques that people learn on sort of like on the job as you play around with this thing that are perhaps not obvious. And Gotchas are things that problems that you run into a lot and how to deal with those problems. And I think a good example is there's a trick in here, which is using stop as a conditional breakpoint. So there's a stop action, which I love. So stop is an action. It's a destructive action you can put into any probe, which introduces basically a debugger stop into that process at that point. But there's a gotcha with it, which is that if you forget to put a predicate on your probe, it is very easy to accidentally stop every process in the system. Gotcha. And of course, so the deck talks about all of those things, which is really good. Another one that people run into when you start building more complicated scripts are different types of drops. So you have buffer drops where you're collecting more data faster than it's being pulled out of the kernel, and so the data gets dropped, or dynamic variable drops where you run out of space for the dynamic variables. And it talks about how to tune those different things. And these are things that are like, it's not really like a bug. It's just like, this is an intrinsic problem associated with what we're trying to do, but you still need to know how to deal with it and work around it. And so the trick goes through quite a lot of those things. I think of this as like, sorry, that's the wrong one. This deck is like, if the other stuff is like the book smarts of it, this is like building up a whole bunch of experience with DTrace. So if you've used DTrace for a long time, there's just all these patterns you learn. Like, what if I want stack traces only containing a particular function? It talks about how to do that. One way to do that is you can, sorry, that's not what this slide is, but you can use an associative array, use a thread local variable to condition your later probe on having been in that function, and then grab a stack trace in that. There's just a lot of stuff like that. The other thing it reminds me of is we've talked about this, like with Vim and MDB and other tools like this. I know all these people that use it every day that know that are like very fluid with it, and we all seem to know about 10% of what they're capable of, and that set only barely overlaps. And so every time you're looking over someone's shoulder, you end up seeing something you've never seen before, and you're like, wow, that's really cool. This presentation distills like a whole bunch of those things. So I think it's kind of like a way to fast forward through a lot of experience with DTrace. So I like that one. Then there's the DTrace book, which is like, if you're going to sit down and spend a lot of time on this and read something cover to cover, I think this is a great resource. This is Brendan Gregg's book. It goes through first principles. It goes through a bunch of examples. It's got tons of one-liners, and it's got a bunch of more complicated scripts. And it also covers implementation details and architecture of the things you're probably tracing, including kernel subsystems and applications and things like that, to explain how to trace them. Because very often, in order to trace something effectively to debug it, you need to understand something about how it works, and you need so that you can understand what points to instrument and what data you're looking for and things like that. So it has chapters on the file system, on different levels of the networking stack, etc. So that's really useful as well. Another good resource, I think, are the scripts that are provided by a lot of projects. And this is very biased by the projects that I have been involved with or close to. So that first one is actually a set of scripts that I wrote while a joint for tracing Postgres. This is PG SQL stat. So Postgres already had DTrace probes, and I wrote a bunch of these like stat tools, kind of like VM stat or whatever, for tracing the activity of Postgres. And I think these kinds of scripts, I think it's great when projects include USDT probes and then also ship scripts, like Alan showed earlier, that are using those probes and providing like a useful monitoring tool or whatever it is. And then you can learn from those, and you can figure out like how I want to apply that to something else. It definitely is like a more active learning sort of thing, because there's just, that's the documentation. Like, if you don't know anything about Postgres, this isn't necessarily going to mean anything to you right away. But I do think the patterns that you see in different project scripts are useful elsewhere and worth digging into if you want to better understand DTrace. So I've linked here in this deck, and I'll share it later. I've got links to all the things that I've been talking about: the decks, the DTrace book, the ebook, the official guide, and then all these projects. And I would love it if people in chat dropped other resources in general, but especially projects that ship their own descripts for their USDT probes. I think that would be really interesting to see. And I also discovered as part of this awesome dtrace.com. I don't know, have you guys seen this before? I had not seen this.
Oh, awesome.
Awesome DTrace. And it just has like a ton of links to a whole bunch of different things, like Ruby and DTrace and past dtrace.conf. I don't know who did this. And like I've only been on this for I know, right? I've only been on this for 5 minutes, and it could be these are all links to malware, but it seems pretty cool. It seems really nice. And that's all I got.
This looks great. Yeah, not awesome. So, thank you very much, Dave. Because you also, I think, helped a lot of people learn DTrace at Oxide. Where have people stumbled?
Ooh, that's a good question. I don't know. I kind of feel like I want to ask some of those people. I haven't done it as much one-on-one at Oxide to know like where people are running into that trouble. In fact, like, so I recommend the boot camp to like everybody, and I've been saying it for a long time. But I'm curious, like, how many people have actually like read it and gone through it and found it useful, or is it like I'm the only one that found that useful?
For what it's worth, some people are like, I read it and it was useful.
That's good. That's good
like,
to know.
I don't get a lot more depth than that. I think they realize that I'm probably not. It's not actually the work in progress it claims to be. But yeah.
Yeah, and Bree in the chat says the biggest place that I stumbled is what should I be tracing? And this is, I mean, one thing we've said, you and I, David, said before that the knowing what question to ask can be really difficult. That's part of the reason why those USDT probes are so important to give you starting points to ask questions.
Yeah, that's huge actually, and also the fact that DTrace has -L, like you learn that at the very beginning and then you forget about it for a while. But it's actually really useful when you walk up to a program you're debugging that you haven't seen before. So a couple of months ago, this is actually at OxCon, we were debugging a problem in our networking stack, not in the kernel networking stack, but in a userland daemon that was doing some of our data path. And all I knew was that it had DTrace probes. And so I walked up to it with DTrace -L, and I saw that a bunch of them were called drop, and I enabled the drop ones, and I was able to confirm that it was not dropping the packets, and that was actually incredibly useful. So there's a couple of pieces around discovery that are there. But I think that is right from my general experience working with people with DTrace is that it's that very first like 10 minutes or half an hour of debugging a problem and trying to figure out like, wait, what do I do? There's 1,000 actions here. I'm not totally sure of the syntax yet. I don't know what probes to use. And that is tricky. And that is where you kind of need a real problem, I think, to motivate whatever you're trying to do. And I was thinking, like, how did I learn any of this? But I had the benefit of like being in a room with a bunch of people that use DTrace all the time. And I would just be like, I need help with this problem. And they'd be like, well, let's teach you how to use DTrace to solve this. So that's pretty fortunate. And I don't know how to replicate that more broadly. But it's a great way to go. You could, I don't know, like, is there like an open office, the DTrace office hours or something like that?
You should do that.
All right, I will do that. I'll do that.
So Matt in the chat is pointing out some of the stumbling blocks that he said was kind of interesting. One is around this versus self, so clause local variables versus thread local variables. Which I think we both I think the tips and gotchas I know talks about it as just the documentation, but that they can be counterintuitive, especially because both this and self have been used in different languages in different ways. So our apologies if that's totally counterintuitive how we've done it in DTrace.
I think part of the reason we did that was like we felt like they were both reserved-ish words. So like we were going to conflict with things.
No, we're gonna conflict with them. We're just gonna override them.
The syntax.
Tactically, only semantically.
Brains.
That's right.
I almost never use clause locals. I don't know. Is that a thing? I mean, I know it's a thing, but like,
I've used clause locals a lot because they're also not clause local. I feel like this points to is like we call them clause local or probe local, but they're not, right? They're like this probe has fired and it lives for the duration of that. And I don't know that we've ever done a good job of explaining that.
Tips and gotchas, let's go into that.
All right, sweet. Well, that's
because the
tip.
Clause local variables are preserved. There are
across
clauses.
Yeah.
Look. Oh,
I can see what this is going. This is going in a new direction. Let's talk about something else. And then Matt does point out that another place he stubbed his toe is with floating point arguments because that doesn't work.
I don't know. What else? Floating point? What?
Why would that be a toe stubbing thing?
Point in USWin.
Floating points? I don't.
It's
like a number.
You know what? Never mind.
Like an integer, like a string.
You're a witness, Keeter. I'm done here.
All right. Cool. Thank you, Dave. We're gonna just pause the video for a quick second while we switch out to Chris.
All right, Dave, thank you again. And I feel very fortunate. Chris Van Hees from Oracle has done some really remarkable work with DTrace over the years. I think you first did the port of DTrace to Oracle Linux.
Yeah.
Quite a while ago now, and talked about
yeah.
that at one of the dtrace.coms. That's right, man. And more recently, and I noticed a video that a presentation you'd given on this. You did some work with eBPF as the underpinnings of a new port of DTrace to Linux. So I'm very excited to hear about that. Thanks for joining us, Chris.
Sure. Happy to. So yeah, I didn't know it was that long ago.
Yeah.
So but and I mentioned this most of the time, but I think it kind of shows you where I'm coming from. So originally, when we were approached to do a port of DTrace to Linux, that came to me for evaluation, and my general response was, I don't think that's going to be possible. So they told me to do it anyway. We got it done. It was somewhat painful, but we have come very far since then. And so when we were later asked to see if we could do this on top of BPPF to not have such invasive changes in the kernel to make it possible, again, I pretty much said, I don't think that's going to work. And well, we have it now. So I got proven wrong twice. That should tell you something. So I'm going to talk very briefly what we had before we started working with BPF, and then get into what happens now that we're building this based on BPPF and other tracing features in the kernel. The how does it work sounds like a very big topic. I'm not getting into all the details. I just want to show a little bit kind of what directions we've taken to make this work, get into some of the benefits of doing this. There's a couple of samples I'll give in to show how creative we've had to be with some of these things, and then highlight complications. And then there's more information like the links. So before we started working with BPPF, we pretty much did DTrace the way it was done before in Solaris, which what you had the kernel space producer and yet a user space the consumer. So the split was about 50-50, if you would look at lines of code, and it essentially worked the same way. Was same type of implementation. The only downfall of it was that we needed these kernel changes, and there was no way they were going to be able to be upstreams in the Linux kernel. So we had a pretty big set of invasive patches that had to be applied to the kernel. And that was kind of obviously a big problem for adoption by anybody who wanted to do this. It's not that easy to convince people to add all these patches on top of a distribution kernel or just upstream kernel. And so it kind of made things more difficult. Plus, kernel changes meant that we had to keep updating these patches. Not ideal for stability, not ideal for overall maintenance. And again, adoption was definitely not something that would benefit from that. So with using BPPF and other tracing features, it's all one component now. Everything lives in user space as far as the DTrace code is concerned. So I shouldn't say all, it's a whole lot. But what we do within user space is these scripts get compiled into BPPF code, and then these programs are loaded into kernel, and everything runs there within the BPPF execution engine. So that means that the actual implementation of how the providers, not how they work, but how you get essentially a DTrace provider presented to DTrace the way that DTrace would want it, based on trace points that exist in the kernel, is all things that have to be done at the user space level. So we have a lot of code there that creates that, but it also means that knowledge about which probes exist on the system now have to be maintained at user space. Before you just ask the kernel for information about the probes you're interested in. In this case, we actually have to have all that information in user space. So that's quite a bit of extra work there. Then there is also a bunch of support functions we need to essentially know how to implement DTrace actions. This, again, nothing exists on the kernel. So this all is implemented in BPPF code. And then there's support code for that. There's pre-compiled BPPF code. Obviously, we compile D directly into BPF instructions. And now we have a linker that meshes it all together and create something that actually works. Interestingly, and this line count obviously is very rough, but it's kind of the same amount of code as existed before. It's just now been shifted into user space and horribly mangled and rewritten into ways that's, it actually does what it needs to do. So I tried to make a graphical explanation of how this works. I don't know if this actually necessarily makes sense, but so on the very top where you have user space, that is where DTrace sits. And that's the only real thing that still exists in terms of DTrace code. So it handles the providers, the probes, we have the compiler sitting in there, the consumer, everything. And it gets its data either from perf event buffers, which is where the trace data is stored. And then there's a whole collection of BPF maps that store additional data. Things like aggregations are kept in there. And some of those are used by the consumer, like aggregations to get data, and other of those are only used by the BPF programs, which is kind of then the next layer, which is all the work. So that is literally the D scripts compiled into a BPF program, all the code added into it to make the actions do what they're supposed to be doing. And that is just presented to the BPF execution engine, which then interfaces with all the other tracing features in the kernel, which is kind of the lower level. And the naming here is a little messy. In some sense, it's mostly a combination of K-probes for function boundary tracing, or F-entry and F-exit. Either can work depending on your kernel. The rest is either trace points, perf probes, or U probes. But I kind of split them out so that there's at least maybe a sense of which DTrace probes would relate to what. And I didn't add a slide for this. Probably should have thought of that. It's kind of a little late now. But sometimes a DTrace probe may have to be tied to multiple operating system trace points or probes in order to accomplish the same, functionality. So it's not always straightforward one-to-one. So how it works? Initially, the idea was it's just going to be a straight compiled decode into BPF code, replace actions with function calls to pre-written BPF code, and all should work. That's not the case because we had to start thinking differently, where DTrace traditionally has been working completely action-based. And so the way the clauses in a script are compiled, the code is being generated on a per action basis. That doesn't work anymore. So we had to start thinking more on a class base, and then still in the back of our mind realize that we're still dealing with DTrace. So you can't completely shift focus. But it made it possible to take an entire class and compile it into what would essentially be a BPF function. In order to do that, we had to come up with a generic probe context, which DTrace already had. BPF does not. So by doing this, it was possible that you can have a single class which is connected to a variety of different probes that actually may use different mechanisms in the kernel in order to be triggered, but the class can still be compiled one time and just linked into the correct program. In order to make that possible, we had to come up with a way to essentially structure trampoline code, which is the beginning of the BPF program that gets attached to a kernel level probe. And it essentially massages all the information about the probe into this generic probe context, which then also contains the machine state that DTrace needs. And so as far as our BPF implementing DTrace probe scripts is concerned, all probes look the same. They all have the same way of how arguments are presented. They have the same ways of the probe IDs. So they act and feel and look like a DTrace probe, which made the rest of the implementation a lot easier because we could just reuse a lot of the way that DTrace was working. So a BPF program really simply becomes a trampoline that creates this generic probe context. And then we essentially just call the classes that are relevant to that particular probe one by one, with obviously checking in between that if probing stops, we need to stop calling them, and handling of error cases. But it becomes pretty much just a program. That did require us to have a custom linker, and this is kind of actually, it was meant to be a linker that takes this BPF program with the trampoline and the function calls, and then resolve these calls, pulling in the code for these different classes, some precompiled code, and create a nice package and load that. It turned out to be a multi-stage linker, because there is also certain information we need that at the time when we link the program, for instance, we don't know how large certain BPF maps are going to be. So we have to do a second stage where we resolve those contents that are kept in the code using relocations, to right before it gets loaded to the kernel, to fill in these constants so that the program actually knows, for instance, how big the string table is, things like that. So the benefits for this obviously are that there is no more DTrace specific code in the kernel. And I don't mean this benefits from the DTrace side, it means benefit from the Linux kernel side. Because we usually depend on some patches, even up until, I would say, maybe a year, 2 years ago, we still needed some patches in the kernel to have a feature called wait FD, just made it possible to wait for both the lifecycle events for processes and what is happening with our tracing, CTF to get our type information, and then this KL mod sims, which associates module names with symbols, even if the module has been compiled into the kernel. Because with the Linux kernel, the fact that the module can be either loadable or built in was posing a problem with having a stability of scripts. We wanted to be able to refer to symbols with the module backtick symbol name, and not have to worry whether the particular kernel we're running on has this module built in or has it as a loadable module. So that was also something we had to add to the kernel. We no longer need to wait FD. The KL mod sims has now been replaced by the modules built-in ranges file, which is a patch that was upstreamed into the Linux kernel. So every Linux kernel starting with 6.12 will have that if the correct build option is enabled, which it seems like most people do want to use that because it's local. Well, it's essentially zero costs for a running system, and it can really benefit tracing, DTrace, and even other tracers. And we also can now use the type information that BPF provides through BTF instead of the CTF. It's not one for one. For instance, right now, BTF does not provide type information for kernel global variables, which is a real pain. But you can always cast the symbol to the correct type if you need to use that in a script. And in the meantime, we are actively trying to work with the BPF teams to get BTF to actually include this type information as well, which would be a big step forwards. So all this work having been done has resulted in a DTrace version that can right now work with upstream kernels starting from 5.2, which is like pretty old at this point. But it's kind of nice to know that that's doable, because we've had to be able to provide support for production kernels that pretty much go back that far. And as I said, there are some limitations, types for the global variables if there's no CTF, but it's all things you can work around. It's not a deal breaker. Now, the real benefit was that by doing this, we have been able to remain true to the overall DTrace design and operational expectations. So semantically, things should work the way you would expect if you're used to using DTrace. That has required very crazy code in some places. And I wouldn't say it's 100% perfect, but most of the time when people have come to me that something doesn't work, it's that they don't understand how DTrace works instead of it being a bug. So at least that's happening more and more. So that's a good thing. So since this morning, we've been talking about is enabled probes quite a bit. I think I'll use it as a highlight of something we had to do. Given the fact that we no longer have code in the kernel ourselves, means that we couldn't implement USDT probes and is-enabled probes the way we did before, because they're using a U probe, which is what we did before as well. But the is-enabled probe would, when it fires, then patch the instruction to make sure that this test would now be evaluated as true, and we would have basically the benefits you had in DTrace beforehand, that it's extremely low cost. We no longer can do that because we can't patch in that way, or at least it would be extremely painful to do so. So we came up with an alternative which may not work with all C compilers, it definitely works with GCC, and we're evaluating others as needed. But it's using this construct where we can essentially declare a variable that is in just that local scope, which is initialize 0, then do our fake function call, and then essentially the value of that scopes variable is going to be given as the value of the macro. So in code, this still works almost the same way. And for BPF code, in this case, we are given, and I have a typo there, should be arg0, because we are passing the address of this locally scoped, very short lifetime variable in this probe firing. The moment the probe fires, we can write in a 1, and that is what will then be given as the evaluation of this expression, and code will work the way it should. So it's not exactly the same way as it was before, but it's about the lowest cost version we've been able to come up with. And that was, I think, probably the 5th or the 6th variant of trying to come up with something that was as lightweight as we could do. So if anybody has ideas to improve this even further, we're open to it. Aggregations, really good feature in DTrace. Was a pest to implement, because the way it was working before in DTrace, where the kernel is accumulating, it's aggregating this data, and then when user space is ready to use it, or on a timely fashion, would read it, which generally would result in a buffer swap, and then it would be further aggregated in the consumer, in user space. That doesn't work, or at least we couldn't get it to work, because access to a BPF map, which is where we had to store aggregations, there's no proper way to synchronize. You can't do locking in between user space and the kernel. And we tried to do a mechanism which is similar to buffer swapping, where we kind of swapping 2 elements in a BPF map, and it was horrendous. We never got it fully to work, and we abandoned that whole idea. So we came up with a different mechanism, which we should have thought of in the very beginning, is if you're aggregating in the kernel and then taking snapshots of that and aggregating those in user space, you can either continue aggregating in the kernel continuously, and instead of having these partial aggregations, and then just have user space read from the kernel whenever it needs the data. That has some impact on how short-lived the aggregation data in the kernel can be. So the footprint in the kernel for memory usage is going to be higher. But we felt it was more important to actually have accurate data than to minimize the footprint. So it works. It was even still difficult to get done. And Clear and Trunk are fascinating implementations. Anybody wants to look at our source code and see how we did that, I would definitely suggest that might give you some very good nighttime reading. So complications. The BPF verifier, it's something you get to either love or hate, or both, more commonly both. So it's what makes it safe to have BPF programs loaded into the kernel and executing, because it does its best to make sure the program cannot do anything malicious to the system. So it tends to err on the side of caution, which means that it may reject a program that is perfectly safe, but it rejects it because it can't prove, well, in a sense, can't prove that it's safe. So it can be very difficult to keep it happy and still write more complex code. Supporting older kernels is a challenge, in part because of this verifier, because the verifier obviously changed over the different kernel development stages. And so things that it would reject in the past will now pass. Well, it would reject in the past, they pass now. But there are things that it would accept in the past that now it rejects because they changed some of the logic behind it, and they felt that would not be safe anymore. So that has been an interesting challenge. And then the overall concept of BPF and the kernel tracing features in the sense of how DTrace works and how DTrace can be used as not necessarily just a one-shot tracing, but you could actually have a tracing session that can be running for a longer time, that is really monitoring the system for quite some time, is not really the use case that BPF and most of the tracing features have been used for. And so we really put those to the test and came up with some issues that had to be resolved. So one of the problems also is that sometimes with DTrace, at least in our use cases, and maybe we're kind of extreme, but it's not uncommon for us to be probing 1,000, 2,000 probes. And attaching BPF programs to about 2,000 probes can be a very time-consuming business to get done. And we brought it up with the BPF maintainers. And one of them, his suggestion was from, well, if you just do one big program that can serve all those probes, you can load it once, attach it to all the different probes, and that will work, which is very ugly. It's not really a good solution because you're just going to have one big program with a very large conditional that says, okay, if it's probe A, then do this, probe B, then do this, probe C, do this. So we're really hoping to have a more sound solution to that, where we don't basically have to load a program to every single probe, of which maybe only 10% of the program will be used. Another problem with BPF is it has a small stack. It's 512 bytes. Yeah, which we can work around because the way, fortunately, D code can be compiled, and the fact that it was originally designed to compile on an action basis helps us, because it means that basically you don't really have that much stack need. The problem comes in when you have pre-compiled code. We have this library of functions that implement things that are not available in the kernel for BPF. Things like, for instance, taking a substring or converting a string into an integer, things like that. They're compiled with GCC, which assumes you have a reasonable stack. So if you have a couple of these functions that are being called, especially in nested levels, you very easily blow through those 512 bytes. So we had to be very creative and conservative in how we write our code, which has also resulted in the decompiler to be a little bit more ugly than I would have liked. And so, in summary, it always comes down to the BPF verifier. If that was not happy, your program's not going to load. So that is kind of the measure we always have to work against. And so we sometimes will go for larger programs with less complexity in order to make sure that we can do that. For more information, so the source code is available on GitHub. It should compile on pretty much any Linux system with a recent kernel. It does depend on the BPF cross compilers with GCC and binutils, and it works. I mean, we use it in production. We use it to develop DTrace. Because one of the coolest things I found is that you actually can trace DTrace with DTrace.
That's
And
nice.
how it works. So yeah, it's been a joy. So thank you.
That's great. Thank you, Chris.
Yeah, thank you very much.
So I've got a bunch of questions.
Okay.
Um,
Better-
Brian, why don't you come on camera?
Sure. Hi, Cameron. I've got a bunch of questions. One, so because we've been using BPF trace to help debug some to get a guest's perspective. So we're running hardware virtualization.
Yeah.
And obviously we've got DTrace and hypervisor, but we don't have it. So I'm very interested to be able to use actually DTrace on BPF in these guests. One of the frustrations has been with dropped data from eBPF.
Okay.
How, and because in DTrace, we try to be very careful that if we drop data, we indicate that we've dropped data.
Yeah.
And I'm still not convinced that I wasn't, I think I may have been holding it wrong, but I was getting silent. It's very hard to know if you're getting silent drops. I mean, so
yeah,
is that something that so obviously it's on BPF to get the UBF to get that right.
Yeah. We haven't had, I mean, we've seen drop data, you know, like we've seen it in general with DTrace even before. I think in almost all cases that I can think of, it is being reported. And that is something that we actually spent quite some time in, is to make sure that the drop counters reports is there. Because that was something we were missing in pretty much any other tool.
Right.
Because the advantage is that actually the biggest drops that occur is basically if it cannot be written to the perf event buffers. And that we have notification for. We actually can provide information.
And so you wire yourself up to that notification.
Yeah.
Okay.
So that is not a problem. So those we have had, what we have run into is that the perf subsystem in some cases, for lack of better terminology, is refusing to fire a probe. And there's not much we can do. Timer probes on some architectures are an issue with that, depending on the kernel configuration. And so, yeah, tick probes, for instance, and profile probes have been inconsistent. And we have been trying to work with kernel developers to find out why. Because it's actually not even anything on the BPF support side. It's actually really in the perf subsystem that it seems that either they're throttling it for some reason. I know one of our developers thought he had a solution for that, but then it still starts happening. So it feels like a situation, and we've encountered in a couple of other cases where the system is somewhat working against us.
Yeah.
But it's a tracing world. You know, we're trying to convince the kernel developers who are so performance driven, which is very important, that, well, if you can't guarantee that the tracing infrastructure is going to be accurate, then you might as well not have it. You know, 90% working that, or even 99% of the time working is not good enough, because the 1% is where we're going to fall down. So that's still a work in progress, but I think it's a bigger problem within the kernel where the data is essentially not being generated.
Yeah, because the frustration that I'd had in particular was trying to pair up events like an IO starting and an IO completing, and you want to know how long these things take. So it's actually important that you get both of these events.
Yeah.
And if you get drops, you just want to know, like, okay, I've dropped this, so I've lost coherence.
Yeah. And one of the problems with that as well is, and that is where Linux is more of a challenge, and that's why we put a lot of work into the different SDT providers that DTrace provide that are documented, because then you have a better notion. Like the IO start and stops. I think at this point we have pretty much figured out that we can support them where they're correct.
Oh, wow.
But that took some time because not all execution paths run the same way.
Right.
And so the IO start usually is very easy to find.
Yep.
The IO done may come from 5 different places. So that's where under the covers, we are actually tapping into those different trace points. And some of them are FBT probes that we place. Some of them are trace points the kernel has. And we synthesize them into one.
So that alone is actually hugely helpful, because I'm not convinced that I wasn't missing one of those paths. I mean, because you're looking at the source code, just like I hope I've got all of these.
Yes.
We had similar problems, even I think early days of DTrace STT. Like it would be when you are placing probes by hand, it is possible to like forget, like, oh, well, actually there might be some completion over here or whatever. So the fact that you're aggregating those things so that every consumer of that conceptual event doesn't need to do that exercise seems hugely valuable.
It is, but that's the power that DTrace has, that it has those documented SDT providers for IO, for SCAD, for proc, and they can hide what is really going on in the operating system, which also makes it possible. I know for some of them, we actually are attaching to different probes depending on different kernel versions.
Right. But you're abstracting that.
But
which
yeah,
is-
with abstracting, we synthesize it into the providers that DTrace
And then,
provides.
and when you, and then this works on different distros that have, as long as they've got eBPF.
Yeah.
So I can run it on Ubuntu.
Yeah,
That's,
should work.
that's great. We're gonna use it. So thank you.
Okay.
No, I mean, this is gonna be super helpful. So thank you very much. This is really great. And what has been the uptake? I mean, obviously you all are using it. Have folks started to use it?
We've gotten more. We've had some, I know Gen 2 has added it to its distribution very recently.
That's great.
So it is becoming, I think people are starting to pay attention more again. I think what fell by the wayside as even, I don't think this makes, but the fact that I think it's persistently still existing.
Yes,
And moving forward.
all credit to you. Like
So I think it's great.
like that is the still existing. That's great. Well, thank you very much. I think this is going to be this is great for because I think by implementing it this way, you just get you are now going to be present in a lot more distros, which is
Yeah, and hopefully that will also encourage people to help to contribute.
Yep.
And move things forward, since we want to keep going forward.
Yep. Awesome.
Absolutely.
Chris, thank you so much, and thank you so
Okay.
for being here.
Thank you.
Really appreciate it.
I'm going to take a break now, or do you want to switch right to run?
Sure. We can. You want to take a 10-minute break? Pick it up at 2:30 Pacific.
Sure.
Does that make sense?
Sounds good.
Yeah. We'll take a quick break. We'll be back in just a few minutes at 2:30.
Right, we will start up in 3 minutes, but if you want to share your screen in the interim, feel free.
Sure. Let's just make sure this all works.
For your slides or whatever you want to do.
Okay.
We're seeing the recovery silo.
Yep. So that one works. Let's just make sure this other thing works. Okay.
Be shirts. That might be shirts.
It feels like shirts.
Every time the doorbell was wrong, I thought this could be shirts.
The doorbell right here. The conference t-shirts may be arriving.
And Chris is here, so it can't be Chris. Chris had this morning to ring the doorbell when we were expecting food.
I think we've already eaten the pizza, so.
I think we have.
Were you trying to share something else, Ryan, or are you good to go?
I think I'm good to go. It looks to me that my terminal sharing and my web browser sharing both work.
Sweet. We'll do it like right at 2:30.
Do people know that you're making a Mr.
Okay.
Pig plus reference?
Oh, I got it.
Yeah, okay. I know too. All righty, everybody. All right. We were back here and really excited to have our colleague Ryan Goodfellow presenting on some of the delicious mashup between DTrace and P4. Ryan, take it away.
All right. Thank you very much. Hello, everyone. I'm Ryan Goodfellow. I work on the networking team here at Oxide. And I'm just going to jump right into a demo with this, actually. And so what we're looking at here is a picture of the Oxide rack. And in the middle of the Oxide rack, we have two switches. Each of these switches run on the Tofino 2 ASIC. And one of the interesting things about this ASIC relative to other ASICs that are on the market is we actually get to write the code that runs on this ASIC. And so with great power comes great responsibility. So it's very flexible, but we can also screw things up massively. So being able to understand exactly how our code is behaving on the switches that are at the core of our network is really important. A lot of times when people talk about like these switches, they talk about like the bandwidth capacity of them. Like these can schlep 12.8 terabits per second of traffic. What I like to think about is the packets per second. So these can schlep each of them 4.8 billion packets per second, which to me is 4.8 billion opportunities to screw up every single packet that goes through the rack.
Right. Hey, right. Maybe you're sharing the login to recovery.
Yep.
Okay, just want to make sure that you're not that. Okay, just want to make sure there wasn't a slide that you want to be sharing. Good, all good. Sorry.
No, this is yep. This is intentional. I have no slides for today. It's all demo. So a picture of the rack is my slide. So between these two switches in the middle of the rack, we have like 9.2 billion opportunities per second to screw up every single packet that is coming through the rack. And so it's important to really understand what's going on there. And actually this screen that I'm in right now is a live running version of the rack. So I can log in, actually the recovery. I can log into this, but this is not actually a real rack. And so when I log into this screen, it shows that there's just 4 nodes. And so this is the development version of the rack. And this is a version of the rack that our networking team, actually, we do a lot of our core work on when we're trying to understand, is our entire system working end to end? And when I talk about like kind of what this looks like in terms of like, how do we develop networking code at Oxide? We're talking about kind of 2 different parts of the network: the internal parts of the network that are internal to the Oxide rack, and the external part of the network. And so what we're looking at here in the diagram, just to kind of orient you a little bit, is I'll start from the bottom up. So we have 4 compute sleds, which are actually these 4 compute sleds that showed up on my little console here for the Oxide rack that I just logged in. We have 4 compute sleds, and then we have 2 sidecars. So it's just like the real rack in the sense that we have 2 sidecars, but we only have 4 compute sleds because we're actually running all this as virtual machines inside of a single box, actually using our own homegrown hypervisor Propolis, which is going to become very important later. But we're running this little like mini rack as a set of interconnected virtual machines to represent the real rack. And so we have these 4 compute sleds here, and 2 of these compute sleds are attached over PCI Express to 2 of our switches, which we call the sidecars. Sometimes we call these gimlets that are attached to sidecars or scrimlets, because they're the sidecar attached gimlets. And these are connected over PCI Express to these sidecars. And then upstream from the rack, kind of like outside of the rack, our racks connect to a variety of different topologies. Sometimes we deploy racks to typical enterprise environments. Sometimes we're in data centers. Sometimes we're in point of presence. And so we want to model all of these different networks that we're interconnected to. But there's a whole bunch of different software that is making all of this work. We have customer virtual machine instances that are running on all of our gimlets that are running on this shared physical network that are facilitated by these sidecars. So we have to run a fairly complex like Geneve encapsulation overlay underlay network to allow all the instances to communicate with each other and with the outside world, but not with necessarily other tenants and other VPCs. If you're familiar with like cloud terminology, we want to keep those VPCs isolated from one another. So there's a lot of complexity going on here. And then we have just raw services that are running directly on these compute sleds, talking directly on our underlay networks. And all this traffic is going through these sidecars. And moreover, we have some fairly complex protocols that are running on the switches themselves, things like BGP to enable routing to take place between ourselves and the upstream networks. There's ARP to make sure that you can just do like basic address resolution, NDP, things like that. We support bidirectional forwarding detection to have reliability in static routing environments. So there's a lot of complexity in what's going on inside of these switches. And so understanding like, and because we write the code that's in the data plane for these switches, like understanding what's happening on a packet by packet basis inside these switches is extremely important. And that is where a technology like DTrace can really shine. But taking a step back, before I said we create these environments out of virtual machines, and in the real rack, this is like a big, ASIC from Intel. ASIC means application specific integrated circuit. It's a fancy name for processor, but this is a network processor. And so how do we represent this in a virtual environment? And so what we do is we basically leverage our homegrown hypervisor called Propolis that we've created at Oxide. I say we, I've had very little to do with Propolis, but like, the group we. But I did build a network processor emulator inside of Propolis. And we call this soft NPU or software-based network processing unit. And what this emulated device allows us to do is we can compile P4 code into a shared library object and then dynamically load that shared library object into this soft NPU device. And it has the exact same semantics of our P4 code that we run on our real switches on the Tofino ASIC, but we can run it in this environment. And what we can do because of that, and we're just running this on like regular x86 boxes inside the hypervisor on the the CPU that the hypervisor is running on, that means we have the opportunity to do DTrace things. And taking like even kind of peeling back the onion one more layer here, we've also developed our own P4 compiler at Oxide, which is key to allowing us to do this. And so when we take this P4 code that represents like how our data plane functions, we compile that code using our own compiler that can then inject DTrace probes into the soft NPU version of that code. So not the code that's getting compiled for the Tofino, but the code that's getting compiled for the development environments that we have. And so what this looks like when it all comes together is we have a hypervisor that has this emulated soft NPU device running on it that is able to load and execute our P4 code. Above that hypervisor, we have a host operating system, which is Lumos for us. That's our host operating system for the entire rack. Inside of the kernel of that operating system, there's a little UART management interface to be able to manage this soft NPU device to do things like load table entries, manage, like bring the ASIC out of reset and initialize it, and things like that. And then there's also a bunch of virtio.net interfaces that allow traffic to be able to go through this soft NPU ASIC all the way up to the host operating system that's attached to it, which is important for doing things like implementing protocols like BGP that are not necessarily implemented on the ASIC itself, but rely on packet transit all the way up to the like host that is attached to the switch through PCI Express. We have enough fidelity here to be able to kind of trick our stack into believing a Tofino is underneath us. We can run our Tofino operating system drivers. We can run our full driver stack. And so what that means is in the host OS user space, we're actually running our Oxide switch stack, our Oxide control plane, and we're able to test our software end to end. And also, critically, when our data plane is misbehaving and we have bugs in our P4 code, we can use DTrace to be able to look on a packet by packet basis what's happening inside this network and catching erroneous behaviors that might completely tank what's going on inside the network. And so the ultimate question that we're trying to answer with DTrace in here is, this is from a slide that conference talk that I gave a while ago of, you often have a real bad day where you have packets that are coming into one of your network devices, one of your ASICs, and then it's just exploding inside the ASIC and not coming out the other side. And so what we're trying to do is understand why. And especially as we're rapidly developing this code base, we're going to introduce bugs into our own code base. And, obviously we catch those hopefully before they go out to production. But these DTrace-based tools that we've built into the compiler allow us to function more effectively as a team and to be able to look at what the execution state of these P4 pipelines are as packets are running through them. And I can't emphasize enough how much of a huge benefit this has been for development of, just being able to look at the system as code pipelines are executing and see what that looks like on a packet by packet basis. But instead of talking about it, I'm going to actually show this to you in a live demo now. So I said before that this web interface here that I'm sitting here and able to refresh and things like this is actually running in one of our virtual environments. So let's go ahead, and these packets are going through our emulated switch to be able to serve this web interface. So let's go take a look with DTrace at what this packet processing pipeline looks like. So with that, I am going to present something else. Window. Okay. All right. So do we see a terminal?
We see it.
Okay, cool. So what's that?
Looks good.
Okay. So the first thing that I'm going to show is just a little bit of P4 code. And so the code that we're looking at right now is the actual code that was actually facilitating the web interface that you just looked at. So packets were actually running through this code. And so P4 is a little bit like, for people who are old enough to remember, like Pascal. It feels a lot like Pascal, maybe Delphi for a slightly younger generation. But I guess I'm still dating myself. But so we have, everything is organized around controls. And so when we look at any P4 pipeline code, we have, yes, begin procedure. We have something like this, which is a signature for the pipeline of how this program is structured. For this, we have the soft NPU pipeline structure, which has a parser, an ingress processor, and an egress processor. If we want to look at the parser, it's fairly straightforward. We're just taking a packet in, and we have an out parameter going to our Pascal here, where we're populating this headers T structure And then we have an in-out parameter where we, it's like a mutable pointer essentially for metadata that we can associate with this packet. And then we just basically go through a state machine of parsing this packet, trying to figure out what it is, if it's IPv4, IPv6. If it's nothing that we can recognize, then we're going to reject this packet, right? And anytime you reject the packet, you should be thinking, this is code that is going to cause somebody a bad day at some point. And so we want to be able to observe this type of thing. And getting into so once we get past the parser, if everything goes smoothly, then we get to like a transition accept point in this parser tree, and then we can go into the actual processing of the packet itself. And here, P4 is actually a very simple language, if not Pascal-like. That it's just basically oriented around these controls with apply box that you can stick some instructions in to look at headers inside of packets, modify headers and packets, do table lookups like single cycle table lookups to figure out what you want to do with a particular packet. And so it's pretty straightforward, but also lots of opportunities to like drop packets when we're talking about 4 billion of these per second going through a 20-stage pipeline in an ASIC. There's a lot of opportunities to actually really screw things up. And so when things aren't going our way and we have like a complicated bit of P4 code, with I think our P4 code occupies most of the 20 stages of the Tofino, that's going through a set of like 20 or 30 different controls on the way through it with a whole big pile of instructions. We want to understand like what's going on with that. And so this brings us to DTrace. So when I compile this code, if I do X4C, which is the name of our compiler, and I do P4 sidecar light.p4, this is going to compile code. Just to show you there's nothing up my sleeve. If I change this headers to like, muffins T and do something like this, right? We're actually doing compilation here. We get, real compilation errors. So when we compile this code, and then we can open out.rs. So from this 489 lines of P4 code, well, it's including other files, so there's a little bit more than that. We're getting approximately 8,000 lines of Rust code. So we're essentially like transpiling this from P4 to Rust. But at the very beginning of this, one of the first things we do is we set up a USDT provider. So from the talk that Adam and Ben had earlier, we are setting up all of the different things that we can say about how this pipeline is actually functioning. So we have things like parser accepted, parser transition, parser dropped. And if we just go look for like one of these packet or one of these macros that are used for the USDT probes, then we can see how the compiler is just kind of like sprinkling them in all over the place inside of this compiled code to give you kind of like a picture of what's going on with this code. And so if we want to look at what this actually looks like in real life, I know Dave was talking about collecting DTrace probes that are shipped with projects. So this, if we just do git remote -v, so this is just the Oxide computer P4 repository, and we have a DTrace folder in there. Adam's presentation earlier made me feel like I know nothing about DTrace, so my DTrace scripts are very pedestrian, but they get a lot of mileage out of them. And so one of the things that we're going to look at first is this DTrace -s soft NPU stats, and then we need to do God mode for this. I can't type. And so this takes about 5 seconds to kick in, but when we do this, we're going to get a picture kind of like statistically of what our P4 program is looking like. And when we're working on our network stack, this is one of the first things that we look at, just to get like a high level overview of like, okay, like I've had, if I want to look at like the router for index function has kicked over 5 times since the last time I ran this probe. Or if I'm looking for like a table miss on the local IPv4, I've had like 13 of those. And like I can see like if something's going wrong, if one of these starts to tick up, then like I know kind of broadly where to look at in the program, and this is extremely useful. Like when we're adding new protocols, I know Nils, one of our engineers that works on our switch stack, was adding support for LLDP a little while ago in our stack. And just, every time we add a new protocol, that's adding new parser functions, new processing functions. And this turns out to be really useful for just shining a light on where things are potentially getting dropped, because we usually don't see drops in the test environment. Now, when you hook up to a real network that is just flinging all kinds of packets at the rack, then yes, you're going to see lots of drops because there's lots of packets we just purposely don't handle. But this is just a high level view. And so if we want to get a more detailed view in here, we can do, let's see here, DTrace, DTrace, and we're going to do -exter size equals 4K to make sure we have enough string buffer, -s soft MPU monitor, and then we're going to do demangle because this is going to have some Rust stuff in it. But when I run this is going to kick back a lot because it's actually going to be running over every single packet. There are some, in this DTrace script, there are some ways to discriminate on particular packet streams, but what we're seeing here is actually every single packet that is going through the pipeline. So I'm starting to look at, so here's what the structure of this packet looks like. So I have the Ethernet destination and source and the ether type. This little null here means there's no sidecar header, no VLAN header, no IPv4 header, but there was an IPv6 header in here. It has the IPv6 information associated with it. This was a TCP packet. I have all the information about the TCP, like the checksum values, ACK numbers, sequence numbers, all of that. And then below that, I have the entire path of what was executed inside of the P4 program. And so this starts to become extremely useful of when we're going back to I'm having a bad day, my packets are just getting gobbled up by this particular ASIC. What the fuck is happening to them? This is what really helps us to get toward the answer to this question. And it even goes into when we're looking at exact match tables, what were we looking for? How, why are we missing on this particular key? What mismatches were happening? And this makes it so quick and easy to debug issues in the P4 code. And one of the really cool things, and kind of the realization of a personal dream for me, is that today we're doing this in our development environments, but soon we're going to be able to do this on our actual ASICs. And so people probably know that the Tofino compiler was recently open sourced, which will allow us to start to bring some of this tooling to the Tofino. And we're also building the next generation of our platform on the Excite X2 ASIC, which is a very, very flexible ASIC, which will allow us to bring a lot more of this type of tooling. So not just for us, but also for operators that are having these really bad days, these multi-million-dollar outages, and trying to trace down what the hell is going on inside of the network and why are all these packets being dropped, being able to leverage these tools to do this kind of sleuthing inside of the network. And so with that, I believe that is my presentation, and happy to take any questions.
Right, this is awesome. And I mean, I had said this in the chat. I don't think it's much of an exaggeration that part of the reason we did our own P4 compiler on soft NPU is to give yourself an instrumentable substrate on which we could develop P4 and understand it. So we weren't having to understand it exclusively on the silicon. Is that?
Yeah, I mean, that was one of the big reasons. The very original reason was we were building out our infrastructure, our software infrastructure for networking before we had a full rack. We had soft NPU working before we had a rack with 2 sidecars in it, acting both as sidecars. And so doing a lot of that initial development work, we initially tried to use the simulator that we got from Intel for the Tofino, but that's a cycle accurate simulator that actually represents the real hardware. So once you get past a couple hundred packets per second, latencies start to spike into hundreds of milliseconds, and then that becomes useless as a rack scale emulation tool. And so the original motivation was to be able to bring our whole network stack together end to end with all the routing protocols, realistic traffic. So soft NPU can handle a gigabit per port pretty fine. I've pushed it up to 10 gigabit aggregate throughput going through soft NPU on an AMD EPYC with no problem. And so we can represent a wide variety of rack topologies and connections with upstream networks using this tool. And so it's just a whole system scale development tool.
And then someone you've never met before in the audience named Kevin is asking you the question, what do folks possibly do today when they have a production network issue without this kind of instrumentation?
Go through a lot of pain, talk to your vendors. Hopefully they'll give you a firmware fix that you have no idea whether or not it's going to fix the problem. You lose sleep for the next year thinking about when this is going to happen next time. There's no real good solution. I mean, I think when we're able to come to market, like with the X2 and some of the advanced features that we're going to be able to bring to Defino now that the compiler is open source, like a lot of that is going to look like living in the dark ages. Like we're going to be able to empower operators to actually understand their networks instead of just kind of deal with the lack of visibility that they have into the executional semantics of the ASICs that they have today. So that's a big reason why I came to Oxide, was I was tired of that. And I saw at Oxide that I could build the world that I want to live in for networking, and that's what we're doing.
That is awesome. Great work, Ryan. Very exciting stuff. As Ryan foreshadowed, stay tuned to what we're doing with X2. We're really excited about that. Very flexible piece of silicon. And you can see some really interesting stuff come out of that. All building on the now we've got our own P4 compiler, building on all these other elements. So really great stuff. All right, you should go straight into Robert. Adam's going to kick us off onto another channel.
Yep.
Dwarves and elves. Is it Robert right? Is the caller there? Oh.
Hey, Kevin, when you see Robert pop up, can you please let him in?
Oh, I just wanted to join you for 1 second, Robert. So this is our colleague, Robert Pustaki. I feel, Robert, like you have a long history of like on the fly putting together dtrace.conf presentations. I don't know if this is accurate, but I think you've been presenting at dtrace.conf as long as there's been dtrace.conf. And
nor in 2008.
Oh, yeah, okay, fair enough. Okay, good. Right, when you were like actually a student in school.
In his defense,
Yeah. I mean,
I wasn't
right,
there.
Right. But I'm looking forward to get another like on the fly put together presentation for dtrace.conf, a longtime contributor.
Yeah, I mean, so I think where Rye gave us a lot of beautiful things that exist, and his was, all no slides, all demos, which is great. We're going to go to a world, talk about worlds that could exist or might exist, and aren't that hard to get to. So for this to kind of talk about, we're going to first talk about elves. So we're going to ignore the questions of what language we're speaking here, but really the thing about DTrace is built around Elf, right? Everything that it reads, everything that it scans are Elf objects here and on most platforms. None of us support A.out, and the one exception would be Mac OS, which does scan non-Elf objects, but for as far as we are concerned, that kind of doesn't exist. Why does this matter? Like FBT and PID, the way we get all those names that we scan, the symbol table. CTF is, stashed also in an Elf section. Ben and Adam were talking about USDT, and what did we do? We stashed more data in an Elf section. Okay, so Elf is here. That's great. So let's talk about some things that people like to do. So like these are two examples of code, one in a language that you probably dislike and one in a language that you like. One, they're on the right, you have Dropshot, and the left you have there. DTrace is great. You can usually get function entry, get some arguments, but there's all these things in between. We have all these pesky local variables, all these things there. So also, if your language decides that, doesn't love the System 5 ABI, you're not getting your arguments. Args is kind of useless. So this a while back, over 4 years ago, there's a little prototype we have of using locals. Same way you have foo points to, or this self, the different clause local variables. Conveniently, everything proceeding in arrows reserved by dtrace as a keyword, so you can't use it. This also got us out of when we first had the bad idea of using locals as an array. But what this meant is that you could actually put a paid provider probe pretty much anywhere in there, and you could get access to your variables, as long as you didn't care about the type. But you got a U64. That's pretty good. And what is this? Okay, what ended up happening is that this was actually all using Dwarf under the hood. This is where the dwarves come in. And it turns out that we had accidentally built a small compiler. Dwarf, is a wonderful and terrible format at the same time that encodes all of this information in its own effectively virtual machine that basically looks very complex, but in practice, actually, you only really need like 2 or 3 things that gets you 95% of what you need, which is basically dereference this register, which surprisingly sounds like the word uregs, and then, copy this thing in, which, you can just use copy into dereference. So there you go. That gives you a whole bunch. But what this ended up doing was saying, what if we could go and basically take the existing D that we had and basically just, insert a little bit of, magic in the compiler and basically transform one bit of D into another bit of D. So instead of having local to foo, you would replace that with, copy in uregs of da-da-da-da. Okay, so this is here. There's a prototype of this. It's great. So that wasn't really great because it's unfinished and sits abandoned from 2020. But let's kind of go into what other things, what's here, what other things. One of the problems is Dwarf itself. You can probably virtually raise your hand if you actually, on your production systems, have binaries with Dwarf. I'm guessing that most folks in the chat right now would say they don't. Even if you had it, it's also not included in core dumps. There's a whole bunch of ways that you can actually get access to that stuff through third-party things. But if you've ever tried to enable the Debian or Ubuntu source repositories to download things, then you have your own mental scars there. So there's this kind of fundamental challenge here. There's some things we've done to enable this. Actually, ironically, back in the day, you can actually separate all this Dwarf into a separate file. And actually for LX, the LX zone, we actually added a whole bunch of work to actually follow all that information. So you could find a symbol table because everyone decided that your symbol table is too big for you. And, what's the use there? So let's talk about some other things that if you basically take what's here and use some of the Dwarf information, there's actually a lot you can do. And other things have already done this. It's just a matter of actually putting these things together. So for example, if you run stack or ustack, you get all these kind of nice symbols and frames. But what if you could actually just, this is really this set of files at these line numbers. So you can actually just go with a fairly straightforward transformation, look up an address and transform it into source line information if you have this Dwarf here. Just like in the last case, everything we did there was basically looking at and using Dwarf at compile time. Here, this is all just using Dwarf at translation time. The same thing is kind of true with inline functions. There's a whole bunch of Dwarf information about where these inline functions are. When you use stack or ustack, effectively the kernel is doing is going to walk the frame pointer, basically give you a whole bunch of return addresses, and just pass down a whole bunch of addresses to userland. Nowhere until you get to userland, that's the first point that symbols actually show up. And that's where we'll start, walking symbol tables and looking at all these other things to try and understand that humans understand. But compilers, especially Rust C and others, really love to inline functions. So if you actually have the Dwarf sitting there, you can actually augment that ustack and stack information with all of this information. If you've used humility, I think, Brian, you added that in humility at one point, or someone did, walking all the inline functions in Dwarf. And so this is here. It's actually The good news, you don't even have to change anything about how you instrument it, how you do what you do in probe context. It's literally all just post-processing in libdtrace or the moral equivalent. But we can actually do something even crazier. So, one of the things is like, hey, if you have ever actually tried, I guess, kind of show of hands, who in the room has actually gone and used the instruction offset to the PID provider and figured out what offset to use in a way that didn't feel gross? Anyone?
We did feel gross. Come on, what kind of qualifiers are you putting on here? Yeah,
Okay.
I felt fine.
Pragmatic.
I felt good.
Pragmatic. Good. Okay.
Pragmatic. It felt like it had utility.
Yeah. No, but so one way to phrase it, what if you could actually phrase that a different way? Especially because, when you're working here, you're saying, okay, I've got a function. It may have been instantiated multiple times. It may actually show up more than once in my address space. Actually, the same way that people like to set a breakpoint in an IDE, like what if I could actually just set a probe point in that same way? So here you kind of have a very vague sketch of what this might look like, where you're specifying a PID that's there, the file in line, and then which instances. And then unfortunately, there's a challenge that you have. One line of code translates to unfortunately many instructions. A simple thing may not actually be that simple. Or make something get inlined in its place. So you need someone to disambiguate that. So this is kind of throwing out just one way of what that might look at. But then this kind of lets you go the other way, again, if you kind of have this information sitting around. But let's go one step further. So, there's a big gotcha here, which is type information. So for doing kernel debugging and other stuff, CTF, which is the compact C type format, has been essential, right? The fact that you can just use print, you can look at arguments, you can look at semantic members of structures is actually one of the most powerful things that DTrace gives you, is that you can look at this stuff in situ, you can create predicates around it, you can actually ask questions, such as only fire this probe when this part is true. So sometimes we've used this to look at parts of the TCP state machine, or just error counts, or you name it. Effectively, it's kind of something that ends up, there or not. If you listen to the USDT talk earlier today, we kind of had a very successful way. We found the max power way to basically get types, type structures into programs. But that's not, but why are we kind of constrained to that? And right now it's because we're kind of constrained to, we know about how to use CTF. The D language itself, inherits kind of the C type system there. But what if we could actually, what is CTF but converted Dwarf in some ways? So while there were some prototypes in the past of converting Dwarf to CTF on the fly, that only really works if your Dwarf looks like C. But if we take instead of trying to say, how can I change D the language to basically allow me to declare types that are different in every different programming language? What if we could instead just, augment print dereferencing and the kind of the arguments vectors to understand existing arguments, to understand existing types that are in there? Then that kind of gives us what you could then print, whether it's a Rust structure, an enum, something that from an entirely different language, as long as it's describable in Dwarf, then you could go there. That's true for Golang and a ton of other stuff too. So that's kind of the next kind of somewhat out there bit. The last bit really is stack unwinding. This is kind of, I'd say, Durin's bane. There's, we've delved too deep and we decided that, hey, frame pointers, get rid of them. That's just kind of the unfortunate reality. Now, this basically translates into a problem that actually looks a lot like a UStack helper. So a UStack helper basically kind of does what it says in its name. It basically is a different D program written in D that helps you that allows you to decode a stack frame and do that. So there have been UStack helpers written for Java. Dave wrote one for Node.js. I think there have been others, maybe. other new stack helpers?
Yeah, the Python,
Python.
Python node and Java at least, and I feel like PHP.
Yeah.
There's a PHP stack helper at some point.
So this problem,
They're esoteric though.
they're esoteric. There's a lot of challenges here because we have on the one hand, Dwarf, which has a very complex VM for describing all this. That ends up creating a lot of data. And there's a lot, effectively at every different instruction, based on context, there's a whole different way to unwind. That's why people like using the frame pointer, because good news, I can ignore all of that. But there's been a lot of experience on getting all of this in eBPF land and trying to use different things, whether it's using this, the exception unwinding. But there's basically a lot that one could explore, taking the whole idea of basically the fact that we can already compile some subset of Dwarf into D, transform this into a very crazy UStack helper or something else, and passing that on. So, whether compiling all that into D for all the different libraries will make sense or not, how do you do that for different programs? You have to be very targeted. But there's a lot that you can actually start to do if you kind of take a step deeper into kind of that integration. The last little bit here, I'll kind of just close on, is just symbol servers. All the part of the challenge with all this is all this works if you have Dwarf. We kind of said also no one has Dwarf. For those who have worked at Microsoft, they kind of espouse the glory of the symbol servers they have and its tight integration into Visual Studio and everything else. But trying to figure out what does that look like? How do you kind of build that into a first class way? So it's not just, it's actually in these tools and not just a object of the package manager. Or how do I point this at my development, even if this is harder to use in production, how can I use it in development to help speed up? Because there's still just as much DTrace in development as there is in production. So really, that's kind of all I got. This is kind of a bunch of, things that could be or might be. And, I think the thing I want to call is that none of this is actually all that complicated. I think there's a lot of things where they've been, things have been kind of like, you kind of see it's like, oh, well, it's not in CTF, or it's not, it's in this other thing. It's in this other binary payload, and I just never looked at it. It's only, that's only the realm of, my source debugger. But it's actually pretty straightforward. It's just, just a bit of work to kind of get them integrated. And with there, you can do a whole lot. So there we go.
That's awesome, Robert. Very inspiring in terms of the things that we can go do. Also on the we talk about walking effectively hidden frames in the UStack helper.
Yeah.
We can also maybe demangle names. I know we piped through the C++ fill, or I piped through.
Yeah. So I mean, so like Apple does automatic demangling. I mean, I have a prototype of automatic demangling. The big question, I had some outstanding questions for folks around semantics.
Yeah.
So that's that. I mean, then the next thing is also how do I specify unmangled names in pro points? And I think that would be one of the other kind of big things, is just getting some syntax for that, because that will help people be able to phrase it in a way that they can recognize and, is somewhat usable.
Yep. And it would be great to be able to instrument when it makes sense. There's some things that are really hard to instrument function entry and return across because they're floaters and so on. But
in theory, with a source provider, you should be able to basically, because the thing is, the Dwarf can point you to where all that has been compiled into.
Right.
So there's no reason you can't say instrument these. It's just that reality might be more complex if there's like 10 different instances.
Yeah. That's great. All right. Well, thank you very much. And the locals points to prototype. We've got that's in a branch that's still.
It's in a branch. It's on the internet.
It has not joined the 2016 dtrace.conf videos in a watery grave.
Not unless GitHub has started to delete data for me secretly. But
okay.
Yeah.
So given our 4-year cadence of this conference, the 4 things, what are the chances of some of this being reality in the next?
Oh, 2028 it's going to be a big year.
Big year.
I can tell it already.
We'll give a good review at that conference.
Yeah, we'll see how much time I'm allowed to actually can make for working on this stuff. But
yes.
Yeah. Okay.
Good stuff. Yeah. And we'll switch over to Eliza.
Yeah, go for it. I'll give a quick intro to Eliza.
Hi, I'm Eliza.
Hi, this is Eliza. Eliza Weiss
Hi.
at Oxide. Very excited to have Eliza here. I think we're talking about Tokyo maintainers that have joined us at Oxide. I think they've been calling you out, Eliza.
Yeah.
Take it away.
Okay, so this is title here is DTracing Two Great Tastes Better Together. And I have a quick disclaimer, which is that I have no idea what I'm doing. I am not a DTrace expert. I'm going to get a lot of terminology wrong. Also, I made these slides and put this talk together in about the last hour. So, good luck me. This is purely in a response to sort of some of the chat conversations that came up during some of the earlier talks. So I hope this makes sense. And if it doesn't, please ask questions. And if I use the wrong word, I'm just a dog. I have no idea what I'm doing. So this is a slide. This is kind of an Eliza deep cut. Some of you may remember this slide from a RustConf talk that I gave about 5 years ago. And this is the slide from a talk that I gave on the tracing crate, which is not a logging library, as it says on the slide. And we're going to actually talk about some of this background. So in 2019, I was working at a company called Buoyant. We were writing a application layer network proxy in Rust. And we were very early adopters of Rust's async ecosystem. In particular, we actually started using Rust async like long before async await syntax was something that existed. We also sort of funded, and I worked pretty closely with some of the original Tokyo developers, including Carl Lerka. And we were like in this stuff when it was pretty raw. We were writing a proxy. We wanted to be able to handle a lot of concurrent connections. So obviously we need some kind of asynchronous execution. We decided to build on top of Tokyo, Hyper, etc. And this was all pretty nice, but the debugging experience, and we're using the Rust log crate at the time, was really bad. Like really, really bad. We're going to look at some examples of what I'm talking about. Here's some logs. These are in a synchronous system. And so we've got like a log record here that says, oh, I've accepted a connection from this IP. I have another log from the HTTP server that says, I've received some request. Oh, there's a warning. It says there are invalid request headers. Now we're closing the connection. If this is a synchronous, single-threaded system, this makes sense, right? You can infer based on like, these are in order. There's some like causal flow of events represented by these logs. You accepted this connection from this IP. Then because this is a synchronous single-threaded system, the request that was received was from that IP. The invalid request headers must have been related to that request. Oh, and so we gave up and closed the connection. Great, that's normal, right? That makes sense. In an asynchronous concurrent system, the same logs are garbage. Right? So like we see, I've accepted a connection from some IP. Oh, I'm closing the connection. Oh, I've received a request. Oh, I've accepted a different connection from another IP. Oh, I've received another request. I've received another connection. Oh, I've invalid request headers. This is nonsense. This is really bad. And this is what the logs in our proxy looked like when we were using the Rust log crate. And as you can kind of tell, it's impossible to know what's happening. This is like, how do you people live like this kind of stuff? So that's not very good. We solved this problem by adding context to these events. Now, this text got a lot smaller. I'm sorry about that. There's nothing I can do. And I pulled this from an ancient blog post I wrote about this library. But here, we can now see that each of these log messages has some context added to it. We have a client address that's attached to all of these as a part of a server context. Then we see a request context when we accept a request on that connection, and it's got the path and so on. And so that means when we see this like this warning down here that says, oh, like there were invalid request headers, it actually says which request, which client that event refers to. And similarly, we can see when we close that connection, it's the same one. So it's like possible to understand this. And at Buoyant, we had sort of come up with an ad hoc homemade version of this type of thing, which worked in our code, right? In our proxy code base, we were using this, but we want to get this information out of Rust libraries like Tokyo and Hyper. We want to be able to see things like, you know, in this async world where all of this stuff is happening concurrently and it's all happening at the same time, and we have tasks that are executing and suspending, and then we're running other tasks, and all of this stuff is just flying around. We want to be able to trace these contexts not just through our code, but through the runtime, in this case, Tokyo, through the HTTP implementation, the HTTP2 implementation, and so on. We wanted to be able to put the same logging context that we had just sort of come up with this janky like hash map in thread local storage thing. And we wanted to be able to put that into libraries that other people actually wanted to use. And this is a big theme in the story of this project, is this idea of like, we want to put this in libraries that other people also want to use, and you can't make them mad, right? Like if you're going to put your shitty logging library into like Rust's async runtime, it's very easy to make a lot of people upset if they don't like your shitty logging library. And because of that, we arrive at a pretty similar set of values to DTrace, which we'll talk about a bit later, even though we've gotten there through a very different path, and we've ended up with, in some ways, a very similar system, and in other ways, a very different one. So the tracing crate is what I'm talking about. And here's some stuff about it. It is maintained by the Tokyo project, right? So it's Tokyo RS/tracing on GitHub. It is an application layer structured diagnostics library. That's the fancy language that I made up because I didn't want to say the log word anymore. And it has a data model that's sort of inspired by distributed tracing systems like OpenTelemetry, Zipkin, Jaeger, et cetera, which we saw a talk about this morning. And in those systems, we have a notion of a first-class context, which is what we call generally a span. And our terminology is sort of drawn from this world of distributed tracing, although primarily we are concerned with in-process tracing. We're concerned with an individual program, and we've gotten here from sort of the recognition that in these asynchronous systems, a single process behaves very similarly to a distributed system, right? Concurrency is kind of just concurrency. The primitives are different. Like, okay, you have one way of doing a compare and swap operation in a database. You have a different way of doing it on an atomic, right? But the same principles are there. You have actors that are, you know, exchanging messages and interacting with each other. You have contexts that are moving between these actors. And, you know, all of this stuff is kind of the same. So these ideas from the world of distributed tracing apply just as well to these async Rust systems. And then finally, this library is really a facade layer that you can plug modular subscribers into that consume diagnostic data in different ways. And this is, you know, part of this broader overarching goal of like, we have to be able to put this in Tokyo without making anyone mad, is that if everyone has opinions on here's how I want to consume my diagnostic data, we need to be able to allow them to bring, here's what I want to get out of it. I want a text-based log. I want JSON logs. I want OpenTelemetry, whatever. And unfortunately, that interface that we've come up with does not work super well for DTrace. We're going to see why in a little bit, but that's sort of the key last point here, is that this library is just a facade that provides the user interface for instrumentation. Like in my program, I want to emit some event. I want to record something happened. And the interface for how you would subscribe to those events in the same Rust process, and none of the opinions for how data should actually be collected, formatted, displayed, filtered, etc. Now, a whirlwind tour of tracing's core concepts, some Rust code. We have an event. We have this macro called event that records an event. Events represent something that happened at a fixed point in time and has some data associated with it. So tracing has a notion of levels. This isn't super important. And we have, this one is just a textual message, hello world. And then we have some fancier events, right? They can have key value data attached to them. So here we've got an event that records two key value pairs, question, which is the value of this variable question, which is the string life, universe, and everything. And then it records a different field, answer, which has the value 42. And we have a fairly simple data model of these can basically be Rust primitive types or anything that can be debug printed. In the glorious future, this may be substantially fancier, and we'll be able to do things like serialize user-defined types in a more structured way. But that's something that I started building about 4 years ago and then gave up on because I started working at Oxide, where we weren't actually using this stuff. And this ends up being kind of a weird whirlwind tour of my career, something I meant to mention earlier. But, you know, we have these events, they represent single points in time, and they have some arbitrary data, which could be a string or some other stuff attached to them, some key value pairs. We can have a bunch of key value pairs. These are just some examples. And then we have a notion of spans. And so we have this span macro, which is sort of like the event macro, except instead of just being something that records an event at a point of time, this represents some period of time where you were in some context or some operation was ongoing. And the way we model this in Rust is we have this span macro. There's an info span. You can also have debug span, trace span, error span, etc. And that's just how they interact with the filtering system in tracing, which is kind of drawn from the like more classical logging terminology of like you have verbosity levels. And when you create a span, it's not just a function-like macro that doesn't do anything. It actually gives you back something. It gives you back this span object, and that represents I'm now in this context. When you have that span, that's something that you can call a method called enter or entered on. There's both. They do slightly different things. That's not germane to this talk. And that signals to the tracing subscriber, I'm now inside of this context. And so in this example here, we've got these braces that create a scope. And we have two events in this example code. And inside of this scope, we create and enter the span, my span. That gives us back an RAII guard, that as long as we're holding that on the stack, we are executing inside of this span. When we drop the guard, we exit the span. So you see, we've got these two events with the field inside span. One of them is true, the other is false. That is how tracing will interpret these events. And spans are sort of a stackful concept, right? Like as you enter a stack frame, you might enter a span inside that stack frame. You might call another function that enters a span. That span is inside of the parent span that was already on the stack, and so on. And this is also how we sort of model asynchronous execution, where in Rust you have a future that can be polled, and then it yields because it has no work to do yet. It's waiting for some IO event to complete, and then you poll some other future. But that first future still exists. It's just suspended. So for this reason, tracing distinguishes between creating and closing a span, right? Saying, I have this span with this name and this data associated with it. That's one thing. Entering the span, saying, on this thread, I am currently in the context of this span, and exiting the span, saying, I'm no longer currently executing in that context. And then dropping the span, saying, okay, this thing no longer exists, are separate actions. And once a span has been created, it can be entered any number of times. And that's how we would model attaching a span to a future that might be polled a bunch of times, do work in the context represented by that future only while we are inside of a poll, but the future still exists, right? And this is very interesting because it allows us to model you're not always in that context just because it exists, but also we can look at really two sort of different periods of time. The period of time for which this operation existed and the period of time when we were actually executing in service of it. So this is interesting, for example, if you have a span that represents an HTTP request, right? Because the time between creating and closing the span represents the total lifetime from the perspective of the client that it took for you to service that request. Whereas the period of time for which you were entering that span represents the amount of time that you were actively working on the request. You can subtract one from the other, get the time that that request was in the system idle, waiting to be serviced. And all of these are very interesting to be able to measure and talk about and to be able to distinguish between. So our spans are first class objects. This is a key differentiation between tracing and the slog trait in Rust, which is also a structured logging library, where you have a notion of loggers that can attach key value pairs to log records. But those are just extra key value pairs that are sort of slammed onto the back of a log record. That's not a first class object in the data model that the entity that's actually consuming the diagnostics gets to reason about. It certainly does not have a known lifetime, and there are not events recorded when one is created or dropped. And it also doesn't really have this concept of being entered or exited. It's just a thing that you pass around, and sometimes you log records that append all of the key value pairs in that context. So tracing's contexts are very rich, specifically because supporting async programs was a priority, and being able to reason about things like futures that represent an HTTP request that might suspend and resume any number of times. We also have this instrument macro that you can just sort of slam on top of a function because you want to have a span. And so in this case, this will include all of the arguments to the function as fields on the span. So we have this connect function, and it takes a socket address. So this will generate a span called connect with this socket address. And so if we then create this debug event connecting, we don't have to say which address we're connecting to because it's already there in the context, because this function has this instrument macro. And there's a bunch of fancy things that people, mostly not myself, have added to this instrument macro. So you can have it, if this function returns okay, it can log that. If it returns an error, you can emit an event that says this returned an error. You can do all kinds of stuff. But this is sort of the basic case, and a detailed tutorial on how do I actually use this library is not really the point of this talk. So this is just sort of a whirlwind tour of what are the core concepts in this thing. Okay, so why are we talking about this thing at dtrace.conf? This isn't DTrace. You may have noticed this. Well, here's one reason. I did not put this picture in to stroke my own ego, but this is the reverse dependencies of tracing on crates.io. This image actually terrifies me, by the way. This is this doesn't make me feel good. I'm not proud of this. This is horrifying. That's a lot of reverse dependencies, 8,984 crates. And these are some of the big ones: Tokyo, Hyper, Tokyo Util, H2, which is the HTTP implementation used by Hyper. A lot of Rust software uses these libraries. These are some big download numbers too. This keeps me up at night. I'm terrified of this image, but maybe these crates that most Rust applications, certainly all of the ones that are doing HTTP serving in the year 2024, depend on these libraries. And maybe you would like a DTrace probe for all of the tracing events that are already in those libraries. That would be nice. I would like that. So, imagine you could have one macro in a Rust program that generates a USDT probe. It emits a textual log. It emits a JSON log. All of this stuff is also potentially part of a distributed trace if you're using OpenTelemetry, JagerZip, and what have you. And all of this can be turned on or off at runtime depending on your needs. You can decide, oh, I want to enable these DTrace probes. I want these different log levels to be enabled, or I don't want that. And critically, again, one of the big design goals for tracing the crate, not the abstract concept, was that it would go in all of these core libraries like Hyper, Tokyo, etc. So we won, right? And you would be able to, have all of this instrumentation be there, and the consumer would decide whether they actually care about that. And that's where we get to this point. Tracing the crate, again, not the abstract concept, and DTrace have some pretty similar values. The way that you put something in the core libraries that people who aren't you depend on without making them mad is by not having any impact on their performance unless they're trying to use the thing you put in there, right? So minimize disabled probe effects. We arrived at that kind of from this question of how do I get away with putting this in Hyper? Well, we have to minimize disabled probe effects. Secondarily, we don't want to lie. We don't want to drop data and not say that we did that. That's kind of a big deal. That informs some design decisions that aren't, again, really all that germane to this talk. And then finally, we also want to reduce the probe effect for enabled probes. But that's way less important than disabled probes, right? If somebody has asked for a piece of information, they're maybe willing to pay some costs to record that information. Obviously, you cannot record anything for free. But if they haven't asked for it, they're going to get really mad at me specifically if my library is making hyperslow, right? So trying to avoid people getting mad at me, we have arrived at these very, very similar values to DTrace. And oh, look, hey, isn't that familiar, right? We also have a core concept of, is this enabled? I have some static metadata about it. This is a method on the tracing subscriber trait, which is how you would integrate a particular way of collecting information with the program. We have this enabled method, and before you record something, you ask if it's enabled. And if you read these docs, which I realize I've just flashed on the screen for a minute, by default, it's assumed that the filter only needs to be evaluated once for each call site. So it's called by this other method called register call site when each call site is registered. This is used to determine if the subscriber is always interested or never interested in that call site. This is intended as an optimization so that expensive filters, such as those involving string search, need not be reevaluated. Now, this is downstream of, in Rust, the log crate has this end logger library built on top of it that has a way of filtering events by Rust module paths, where you say, like, I want the foo module at info and the bar module at trace, and then you get like a bunch of logs when you run your program. And when you hit the logging macros from the log crate, what you actually do is a string comparison on the module path. And you do that every time you hit that macro, which means that if you never said I wanted any logs from Hyper, the logging macros in Hyper still cost you a string comparison every single time you hit one of those macros in the source of the library that you're calling into. That's a disabled probe effect, and it's actually pretty bad. Now the log crate ecosystem has a way to statically say, I would like to not compile any of that into my binary at all, which is great, because now it's not in your binary at all, which means that you can never have it. So neither of those is all that satisfactory. So instead, what we've done in tracing is we have made this assumption that most of the time, if I ask the subscriber, do you want this? It will say, no, I don't want it, or yes, I do want it. And it will always say that for the same static metadata that identifies a particular event at a particular line number in some file in some module, right? And if that is not the case, it can explicitly say, actually, ask me again, because whether or not I want this depends on some runtime context that I can't give you the answer to. And that's a big part of how we minimized probe effects in tracing. And this feels a little bit familiar. Now, it is different from the way that enabling and disabling DTrace probes works, but it's relatively similar if you consider that the tracing crate and DTrace have radically different design constraints. Similar values, different design constraints. So our design constraints is, our being tracing, is that we would like this to just be plain old normal Rust code. This is just a library that you depend on. It does not do any dynamic rewriting of your binary. It does not get help from the kernel. And all of the subscribers and all of the filtering is occurring in your process in normal Rust code. So, and when I say normal Rust code, you see the screenshot here, which is full of just some of the least normal Rust code that anyone has ever seen. You're not expected to understand this. This isn't on the test. Don't actually try to read this. It's grody as hell. This is macro-generated code. But what it's doing is every time you say tracing info or whatever, you generate a static. And that static has a bunch of metadata, such as the file and line number. And then it has this thing, which is called a call site, which in practice is essentially an atomic. And that's where we cache the value of, is this enabled or not? And because we have a separate static for each of these call sites that represents a tracing spanner event, we can just load the value of that static. Is this enabled? Okay, great. I'm going to do all of the expensive stuff to do some string formatting and print it. Or, oh, it's not enabled. I'm just going to keep going. That is not free. That's not a NOP, but it is one branch, which is pretty good. That's about as good as you can get without doing dynamic program text rewriting, right? This is close to the theoretical maximum. Certainly in x86, I have both benchmarks and I've looked at assembly output, that it's basically a probe cost of one instruction. And it's not terrible. It's about as good as you can get in normal Rust code that's generated by a Grody macro. There is a cost to doing this the first time because that is still occurring at runtime, right? You still have to do the string matching, but you only do it once. As a sidebar, that actually was a huge issue for Rust C, because the performance picture that I sort of had in mind when I was developing this library was, okay, your program is a long-running server, some other like application that runs for a long time. It's going to see every event at least twice. So the cost of amortizing, like doing that string comparison once over the entire rest of the lifetime of the software is not that bad. Rust C runs to completion. It doesn't take that long to do it, contrary to what you might have heard. You know, it's certainly not a long-lived server that is responding to requests for an indefinite period of time. It actually has a lot of logs or tracing events in it that only ever happen once in the lifetime of the whole process. And so my like, oh, this is all very cheap was not the case for the like CLI program that runs to completion. But in the case of your long-lived servers and networked applications where you're, you know, doing the same code path any number of times, the cost of the one string comparison is amortized over every other time where you get to skip that thing. This is not as good as what you can do with the USDT probe. It's substantially more expensive, but it's about as good as we could get without, you know, doing things that were not, that were not portable, that could not, for instance, be compiled to WASM, or that required platform-specific assembly that I didn't feel comfortable writing, or required help from the kernel. So similar values, radically different design constraints in many cases. And then finally, we also have this design constraint of we care about this concept of context spans being first class. We would like to be able to glue these things onto a distributed tracing system and go from the sort of small scale of I'm looking at what's happening in the process to I'm looking at how that process is interacting with the outside world and then back down again. So tracing's model for integration is this subscriber trait, where we expect different ways of consuming diagnostic events to implement this trait that has a bunch of methods that get called synchronously when something happens. Either because you want to record a span, record an event, enter a span, exit a span, or you're done with the span and you want to say this span is over. And these are just like normal synchronous Rust methods that get called on an implementation of this trait, which can be set either globally or on a per thread basis as the subscriber for the program. And, you know, that interface works pretty well for stuff like I want to emit JSON, or I want to emit Bunyan, or I want to emit some other format, or I want to ship all of my logs to some log aggregator, or no, I just want to log human readable strings to standard out, or I want to write things to a file, or what have you. There isn't a nice way to tie DTrace into the model of a thing that implements this trait, because we have this notion of there's some code that we're situating at the individual event in the instrumented program, these statics and stuff. But by the time that it gets to this subscriber trait, we're just giving you a pointer to that. We're saying, here's the metadata. Do you want this thing? Okay, if you want this thing, here's some dynamic runtime data for that thing that you can now decide what to do with. So a subscriber that is translating from this, like, I'm getting methods called on me model to emit that are methods that could be called with the metadata for any event in the program into DTrace probes, which are also sort of situated locally within the trace point. That doesn't work really well, because what you're going to end up with is basically you have one probe for like every tracing event, tracing the crate. You have one probe for every time a span is created. You have one probe for every time any span is exited. That's not what you want, because the whole idea of tracing system for caching filters is that it's per event, right? It's per each individual call site where you want to emit an event from. We have cached some piece of data that says whether or not you want that. That's also how USDT works. You go back and you say, I want this specific thing. Well, now we've made it so that you can't do that. We've also made it so that the structure of all of those things has to be made the same, because there's only one probe in this model. This is bad. This defeats the whole point of having DTrace, right? Like this sucks. Like, yeah, you can have one probe that's just sort of like, there was a log, but like, how are you going to consume that? I am not a DTrace expert, but to the extent that I understand like what you would want if you were writing a D script, you don't want one probe that's like every time the program ever logged anything. That's not really like, why even turn that into DTrace? You know, you just that's just a textual log. So what we could do instead is we could do what I'm calling first party integration, where the tracing macros, in addition to generating all of this other junk, also generate a USDT probe. Now, again, core value of not pissing people off. Lots of people probably don't want USDT probes. Lots of people are probably compiling for architectures and platforms where you can't have them, where there is no support. Lots of people are using the tracing crate in programs that are compiled to WebAssembly, right? That's not going to help you. But we can make this optional. And I am the maintainer of this library, and I work at Oxide now. So I can just put that in there, which is pretty cool. The integration model was very much designed around the idea that implementations of particular formats or of log aggregation systems or open telemetry or what have you would live in other crates. In the specific case of USDT probes, we can just stick them in the macro. We can have a feature flag or something to control them. So obviously you opt in and you don't get them if you don't want them, but you know, we can just generate them in our macros anyway, because it's a macro. And that allows us to have, you know, this does cut out most of the rest of the plumbing in the tracing ecosystem when you are specifically consuming these things as USDT probes. But that's good, because to be honest, as the author of this library and ecosystem, DTrace's plumbing is substantially better because it doesn't have the constraints of no help from the kernel, no dynamic binary patching. Like those give you more performant plumbing, more expressive ways to control what's being consumed. It's strictly better if you are not operating under these constraints. So why not just have both? And then the other sort of big unanswered question is, how do we model tracing's notion of spans as probes? What I imagine this would look like is we would have a probe generated for each life cycle event that can occur in a span. The span has been created, entered, exited, or closed. The new span event would include all of the key value data that particular span would record. And a very nice thing about the tracing crate that makes life much easier when integrating with USDT is that we statically declare all of the key value fields that are recorded on a span. Now, we don't currently have a way to reason about their types, because the statically declaring metadata in the tracing crate is purely in the form of, we're looking at the names of the fields, the keys that are passed to the macro, and we turn them into an array of strings. But at the very least, we can generate the structure of the keys that will be present on that span. And then the tracing subscriber gives spans IDs, which are U64s. They can be, correlated with events or with other distributed tracing spans. So you can say like this local U64 ID corresponds to this UID in OpenTelemetry or whatever. And those allow us to to make the life cycle event probes very lightweight. It's just sort of like, it was this span with this static metadata, and it's this instance of that span with this ID. You've previously gotten all of the key value pairs that it recorded, which we would probably just turn into strings because we can't reason about their types, which is sad, but it's better than nothing. But, again, I have no idea what I'm doing. I don't know if this is actually the best way to consume this data model in USDT probes. I would love input from people who actually know how to write descripts, which I really don't. This is sort of a straw man proposal. I'm this dog. Anyway, we would love your help with this. Thanks for coming to my dtrace.conf talk. Ask me questions after class.
Awesome. Eliza, thank you.
There were probably a bunch of questions in the chat that I just wasn't reading.
Let's see. Adam accusing me of suddenly carrying the name of probe effect. The single probe points are actually are not totally unvaluable.
Okay.
So that's we have had similar constructs. We've done worse, and it's been
In particular, for example, like in dynamic languages, often we had a probe that's like, you're entering this method, and then when the arguments to it is the name of the method.
Right.
And it's not great.
It's not great,
but it's better than that.
Is that right? And you can kind of use predicates
Yeah.
to avoid the stuff you're not interested, or looking for the stuff that you are interested in. So your aversion to it is not wrong. And also if it's easy, it would certainly be useful. So anyway.
It seems like we could certainly do better than something where everything is just one probe with a ton of strings.
But as Dave also observed, there can be value of actually having a choke point for everything has a different value, right? If I just want to kind of slurp up that stream, and not even from just one process, but from everything on the system.
Right.
That's potentially pretty nifty.
It does also seem like, you referenced dynamic languages. There is a slider, I think, there between instrumenting the program and instrumenting the runtime.
Yeah.
Right. And if you are getting a single event for every method call in JavaScript with the name of the JavaScript method, you could sort of argue that that's instrumentation of the JavaScript runtime and not of the program, which is also something you might want.
I also think that your proposed model for how you would have spans probes very useful.
My question for you, Brian, is there a notion of reasoning in a descript about has some previous probe occurred with some specific value? Can I say, I want all of the probes A, B, and C if a probe called some span enter occurred with some ID?
You'd instrument multiple things and then have predicates.
Yeah.
Okay.
Where this gets particularly tricky is that where we would typically do this is on a thread local variable.
Mm-hmm.
And in async Rust,
it would be an associative array that's global.
Yeah.
So
on an ID that you need to sort of const up, because getting the task ID is not a thing.
But you have the span ID.
The span,
right.
Span,
yeah. It's similar to IO probes where you have the starts.
Yes.
Which might be.
Yes.
Yeah.
Right. We just need the unique ID, but I guess you're right. It's the span.
Tracing's notion of having entered a span is thread local, but its notion of these are the spans that there are is global.
It's thread local or task?
It's thread local,
really?
Because a task would be a span, and entering if you something I didn't show in the slides, which I should have, because it's relevant to this, is that the way that you would instrument a future or an async block is you would have like a future combinator that wraps the future into a like instrumented future with a span. And when poll is called on that future, it calls like I'm entering the span. The entering of the span is on the stack for the body of the future being polled. And then when the poll call returns, you have exited the span because you've dropped that guard. And that is an inherently thread local thing because it's functionally on the stack. And that's how you would like allow a span to be attached to a future, which might then become a task. This it could have been implemented like on top of Tokyo's notion of thread local storage, but that didn't exist at the time. And also one of the other design constraints, which I didn't get into here because it didn't really feel relevant, was this thing should not require Tokyo to work. You should be able to stick it in purely synchronous like CLI tools or whatever. And so there is no first class notion of a task in tracing. It's just when you enter the span, you are in that span on the current thread, which might be associated with a future. Yeah. I will pass the mic.
Great stuff.
Thanks, y'all.
Thank you. Got one more talk before I wrap. Yeah, nobody's gonna. Oh, also. Yeah, I'm stoked. So we let me see if yeah, and actually, Taylor, let's do this. Let us let me see if Lukeman's ready to go here. Cool. There's Lukeman. Awesome. I had said this at the top that on the one hand, it's been DTrace has broadly worked. We haven't had too many bugs, but we have had some. In particular, we had a bug that goes back to the very, very beginning of DTrace. Adam had mentioned we were talking about USDT, had mentioned briefly STT, which is one of our earliest providers. And Lukeman and Kyle working together discovered kind of a gnarly issue. And what so when that dates back to DTrace's origin. So Lukeman, you wanna take it away with a tale of finding a bug in DTrace itself?
Sure, yeah. And I don't have any slides for this, so we'll just kind of be looking at maybe some code and maybe some, let me find this bug. Which window? Yeah, so this was actually discovered by my colleague Kyle, who presented earlier. And while refactoring OPTE, and specifically XDE, which is the kernel module that actually uses the Oxide packet transformation engine. And since it runs in a kernel context, we use STT probes. And as part of like refactoring and working on some other issues, Gal was running into these panics, which is just like, were very weird kind of stack traces that was like, how on earth did you kind of end up in there? And at some point realized, oh, turns out at some, maybe I don't know if there was also a tool chain upgrade involved, but at some point those probes had become tail calls instead, which was causing some havoc. And maybe to explain some of that here, actually, we'll take a look at what these STT probes end up looking like.
And Bookman, this was not, this is not panics when using DTrace. This is
No.
panics when executing the system
Yeah.
without, it's like even worse than DTrace dying when you run it. DTrace is, so yeah, just to set the context.
Like you didn't even have to, like register a particular probe or anything. It's just once it got to that point where the probe would be fired. And then after that. And to kind of explain what was going on here, so this is an example of these STT probes. In C, they end up you use these macros to generate them. And basically this kind of expands into something prefix with what? Underscore DTrace and then the name of your probe. And then it turns into a function call. So if we actually look at this, what this looks like on disk, this is something that's included on the system here. And so if we look, it's like, yeah, so we do a call. We're calling this function. And you can actually see right underneath here, there's this relocation with this, like that fake function that it had generated, because it's like, actually, I don't know where this function is. So it's all zeros. They'll get filled in at runtime. And just for reference, what a tail call version looks like is more or less the same, except instead of a call, you have a jump with nothing after it. And at runtime, once you actually load this, the kernel runtime loader will fill in, well, if it was a normal function, it would fill in that offset. But in this case, instead, it just patches all those to NOPs. And similarly for the tail call version, well, now you actually see that its fixers are right at the bottom, but before these were all just a bunch of NOPs. And so what was happening was it would get to this point, this kind of function, the probe would fire, and it would just kind of continue on to the next, like whatever could happen to be after that, which, explain the weird stack traces, because it's like, how did you end up in this function here? And now all of a sudden these invariants that should be held in a normal function call are no longer held, and then eventually it led to some kind of panic. So, I mean, the fix here is basically just patching in that ret so that it actually properly returns from this function and continues on. And you can take a look at what it looks like actually also when you register for, like, let's say I want to get the test R's one, the non-tail call version. If I disassemble an app, also this is in an MDB session, so this is kind of live, and you can see actually it patched it to a lock knob. So this will trigger, I believe, like the undefined function handler, which eventually makes its way to firing the actual probe. And, if I run this thing now, which fires the probe, hey, actually this one should have never panicked, but the tail call version similarly should now also be patched. Well, actually, this one is no longer patched because I'm no longer asking for that one. But if I look at the tail call version, now it's the one that has the lock knob. And if I run it, it's not panicking anymore, which is great. So that was kind of an interesting thing to figure out. And then the other interesting part was, this is the code wherein the kernel runtime loader, and this is actually the Spark version. And I saw this and I'm like, hey, this sounds very much like what should be happening, except it wasn't happening on the x86 handler until it got updated. But yeah, that's kind of the quick of it. Very last minute, so there's no slides or anything, but yeah.
Well, that is great, and this is definitely, I think, 100% on. I haven't actually gone through the history to confirm this, but I think we can say with confidence that this is on me.
Well, I mean, the surrounding code looks like has not been touched in like 20 years.
Yeah, right. I mean, it is, and the question in the chat was like, well, how you never hit this? And Yeah.
Oh, right. So I ran into this while I was adding a test. Turns out, like in the kernel, we just have no optimize symbol calls. So there are no STT probe points that were like tail called in that way, at least in tree. So like we just never hit it in like the in like all the kernel modules that are just already included in the Illumos tree. And XCE it's like, developed outside of that. Also, it's in Rust, different tool chain, different rearranging the code. We just happened to hit it at that point.
That's right. And it's actually it's kind of a great thing about having now having Rust in the kernel allows us to get a whole bunch of different exposure, and it's been very okay, I know this is good. This is a bad look. There's a question in the chat of like, didn't Ben talk at a conference about finding some of the zero-day initiative discoveries for DTrace? Yes, that was in 2016. Yes, those are the videos that have been lost. Yes, that's a bad look, but it's like, so unfortunately that's I would love to recover those videos because of that. But part of what actually that's right. Do I need to have my lawyer? Actually, you know what? I feel my fortunately, it's also my financial advisor and personal physician, in addition to a hardware engineer. Adam Leventhal advises me not to answer. Yeah, use of Vimeo, totally. And actually those vulnerabilities were part of what drove me personally to Rust, because it was the vulnerabilities were somewhat chilling in that it was an easy mistake to make in C. But that's not what this is. This is more just I'm not even going to try to explain myself on this one. I'm just going to throw myself on the mercy of the court. And Lukeman, thank you very much for debugging this and debugging a 20-year-old bug and getting it fixed.
Not just that, but also I love that you pulled up like the Spark implementation, which describes handling of tail calls.
Yeah.
Whose lawyer are you anyway?
The restore followed by the call followed by the restore like brings me back in terms of like the restore and the delay slot. Like those are a simpler time.
Yeah, it's like, if we must patch to be a ret. Like, that's exactly what we need to do.
Awesome.
Yeah, cool.
Yeah, and right. And someone was saying how generally your probes would be kind of in the middle of the function. I think we were seeing this especially because we had like some kind of little functions like this that basically ended up being wrappers for the probes, where they would just do the probe. I believe I'd have to go look at how OPT did it, but like they just worked out in such a way that, the probe is at the very end of this call of this function. And because of, now that I think Kyle had said something, like they didn't need drop anymore. So all of a sudden they became eligible to be tail called in this context and trigger the bug. Fun. Yeah.
Very cool.
Awesome. Well, thanks again, Lukeman, and thanks for debugging that and fixing it. Really appreciate it. Great. All right.
Zoom out. Sorry.
Sure. Yeah.
Zoom out.
Zoom out a bit there.
There you go.
All right. Well, we're at the end of dtrace.conf 24, and I don't mean to sound surprised. That was really great.
You sound surprised.
That was great. That was a lot of fun.
I think people talk about like fatigue when assembling conferences, and we did not experience that. But I don't think people talk about unconference anxiety, which is
true. Yes.
Also a killer.
Yes. You may think, God, they did no work for this conference. That's not true. We did the emotional labor of panicking that this thing was going to be a total disaster.
Yeah. And I think it basically wasn't a disaster. Yeah.
It was not a disaster.
And it wasn't a disaster thanks to like all you who showed up. The stream was great. The chat was awesome. And of course, like to everyone who put together a presentation, whether it was yesterday, the day before, today, or even tomorrow.
But so just like to Ben, Kyle, Alan, Apo, Nahum, Dave, Chris, thank you so much. To Ryan, Ryan Goodfellow, to Robert, Eliza, and Lookman, thank you so much. Thanks for making this happen. Really appreciate it.
Really appreciate it. And Kevin Spring on logistics and Matthew Santabria, our newest Oxide employees, also been helping Kevin today on the logistics. Thank you very much for everything. And I think that we would obviously love your feedback on the kind of the online format. I think it worked really well. I liked having the Discord. I gotta say, I mean, I love the DTrace demographic. The Discord was just funny as hell. I mean, there was just the right up until the dtrace.conf 2016 video controversy Wikipedia link was just dropped. It's just it was funny and informative. I think it's great actually to have that kind of parallel track on and be able to have a conversation going on during talks and really supplementing the content. So it was great. So thank you very much. Thank you all for attending. I would like to say that in terms of we had, I mean, the numbers have obviously been fluctuating through the day, especially as people have gone off to other things, but we've had more people attend DTrace.conf 24 than any previous DTrace.conf. Thanks for being online. So thank you very much. And until the next Olympiad.
Until the next Olympiad.
All right. Thanks, everybody.
All right, good meeting.